which started 30 years back. My background is that I was in IIT Delhi as a student. After that, I did PhD from TIFR in Bombay. So I'm a mathematician, worked on algebraic groups, Lie groups, and now do no more number theory. After TIFR, I moved to ISI in Bangalore. There is an ISI, Indian Statistical Institute. So I've been, yes, I think Matthew is there. So I've been there from 99 to 2025 when I retired, and then I'm now a visiting professor at ICTS in Bangalore. Okay, so, and I wanted to convey one message, which is this. That's why I wrote this. You know? Can you read it? Yeah. So I think this is small enough message. And I would now kind of go around a little bit. Maybe we'll start from here and we'll go like that.
So, hello, my name is Shantanu Shukla. I'm a faculty at the Indian Institute of Science in the Department of Developmental Biology and Genetics. And I'm a microbiologist and ecologist, and I work on microbiomes and their role in host physiology and adaptation.
Hello, I'm Shudip Tutung. I am currently at Ashoka and currently in transition to JNCSR Bangalore. I am mostly interested, or my lab is mostly interested in understanding the evolution of metabolism and the effect of diet. So we use fruit fly as a system. And yeah, love to interact with all of you.
I should say that one of his recent articles in Resonance, you should have a look. It's really very nice. Yeah, I'll just go.
Hello, my name is Anil J. Elias. I just retired from IIT Delhi. I studied in IIT Madras for my PhD. I'm an inorganic chemist. Afterwards, for 10 years, I worked as an assistant and associate professor at IIT Kanpur. Last 24 years, I was still at IIT Delhi. I am one of the associate editors of Resonance. I have written 5-6 articles in Resonance also on different aspects of chemistry. Students who are in chemistry may know some of the textbooks I have written, which are, as textbooks accepted all over India for inorganic chemistry, organometallic chemistry, etc. Thank you.
Good morning. I'm R. Geeta. I've had a very checkered career. I did my bachelor's and master's in botany in Delhi University. And then I joined the ICAR. I was the Central Marine Fisheries Institute for several years. And then I decided to follow what I was interested in. This might be relevant to some of you. I finally realized I needed to follow my interests, went to do my PhD in University of Arizona in Tucson. And then I was on the faculty at Stony Brook for about ecology and evolution for about 11 years. And then I decided I needed to come back, and I was at the University of Delhi until about 6 years ago when I retired. At this time, I'm basically looking for what to do when I grow up.
So we're just introducing ourselves.
Well, my name is Dipankar Bhattacharya. I'm currently at Ashoka University in Sonipat. I head the Department of Physics over there, and I'm astrophysics professor. I did my PhD here in the Indian Institute of Science in the first batch of the joint astronomy program, of which Raman Institute was a part. And I did most of my PhD work here at this institute. After that, I joined this place as a faculty member. I was here until 2007. Then I moved to Indian University Center for Astronomy and Astrophysics in Pune University. So I was there for 15 years, and then I retired, and then I moved to Ashoka University after that. So my career has all been astrophysics right from the beginning.
Yeah, I wanted to say that many people, do you know what RRA stands for, right? Some people don't seem to know. So this is the statue of Raman, and you can see his name written in 4 languages. And I also happen to be a relative of Raman relative effect, so to say. So, Professor Mukunda.
Enough yesterday. Maybe I should not say much about myself, but about the activities of the academy, which are relevant, and this is part of that. Anyway, briefly, I was a student of Delhi University in St. Stephen's College. I think you were also there, is it? Okay. And then I joined TIFR Bombay as a student in theoretical physics in 1959. And after many years association with TIFR, I moved to Indian Institute of Science in 1972. This must sound to you like AD and BC, so long ago. And then I retired from the Indian Institute of Science in 2001. I live in Bangalore. Now a little bit about the academic activities. In 1994, the president of the academy, Professor Roddam Narasimha, a very distinguished aeronautical engineer of the country, he was the president, and he set up a panel to advise, to prepare a report on science education in India at the college and university levels, and to give recommendations to academy in what way it could help. So that was set up in 94, and I was part of that group of 8 or 10 people. We prepared a report, and we suggested, apart from general comments, we suggested some of the things that academy could undertake to do. I must mention, this academy was founded by C.V. Raman in 1934, and INSA in Delhi 1935, Nasi in Allahabad even earlier, 1930. Until our report, I believe, the academies had remained somewhat exclusive bodies. They elected fellows, they had annual meetings or even more frequent meetings, but there was not that much direct contact with science students in the country, science teachers, and people in other research institutions. It was limited. So after this 1994 report, starting in 98 or 97, 98, approximately that time, one of the recommendations of this committee was to have a summer research fellows program for students and teachers on an all India basis. And that was started, as I mentioned yesterday, in probably the first year of it was 1999, when there were just 3 or 4 students. It has grown over the years, and as I mentioned yesterday, and I may repeat, sometime around 2010 or 12, the number of applications was approximately 25,000 each year, and the number of fellowships given was about 2,000. Yesterday, I was told, I have not been in touch with it since a long time, I was told this year the number of applications was 30,000. But the number of fellowships offered had to be cut down to 1,000. Reason, at least when I was involved with all these programs, we were getting very generous support from the Department of Science and Technology, more importantly, on a timely basis. And we were able to offer 2,000 fellowships a year. Apparently, now the receipt of finances from DST is not so dependable. For that reason, and that makes me very sad, the number of fellowships offered had to be cut down from 2,000 to 1,000. Anyway, that is about this program of which all of you are part and all of you are beneficiaries. And I hope you will find this a valuable experience. Another recommendation of this panel of 94 was to start a journal of science education. So that was the origin of Resonance, and the first issue was in January 1996. So that's why it is now 30 years old. And it has had a series of chief editors, very distinguished people over the years. 2 other activities, part of this overall plan, is refresher courses for teachers. I think they are also running. They used to be of a 2-week duration, to help teachers in science and mathematics all over the country, engineering also, to improve their background knowledge so that the teaching quality improves. It was not meant to be a course where the latest research results of different fields are presented. No, the idea was to improve the quality of teaching at college level. And that has been going on very well. And there's one set of refresher courses I must mention. You must know that this was achieved in this country. One of my senior colleagues, Professor R. Srinivasan, who was a very distinguished physics professor at IIT Madras, after his retirement, he moved to Bangalore. He worked at this institute for many, many years. But he decided the state of experimental physics in colleges and universities needs a lot of improvement. And so he undertook to run refresher courses for teachers, 2-week duration, all over the country. And this must have been started around the year 2000, 2002 or something like that. Maybe he's 95 years old now. He lives in Mysore. But until 4 or 5 years ago, he was running these courses. And anyone take a guess, how many courses in experimental physics do you think he ran? He planned and had a team of people to help him. Anyone take a guess, how many courses do you think he ran? All over the country. I want you to have some idea. Huh? I'm glad you said it. It was about 100, just over 100. Can you imagine one person doing that? That is a great experience. And that is something I can never forget. The way he used to approach us each year for, this is my plan for this year, 2 courses, 3 courses. And now he's 95 years old and he is living in Mysore. The other last thing I want to say is all these activities of this academy were started around the time I described. In 2007, because these activities were going well, the other 2 national science academies, INSA in Delhi and NASI in Allahabad, they expressed their desire to join this effort. And that is why now it is a 3 academy set of activities. But I must say, the only reason these things could be done and they still are lasting is because of the structure of this Indian Academy of Sciences in Bangalore, the successive presidents, their support for these activities, and the staff of the academy. They have been outstanding, and without them, nothing could have been achieved. So thank you very much, and wish you all the best.
My name is Matthew. The various institutions I have been associated with have all been mentioned so far. Okay, IIT Delhi as an undergraduate student, well, master's. Indian Institute of Science for my PhD. TIFR is where I have worked for many years. I retired in 2020. Yeah, so now I'm a gentleman of leisure. Yeah. But when I was running a lab, we looked at how small molecules and ions crossed cell membranes, different cell membranes, plasma membrane, internal membranes. And part of that was applicable in neuroscience, and some of it was important in plant physiology. Yeah? And I'll talk about the latter this evening.
So we'll just briefly introduce ourselves.
Yeah, good morning. My name is Indulekha. I was teaching most of the time. Otherwise, I do some astronomy. Plus, you have these science congresses, so I have worked with some data that is of local relevance because science congresses have themes which are of local relevance. Apart from that, I've done all sorts of little things, explainable AI, some zonification, if you know what that means, and lots of interesting things. So hope you enjoy detective stories. Science is a detective story.
So what I'll do is just quickly introduce yourself, where you're from and what program you're doing. What is your subject?
I'm from Chennai, and the program I'm in is high energy physics at ISC Bangalore. My name is Ayan, and
Hi, I'm Adriza Yogi. I'm from Jadavpur University, Kolkata, and I'm doing my SRFP at ISC Bangalore in the Department of Mechanical Engineering.
good morning. My name is Saptak Ghosh. I'm also from Jadavpur University, and I'm doing my fellowship program at ISC Bangalore in the Department of Mechanical Engineering.
Good morning, I am Harshavardhan. I am from NIT Patna. I am doing my SRFP intern at IISc in Material Engineering Department.
Good morning, myself Shruti Soumya Mishra, and I'm from Bhubaneswar, Odisha, and I'm doing my SRFP in Mechanical Engineering, IISc Bangalore.
Good morning, my name is Darshan Kamble. I am from ICT Mumbai. I am doing my internship at Chemical Sciences Department, IPC.
Good morning, professors and all my friends. My name is Shrishti Kumari, and currently I am pursuing BSc Physics from Amity University, Jharkhand, and I'm an intern at JNCA-SR under Professor Sundareshan. Thank you.
Warm greetings, everyone. I'm Sadiksha from Tamil Nadu. I'm doing my undergraduate program at chemistry. I'm currently doing my SRF program at IISc Bangalore at IPC department.
Good morning, one and all present here. I'm Minu from College of Engineering, Guindy, Anna University, Tamil Nadu. And at IISc, I'm doing my intern as a SRF fellow under Saptashi Basu sir in Mechanical Department. And I'm undergoing research on droplet dynamics.
Good morning, everyone. Myself, Vahini. I'm from Andhra University from Andhra Pradesh. So I'm currently doing my SRF program under Professor Govindas Gupta, sir, professor. So I'm working on biomass sources to the concept of biorefinery concepts.
Good morning, everyone. I am Pragati from CSR Sikri, Tamil Nadu. I am doing my internship at Chemical Engineering Department at IISc Bangalore.
Good morning, everyone. I am Drishti. I am doing Masters in Mathematics from Harish Chandra Research Institute, and here I am doing my internship in IISc under Professor Naveen Kashyap and in ECE department.
Good morning, everyone. My name is Sakshi Raj, and I am from NIT Patna, currently doing my BTech. I will be entering 4th year. And I am doing my intern at IISc under Professor Sushmita Das on microthruster used in satellites.
Good morning, everyone. My name is Ujjal Barman. I am from IIT Kharagpur. I am pursuing my internship at IISc Bangalore in Mechanical Engineering Department.
Good morning, everyone. I am Bhuvanesh, and I am doing my BTech from NIT Trichy, Civil Engineering. And I am working under Dr. Devraj Ghosh, broadly under computation topology in IISc Bangalore.
Good morning, everyone. I am Purvai Chandrasen from IISER Bhopal. I am pursuing data science. I'm a third year student going into 4th, and my current interest is in neuroscience in monkeys right now. So the project is analyzing, using deep learning models to analyze data, neural data from monkeys.
Good morning, everyone. Myself, Pragya Paramita Pradhan. I'm from Vellore Institute of Technology. I'm doing masters in microbiology, and here I am doing my internship in IISc Bangalore in neuroscience department on C. elegans, that how they are exploring the food and their locomotion mostly.
Good morning, everyone. I'm Bhumika Kundu, and I'm currently pursuing my BTech in Chemical Engineering from Jadavpur University. And currently, I am under Professor Sanjeev Gupta in the Interfacial and Colloidal Lab in the Department of Chemical Engineering at IISc Bangalore. Thank you.
Good morning, everyone. I'm Shubhadeep Chandra from Kolkata, West Bengal. I am pursuing my physics undergrad at St. Xavier's College, Kolkata. And currently, I'm pursuing my research in statistical physics and condensed matter group at the International Center for Theoretical Sciences, TIF at Bangalore.
Good morning, everyone. I'm Shomik Pal. I'm from Jadavpur University, Kolkata. In Bangalore, I'm currently pursuing my SRF under Professor Gaurav Tomar. Mechanical Engineering Department.
Good morning, everyone. My name is Aryan Shah. I'm from NIT Durgapur, and my fellowship is from ISC under Professor Alok Kumar, Mechanical Engineering.
Good morning, everyone. Myself, Jasweenus. I'm currently pursuing my master's in biotechnology from Guru Nanak Dev University, Amritsar, and here I'm working as an intern at IISc Bangalore in biochemistry lab.
Good morning, everyone. My name is Kripa. I'm studying integrated MSc in Acharya Nagarjuna University, Andhra Pradesh. I'm here working as internship under Deepankar Das Sharma at Chemical Sciences Building, SSCO unit. Thank you.
Good morning, everyone. I am Ashmita from, I'm currently pursuing my integrated bachelor's and master's degree from Aizer Mohali, and I am working in Reva University in the Department of Biotechnology on GPCR signaling in insulin secretion.
Hello everyone, I'm Jagruti Vakpanjar and I'm from IISER Bhopal pursuing my BSMS and I'm a biology major. Here at IISc, I'm doing my internship in biochemistry department.
Good morning, everyone. I am Sritama Ghosh. I am pursuing my master's in chemistry from Delhi University, and here I am working under Professor Jagidar.
Good morning, everyone. I am Jyotsna. Currently, I am a master's student at Indian Institute of Technology, Bombay, and here I am working under Professor Namrata, studying how the cells interact with the substrate and what changes are observed upon application of forces. Thank you.
Hello everyone, myself Boshali Vora. I am doing my master's in Rajiv Gandhi University, Arunachal. I am doing my SRF program under Dr. Surya Sarthi Bose with Polymer Processing Group. Thank you.
Good morning, I'm Shikha Gupta and I'm pursuing my integrated MSc from Naizer Bhubaneswar, and I'm doing the SRFP program in IIA in astrophysics under Dr. Aruna Goswami.
Hello everyone, myself Pallavi Pal. I'm pursuing my BTech. I've completed my second year now and from NIT Hamirpur in Mechanical Engineering Department. Right now I'm under Dr. Shubhadeep Mandal in Mechanical Engineering Department as an intern.
Good evening, everyone. My name is Kritika Masti and I'm a student from NIT Raipur. Recently, I have completed my second year, moving towards third year. Right now, I'm doing internship under Mr. Shubhadeep Mandal in Mechanical Department, and my topic is computational programming of microswimmers. Thank you.
Good morning, everyone. I'm Geeta. I work for Resonance, and incidentally, I complete 10 years with Resonance today. So, welcome all.
Hi everyone, I'm Anisha. I am pursuing a master's in biomedical science from DU. I'm interning under Professor Varatharajan in molecular biophysics department. Thank you.
Hello everyone, I'm Ria and I'm from Ferguson College in Pune. I'm pursuing my bachelor's in mathematics and currently I'm an intern under Soumya Das in IISc Bangalore and I'm doing my project on algebraic number theory.
Hello everyone, I am Tejaswini. I'm a mathematics undergrad at Delhi University and I am doing my fellowship at IISc in the Department of Civil Engineering.
Hello everyone, my name is Tejaswini Chedilla. I am from RGKT RK Valley from Andhra Pradesh. Now I am currently pursuing my internship at CMTI in the MEMS technology.
Hello everyone, I am Ajay. I am pursuing bachelor degree at Vishnu Institute of Technology, Andhra. I am currently pursuing intern at CMDI, Central Manufacturing Technology Institute, about on cyber security. Thank you.
Hello everyone, I'm Hasni. I'm currently pursuing bachelor's at SVCW, Andhra Pradesh. I'm doing internship at IISc under Departments of Electronic Systems under Dr. TV Prabhakar.
Good morning, everyone. My name is Riddhiman Ganguly. I am a bachelor's in biomedical engineering at MIT Manipal. I'm exploring hydrogel fabrication and analysis for immunoassays at Achira Labs Private Limited under Dr. Dhananjay Dendukuri. Thank you.
Good morning, everyone. My name is Amruta Patil. I am currently pursuing BSc Biotechnology third year, Rajashri Shahu Mahavidyalaya, Latur, in Maharashtra. Currently, I am working under the Dr. Pratibha Ranganathan ma'am in Center for Human Genetics in Cancer Lab. Thank you.
Hello all, I'm Nitya. I'm from Salem and I'm pursuing my BSc Biotechnology and I'm a third year student right now. And I'm interning at the Center for Human Genetics under Dr. Jairama sir and I'm learning conventional cytogenetics now. Thank you all.
Good morning, everyone. My name is Anushka Haldar. I'm currently pursuing integrated MSc in Life Sciences from Tezpur Central University. I'm currently an intern at IISc in the Computational and Data Sciences Department. Thank you.
Good morning, everyone. I'm Kirti Priya. I'm currently pursuing BSc Biochemistry in PhD College of Arts and Science. Yeah. So, PhD College of Arts and Science, and I currently work under the Pratibha Ranganathan ma'am at Center for Human Genetics. Thank you.
Hello everyone, I am Sunny. I am an undergrad currently doing SRF at Electrical Engineering Department at IISc. I am from Rajasthan.
Good morning everyone. I am Chaitanya from Sri Venkateswara College of Engineering, Tirupati. Here I am working under Anshu Pandey, SSCU department. Thank you.
Hello, I am Sashank, undergraduate at IIT Kharagpur. I am currently an intern at CDS under Professor Ratikanta Bera.
Good morning everyone, I am Ajinkya Sirsagar. I am currently pursuing my BTech degree from SVP CET Nagpur. I am working on experimental study of microstructure of cementitious hydrated cement paste and under Dr. Keshav Bharadwaj. Thank you.
Suprabhat, I am Amit Vikram Sonu, BSc second year student of Central University of South Bihar, Gaya. So I am working under Aqueous Zinc and Battery under Professor Praveer Barpanda in Material Research Center of IISc Bangalore.
Good morning everyone. I am Haryansh Gupta. I am from Jammu and Kashmir. I am currently working in the domain of digital signal processing.
Good morning everyone. Myself Yuvraj Singh from West Bengal. I am currently studying in MCKB Institute of Engineering, doing my BTech in Computer Science and Engineering, a specialization in AIML. Currently I am doing internship at Material Science Department in IISc Bangalore under the Professor Dr. Ankur Chauhan. Thank you.
Good morning everyone. I am Prashant Kumar Gupta, currently pursuing my integrated BSc B.Ed course at IIT Kharagpur, and currently I am intern here at Raman Research Institute in Pramod Pulkut sir.
Good morning everyone. My name is Kishan Lal Sharma or I am pursuing my master in physics at Central University of Rajasthan, and currently I am working in germanium based hybrid perovskite and Dipankar Das Sharma, SSCU IISc Bangalore.
Good morning everyone, I am Sankalp Panchal. I am doing my masters in Banaras Hindu University and I am doing my fellowship under Dr. Vidya's lab in molecular biophysics unit IISc.
Good morning everyone, my name is Rishi. I am from IIT Dhanbad and currently I am doing my fellowship at IISc under Department of Electronic System Engineering.
Hello everyone, my name is Anurag Patel. I am from Varanasi, Uttar Pradesh and I am doing BTech from Civil Engineering at NITK, and here I am doing my internship at IISc on payment design.
Hello everyone, my name is Sheikh Mustaqim from PMEC Odisha. Currently I am doing my fellowship at Department of Electronic System Engineering IISc.
Good morning everyone, I am Arvind. I am pursuing BTech Electrical Engineering in Central University of Karnataka. I am working under Dr. Nagahanmaya at CMTI, working on three-phase inverters.
Hello everyone, I am Fiza Khan from Jamia Millia Islamia and currently I am doing my bachelor's with research in biotechnology, and I am interning here at CSIR CMAP under the guidance of Dr. Dinesh A. Nagegovda, and I am working on aromatic plants.
Good morning and peace be upon all of you. My name is Rida and I'm pursuing bachelor's in pharmaceuticals from Jammu University. I'm from Jammu and Kashmir.
and currently I'm working at CDS Computation and Data Science Department under Professor Debnath Pal. Thank you.
Good morning, I am Zahira. I am from Kerala. I am pursuing my MSc in Chemistry from Central University of Kerala. Currently, I am doing my internship under Dr. Abhishek Mondal, SSU Unit, IIC Bangalore.
Good morning, everyone. I am Kostava Anda from Assam. I am currently pursuing my integrated MSc course in chemistry from Tezpur University. Here I am working as an SRF intern under Professor D.P. Hari in IIC Bangalore, Chemical Science Department. Thank you.
Hello, good morning everyone. I am Ronak Dubey pursuing my masters from IIT Bombay. I am currently doing my intern at JNCSR under Professor Sebastian Peter in material chemistry. Thank you.
Good morning everyone. Myself Pragyan Bagchi. I am from Kolkata, West Bengal. Currently I am a BTech student at NIT Durgapur and I am interning under Dr. Rishikesh Narayanan from the Department of Molecular Biophysics, IISc Bangalore.
Good morning, everyone. My name is Agam Borwa from Assam, and I am doing BSMS in IISER Pune. I am interning in the field of astrophysics. My topic is FRBs as probe of understanding cosmic Brownian distribution in the universe under the guidance of Pratik Sharma from IISc Bangalore. Thank you.
Good morning, everyone. I am Nayana. I am studied second year BSc in Rajajana First Grade College. Thank you.
Good morning everyone, myself Bhagyashree. I am from GFGC Rajajinagar. I am currently pursuing my Bachelor of Science in second year.
Hi everyone, I am Fatima Anisa. I am pursuing my second year BSc in Chemistry at Bangalore City University.
Good morning everyone, my name is Manasa. I am currently the second year undergraduate student.
Hello everyone, my name is Tanu. I am from Bangalore. I am currently pursuing my first year BSc in Chemistry, Bangalore City University.
Good morning everyone, I am Lakshmi. I currently second year undergraduate student.
Good morning everyone. I am Ashwini. I am currently second year undergraduate student pursuing my degree in chemistry at Bangalore City University.
Good morning everyone, my name is Archana. I am studying BSc Chemistry in Bangalore and I am from Bangalore.
Good morning everyone, I am Mahadevi C. PMCS second sem, GFGC Rajajinagar, Bangalore City University.
Good morning all, I am Sachin. Now I am from Bangalore. I am pursuing BSc second year from Manmohan Singh University.
Hello everyone, my name is Aditya Poddar. I am from IISER Bhopal, just currently completed my third year and I am interning at Indian Institute of Astrophysics under Professor Umanath Kamath. Thank you.
Hi everyone, I am Divya. I am currently pursuing BTech Mechanical Engineering in NIT Trichy and I am interning under Dr. Ram Sharan in Mechanical Department of IISc.
So thank you everybody, and I must tell people that apart from the interns here, apart from the summer research fellows, some of the local students are also attending. That's why they didn't mention any internship. So all of you welcome again. And I want to say that one of the ladies who is not present here, her name is Pushpa. She is also behind the scenes worker in Resonance. So like Geeta, who has completed 10 years today, Pushpa has completed many more years also now. So I think although we are learning late, I guess we can sort of eat up into the lunchtime, so to say. So maybe we can start now, and I request Professor Geeta to chair this session.
Thank you. So let me, without much more, invite Dr. Sanyukta Roy, who is at the RRI, and she works very nicely. We have her title there, so you don't need me to read it out to you. She got her PhD in, I've forgotten, TIFR, and she went on to do a postdoc in Europe, Paris, and then somewhere in Italy, Florence. And she got a prize a couple of times, I think, for her Bose-Einstein condensate, which I have no idea what it means, but I'm sure it'll be part of what she's going to talk about. Please come.
Can you hear me? Good morning, everyone. So I thank the organizers for inviting me to give a talk in this very nice program. So today I will take you to a very exciting world of atoms near absolute zero temperature. So I've prepared my talk specially for the students. The experts, please bear with me. So today I'll talk about how we can do quantum technology with atoms near absolute zero temperature. And before that, I'll tell you how we actually go to absolute zero temperature in our lab. So the outline of my talk is, first I'll give you an introduction to ultra-cold atoms and Bose-Einstein condensate, how we realize Bose-Einstein condensation in the lab, and then I'll talk about how we can actually use these cold atoms to do quantum technology. And then I'll talk about ultra-cold atom experiments on Rydberg atoms, which we are doing here at Raman Research Institute. So Bose-Einstein condensation has a very strong Indian connection, as you can see. It was predicted way back in 1924. So by Satyendranath Bose and Albert Einstein. So Satyendranath Bose had worked out a new statistics for photons while he was teaching at Dhaka University. And he wrote an article, Planck's Law and the Hypothesis of Light Quanta. And he sent this work to Albert Einstein. Einstein immediately realized the importance of this work, and he adapted this seminal work by Bose to apply it to other bosonic particles and atoms, and thereafter predicted the phenomena of Bose-Einstein condensation. It was first observed in strongly interacting system in 1938, but it was observed in weakly interacting system more close to the predicted Bose-Einstein condensation phenomena in 1995. So what was the prediction of Bose-Einstein condensation? It says that the lowest energy state can be occupied by a large number of particles well above the absolute zero temperature. So when the temperature is very low, close to absolute zero temperature, the bosonic particles gather together at the lowest quantum state, even without any attractive interaction between the particles. And this is called Bose-Einstein condensation. So one specialty of this state of matter, as you'll see later in my talk, that all these particles are in phase. They are phase coherent. They're like a giant matter wave. So let me give you a simplified picture of Bose-Einstein condensation. So at very high temperatures, you know, like in the room in this room, the atoms are moving very fast. They are moving like billiard balls. They're classical particles. And as you go lower and lower in temperature, the de Broglie wavelength, which is inversely proportional to the square root of temperature, increases. So they behave more like waves than particles. So as you reach what is called a critical temperature for Bose-Einstein condensation, these waves, or you can say matter waves, they overlap when the de Broglie wavelength becomes equal to the interparticle distance. And this is how you get a phase transition to Bose-Einstein condensation. And at absolute zero temperature, we get a pure Bose-Einstein condensate. which is like a giant matter wave because it's a coherent state of matter. So let me show you how this happens. So you can see at high temperature, the particles or atoms are moving very fast like billiard balls. And as you're lowering the temperature, please look at the thermometer, you can see that there's a fuzzy behavior which is coming into picture. Okay? So this de Broglie wavelengths are increasing, they're behaving more like waves, and you can see they're starting to overlap with each other, and the size of the waves are increasing. And as you go lower and lower in temperature, you can see they are merging almost together, and after the critical temperature, they go to the lowest quantum state and form what is called the Bose-Einstein condensate. So how cool do we have to cool down the atoms to go to this coherent state of matter? So let's look at the temperatures. You know the sun surface, which is a few thousand Kelvin, then freezing water is at 0 degrees centigrade, or then you have liquid nitrogen at 77 Kelvin, which is very cold, then liquid helium at 4 Kelvin, and we all know cosmic microwave background is at 2.7 Kelvin, but we are cooling down even more. So we use several processes, which I'll not go into details right now, but here we go all the way down to the temperature scale, all the way to nanokelvin temperatures to get the atoms into Bose-Einstein condensate. So, which is very close to the absolute 0 temperature. And here the record for the lowest temperature is 38 picokelvin, which was the Bose-Einstein condensate, which was achieved in space by NASA. And we can say that it's the coldest matter in the universe. So as an experimentalist, we will think that how to achieve this in a lab. So we need to know the physical parameters which we have to achieve to get to such low temperatures. So the requirement for BC is that the phase space density, which is the product of the atom number density and cube of the de Broglie wavelength, to be of the order of 1. Now, this is the de Broglie wavelength, which I had mentioned before, that it is inversely proportional to the square root of temperature. That means as we lower the temperature, the larger is the de Broglie wavelength. And for Bose-Einstein condensate, we need like 300 nanometer, which corresponds to a temperature of around few hundred nanokelvin, and we need a large atom number density, okay, which is N, which is roughly around 10 raised to 14 to 10 raised to 15 atoms per centimeter cube. Now, it is not achieved in a single step. Please don't go into the details. The point which I want to make is that this lowering of temperature or cooling down of the temperature of atoms to near absolute 0 temperature, it takes several steps. And the success of any of the steps crucially depends on the success of the earlier step. Okay? So first we do what is called a laser cooling and magneto-optical trapping, where we achieve a temperature of 100 microkelvin and we get a phase space density of 10 minus 6, which is way below 1, which we want to achieve. Then we do further cooling using what is called a subdoppler cooling and temporal dark mode, and we get a phase space density of 10 minus 3. And then we load in optical or magnetic trap. We again have slightly more phase space density. And then we do evaporative cooling to Bose-Einstein condensate, where we get the phase transition to get the Bose-Einstein condensate. So I will touch upon these steps in this talk. So here you can see how we step by step go to the final goal of achieving the phase space density for Bose-Einstein condensation. So the first step is laser cooling and trapping, which is taking the atoms which are at room temperature and cool them to microkelvin temperatures, not yet nanokelvin. So how do we do that? So the principle is similar to why we have a tail of the comet. You have seen comets where you have a tail which is pointing away from the sunlight because of the radiation pressure of the sun. So we use this radiation pressure of light to cool down atoms. So let's see, how do we do cool down atoms with light? So suppose we have a laser beam coming in one direction, and we have an atom, and you can see this energy level of the atom. And what we do is we have this laser beam, the frequency of this laser beam slightly red detuned. That means the frequency is slightly less than the atomic transition frequency. So why do we do that? Because the atoms are moving and it has a Doppler shift. Okay? So to compensate for the Doppler shift, we already have this laser frequency less than the atomic transition frequency. So when the atom is moving towards the laser beam, it sees the frequency upshifted and comes on resonance, absorbs a photon, and it gets a momentum kick opposite to its direction of motion. And when it gets a momentum kick opposite to its direction of velocity, it gets slowed down. Now, when it absorbs a photon, it has to emit the photon. But then you will see that what happens to the emitted photon. But that's a spontaneous emission. That's a random process, and it happens in random direction. To give you an idea about numbers, in 1 second, typically there is 10⁶ times absorption and spontaneous emission. So in each absorption, the atom gets slowed down, but the effect of the spontaneous emission, which happens in random direction, that averages out to be 0. So on an average, the atom gets slowed down. So you can see there's a strong interplay between the dynamics of internal and external degrees of freedom, which leads to cooling of atoms. Now, here you can see how the force, there's a damping force which cools down the atom. So this force is proportional to the velocity in the opposite direction. So you can see it always has opposite sign for the velocity. Here you see the force as a function of velocity, and it's like a frictional force or damping force which cools down the atom. So here you can see in this linear regime, which is called the capture velocity. So only when atoms are in this velocity range, then only they can capture and cool down the atoms. So this is a velocity dependent force, or we can also say friction damping. So this is only in 2 directions. What happens when we have it in all 3 dimensions, because we have to cool down in all 3 directions, it's called an optical molasses, and the atom feels a viscous force within the laser beams which cools down the atoms. And here you can see a real photograph of atoms, sodium atoms, which has yellow, which cools down with yellow light. So here you can see the cooled optical molasses, which is at the center, and you have this laser beam in all 3 directions. But this is only damping, this is only cooling, there's no trapping. If you want to do some meaningful experiments on the atom, we have to confine it at a point in space. So how do we do that? So we do it using a position-dependent force. So what we do is, we use a spatially varying magnetic field, using what is called the anti-Helmholtz coil, where you have currents, we have 2 coils, where current is running in an opposite direction, which causes a 0 at the center, and then it increases linearly in all directions. So as the atom tries to move away from the center, it comes into resonance because of the Z-band shift, and it feels a force which pushes it towards the center. So more it comes out from the center, more force it gets, which pushes it towards the center. It's like a restoring force in a spring. So more you're stretching it, the more force you find, which is towards the center. So this is this restoring force, like a spring, which traps the atom at the center of the strap, which is called a magneto-optical trap. So the configuration of the magnet-optical trap is you have 6 laser beams which is forming the optical molasses, and then you have 2 coils which creates this magnetic field with 0 at the center to trap the atoms. So we have trapping and cooling all together. So the typical parameters of the magnet-optical trap is that we can go to 100 microkelvin temperatures, and the typical velocities, I mean, you can make a comparison. The typical velocity of atoms at room temperature is like 30,000 centimeters per second, but we can reduce it to few centimeters per second when we cool down atoms in a magnet-optical trap. So here you can see a picture of cold atoms in the magnet-optical trap here. And I want to mention that these atoms are kept at ultra-high vacuum because you want to evacuate the chamber completely so that the hot atoms don't knock out these cold atoms with low energy out of the trap. So here you can see the atoms are inside a vacuum chamber where the pressure is around 10 minus 11 torr, which is like 100 billion times less than the atmospheric pressure. So for the discovery of laser cooling and trapping, for developing methods to cool and trap atoms with laser, Stephen Chu, Claude Cohen-Tannoudji, and William Phillips had received the Nobel Prize in 1997. So you may be wondering, how do we know that we are cooling to such low temperatures? So as you can see, the velocity is proportional to the square root of temperature. So what we do is we release the atom from the trap and let it expand because of its momentum, because of its temperature. And as it expands at the rate which is depending on its temperature. Larger the temperature, faster it will expand. So we get the expansion rate of the atoms as we release the atoms from the trap, and from that we get the temperature of the atoms. So still we are at microkelvin temperatures, but if you recall, we needed around 100 nanokelvin temperatures to go to the Bose-Einstein condensate. So what is stopping us from just using laser cooling to go to the Bose-Einstein condensate? So this is something called single photon recoil limit. That means the heating of the atoms, if the atom absorbs a single photon. So heating is like of the order of 1 microkelvin. So if you heat up the atoms of the order of 1 microkelvin, you cannot cool down below that. This is because we have near resonant photons. So we need a dark trap where you don't have absorption emission of photons, where you can cool down the atoms below this limit and go to nanokelvin temperatures. So the solutions are dark traps, where we can do what is called an evaporative cooling. And there are 2 kinds of traps, dark traps. One is magnetic trap and one is optical dipole trap. So I'll explain them in a minute. So what is optical dipole trap? So in optical dipole trap, we have the laser beam very, very far away from the resonance. There's hardly any absorption or emission of photons. But then you have the dipole force, which is trapping the atoms. So if you focus this laser beam to a very small focal spot, you can create a potential where atoms can be trapped. So the trap depth is proportional to the intensity of the laser beam, and the scattering rate is inversely proportional to the square of the detuning. So we want to have very high intensity and very large detuning for this optical dipole trap. So as when I did my PhD in TFR Mumbai, we had this dipole trap. Here you can see the cold atoms trapped in this optical dipole trap, and which was loaded from a magnet-optical trap. You can see the atoms which are not loaded in the optical dipole trap, they're just falling away, and we have just the trapped atoms there. So another kind of trap is the magnetic trap, where we again have atom current in the opposite direction, which creates a 0 at the center, and we form what is called a quadrupole trap to trap atoms here. So it's like, have a spinning magnet held up because of this magnetic force. So it's the same principle by which we trap atoms in the magnetic trap. So how do we further cool down atoms to nanokelvin temperatures? So when we have a trap, so what happens? We lower the depth of the trap. That means we lower the, for the optical dipole trap, we lower the intensity of the beam, which lowers the trap depth. So what happens? The atoms which are hot, they're at the periphery of the trap, and they move out of the trap. And the remaining atoms, they undergo elastic collisions, and the overall temperature reduces. And finally, we get a lowest possible temperature in this trap, and we achieve the Bose-Einstein condensate where all the atoms are in the lowest quantum state of the trap. So it's like cooling of coffee in your cup. So the higher energy molecules are just evaporating away, and then your coffee gets cooled down because what is remaining are the lower or the colder molecules. So that's why it's called evaporative cooling. So before I tell you how do we recognize that we have got the Bose-Einstein condensate. So we have to recognize the Bose-Einstein condensate in the experiment. So before I go into that, I'll tell you the role of interaction has a very important, significant role in recognizing the Bose-Einstein condensate. So in a dilute Bose gas, it follows what is called a Gross-Pitaevsky equation, which is a nonlinear Schrodinger equation. So because of the strong interaction between atoms in the Bose-Einstein condensate, and this is the interaction term, which is the mean field interaction. So in the Thomas Fermi limit, or we can say the kinetic energy is 0 because we are cooling down atoms to very low temperatures, we can neglect this momentum term, okay? And then we have this as the atomic density profile, and this is what is called a parabolic or max function, where we get a parabolic profile for the Bose-Einstein condensate. So if the atoms are not in Bose-Einstein condensate, it will have a Gaussian profile like normal thermal atoms, but as it goes to the Bose-Einstein condensate, the profile changes. It's no longer a Gaussian profile for the atomic density, it follows a parabolic profile because of this interaction. So that's how we can recognize that the atoms are in the Bose-Einstein condensate. So this is the phase transition temperature for Bose-Einstein condensate. So what is the signature for atoms in a harmonically trapped BC? The harmonic trap in which we are trapping the atoms has a very important role to play. So in uniform Bose gas, you cannot recognize very clearly because it's, the condensation is both in position and momentum space. So in a harmonic trap, the onset of BC is observed as a sharp peak at the center, which has a parabolic profile. It is distinguished from the thermal profile, which is in the background. So here you can see a profile of our atomic density, where atoms were in a Bose-Einstein condensate. You can see a clear difference in the profile. So here you can see a dense part at the center, where which is the atoms in the Bose-Einstein condensate, and you can see there a dilute background gas, which are still in the thermal state. So here is the density profile of our Bose-Einstein condensate at TFR Mumbai. So the coexistence of condensate and thermal cloud in this bimodal profile is the characteristics of Bose-Einstein condensate in a harmonic trap. So here you can see where we have no onset of Bose-Einstein condensate. It's a dilute gas, which is only thermal atoms. So as we go below the phase transition temperature, we have a coexistence of both thermal atoms and atoms in the Bose-Einstein condensate, which is the dense part at the center. And as we cool down the temperatures further, we get a pure Bose-Einstein condensate. So I just show you the process by which one can achieve a Bose-Einstein condensate. So here you can see still a thermal gas, and then you can see a sharp peak at the center, which is the onset of Bose-Einstein condensation. So for realizing the Bose-Einstein condensate for the first time in dilute atomic gases, Eric Cornell, Wolfgang Ketterle, and Carl Wieman were awarded the Nobel Prize in 2001. So what is the specialty of this Bose-Einstein condensate? Why is it so interesting? Because it's a coherent state of matter, where atoms are like marching in locksteps. Like you have seen soldiers in Republic Day who are marching in locksteps. Their steps are matching with each other. That means they are walking coherently. Or here the atoms are in the same way, are like soldiers marching in locksteps because they are phase coherent with each other. So they are like a giant matter wave. So here is the signatures of Bose-Einstein condensate, which we achieved in TFR Mumbai. Here you can see the thermal gas, and then you have a bimodal profile, and then you have almost a pure Bose-Einstein condensate. So this was our BC team. So here is the experimental setup for the Bose-Einstein condensate. So here in this jungle of optics, we had the Bose-Einstein condensate somewhere here. I mean, this whole set of optics, they're all equally important. If we take out one, it will not work. So the challenge of these kind of experiments is not to have the individual parts working successfully, but the challenge is to have all the parts of the experiment working together successfully. So that's how you can get this Bose-Einstein condensate. So we had this chamber here where we had achieved the Bose-Einstein condensate. And so this happens to be the first Bose-Einstein condensate in India. And this was our humble tribute to Satyendranath Bose. So this is, you can see the BC phase transition where we have no condensation. And as soon as we reach the BC phase transition, we have a sudden jump in the condensate fraction in our atoms. So the international media had taken note of this achievement, and here you can see it was highlighted as condensation in the country of Satyendranath Bose, and it was much before there was a Bose-Einstein condensate in Spain, for example. So I'll tell you about another BC experiment which had built up in Florence in Italy. This was a potassium BC experiment. Here you can see it was slightly more advanced. So this was a 3-chamber system where we cooled down the atoms and took them to what is called a science cell and did our experiments on Bose-Einstein condensate there. So there's cooled atoms here, and then it was transferred using a magnetic transport to the main science cell where we did all our experiments with Bose-Einstein condensate. So this was the phase transition for Bose-Einstein condensate. Here you can see thermal gas and then bimodal profile and a pure Bose-Einstein condensate. So as I was saying, what makes Bose-Einstein condensate so special? Because it's like coherent laser light. So as you can see in coherent laser light, the light is all phase coherent and we can see an interference pattern, but the thermal atoms are like incoherent LED light where we don't have a phase coherence between them. So here you can see interference pattern, and in analogy we can see the same for atoms as well. So here you can see that thermal atoms here, and the Bose-Einstein condensate is coherent as we could see in the earlier slide. So the evidence for coherence is that we can see an interference pattern. So what happens if the BC is divided into 2 and then overlapped? You could see an interference pattern as you can see an interference using a coherent laser light. So this is the evidence that Bose-Einstein condensate is a coherent state of matter. So Bose-Einstein condensate is also a superfluid. If you rotate it, you will have vortices, as you can see you have in superconductors. And if you rotate the BC, you can see vortices as well, which is evidence for that the BC is also a superfluid, which is flowing without resistance. So this was the realization of Bose-Einstein condensate, and then I come to what can it be used for. So as was the title of my talk, I would now describe how can we do quantum technology with cold atoms. So the idea of quantum simulation came from Richard Feynman, who said we can control one quantum system using another. So how can we do quantum simulation with atoms, cold atoms? So what we do is we can load these atoms in what is called an optical lattice. So this emulates the solid state lattice, where electrons are moving in solid state lattice. In the same way, we can have Bose-Einstein condensate or quantum gases in an optical lattice. So optical lattice is formed by retroreflecting a focused laser beam, where you have interference pattern, and then you have a standing wave, and atoms can be trapped in the antinodes of this standing wave and form what is called an optical lattice. So quantum gases in optical lattices emulates electrons in solid state lattice. So why it's very promising? Because it's a highly controllable system. We can control any parameter of this system. We can control the dimensions, the lattice geometry, the interaction between atoms, and everything about it. So we can go to parameter range well beyond that achievable in the system which we are simulating. So we can put it in any geometry. We can do checkerboard, triangular, or honeycomb lattice to do a simulation of various kind of physical systems. Because electrons in a solid state lattice or in a solid state system, it's not possible to explore the physics of the system in its pure form, because there is very strong Coulomb interaction. But here we can completely control the interaction, and we can study the physics of the system with full controllable parameters and just study the physics of the problem in its pure form by controlling all the parameters in the system. So if we have a 1D optical lattice, we can make a 2D geometry, because if we have Bose-Einstein condensate trapped in a 1D lattice, we'll have an array of pancake-shaped traps, which are each in a 2-dimension form. If we have a 2D optical lattice, we can have them in 1D structures, and we can study physics in 1D. And of course, this is the 3D optical lattice. So why this is very important? We know that new materials change the world. So we have seen kids playing with Legos, and with very few kinds of Legos, they can make beautiful structures. So in the same way, we can use atoms to simulate various kinds of materials and study the physics of these new materials and even design these new materials. So we can explore the physics of these materials by arranging these cold atoms in various configurations. And probably we can explore the physics of quantum magnetism or even high temperature superconductors. So for this, we have built up an experiment here at Raman Research Institute, where we have not a single species of BEC, but we are making a quantum mixture of two kinds of atoms, sodium and potassium. So this is the schematic design of the experiment, and here is the real picture of the experiment, where we have sodium and potassium atoms cooled together, and they're mixed together, and we form a quantum mixture of these two atoms. So here you can see a cold cloud of potassium atoms and cold cloud of sodium atoms here in vacuum chamber. So why we want a mixture? Because in a mixture we can address many physics problems which are not possible in single species experiment. For example, we know that in quarks, which are like fermionic, the interaction is mediated by gluons, which are bosons. In Cooper pairs, electrons, which are fermionic, their interaction is mediated by phonons, which are again bosons. And in polarons, the electrons are dressed by lattice vibrations to form this polaron. So we can see that in many of these physical systems, the interaction between fermions is mediated by bosons. So this was our motivation to build this experiment. Because in high temperature superconductors, for conventional superconductor, the Cooper pairing it shows S-wave symmetry, which is spherical. But in high temperature superconductors, it's P-wave or D-wave symmetry. So in this kind of post-Fermi mixture of sodium and potassium, it was predicted that we can have symmetry, P-wave or D-wave symmetry, which is not observed in conventional superconductors. So we can use this Bose-Fermi mixture to do a quantum simulation of high temperature superconductors in this system, where we can load them in a 2D optical lattice. So we can have a various arbitrary geometry of these atoms in an optical lattice, so in any arbitrary potential, and it has promising possibilities to do quantum simulation of condensed matter systems. So we had celebrated our platinum jubilee of RRI, and we had made with light these structures for atoms, and this was our tribute to C.V. Raman. So now I come to the last part of my talk, where I talk about quantum technology with Rydberg atoms, which is my present area of research. So quantum technology has 4 different regimes: quantum computation, quantum sensing and metrology, quantum simulation, and quantum communication. So Rydberg atoms are atoms at very, very highly excited state, where so they have a very high principal quantum number, and this was discovered by Johannes Rydberg way back in 1888, and this played an important role in the birth of quantum mechanics. So this highly excited state in Rydberg atoms gives rise to many exotic properties, which is very promising for quantum technology. For example, it has a long lifetime, which goes as n cube, which is the principal quantum number to which the electron is excited, and it gives long coherence time to the Rydberg atoms, and it has large polarizability, which goes as n to the power 7. That means it's extremely sensitive to small DC or AC electric field, and hence it's very, very promising for quantum sensing. And another very interesting property of Rydberg atoms is that it's very strongly interacting with each other. So it has n to the power 4 variability of the interaction, and the van der Waals interaction goes as n to the power 11. So it has very, very strong interatomic interaction. So the consequences of this is that because of the strong interaction, we can do quantum entanglement with Rydberg atoms, we can do quantum simulation of condensed matter systems, and we can use it as single photon source for quantum communication. So how is it very useful for quantum entanglement? Suppose you have a Rydberg atom and you have another atom very far away. If you bring the other atom close by, because of the strong interaction, there's an energy level shift. So if you have one atom in the Rydberg state, you cannot excite the other, and vice versa. So you can see that we can make a correlation between these two atoms, which leads to quantum entanglement between the Rydberg atoms. So the fact that quantum entanglement is very important for quantum technology, the Nobel Prize in Physics in 2022 was awarded to Anna Aspey, John Clauser, and Anton Zeilinger for experiments with entangled photons. So how do we excite these atoms to the Rydberg state? We use a 2-photon transition, where we excite one atom, the atom first to the intermediate state using an infrared laser, and then from the intermediate state to very highly excited Rydberg state using what is a 480 nanometer laser in the blue regime. So we use what is called a electromagnetically induced transparency. So how do we do that? Suppose you have just one transition, then you will have an absorption profile. So what happens if you have this 2 transition, then there is a destructive quantum interference between the transition probabilities of these 2 atoms, which leads to complete transparency in the medium. And this is the electromagnetically induced transparency. So this is how we detect atoms in the Rydberg state. So here you can see the signals from Rydberg atoms in our lab. So this is our experimental setup. You can see this blue laser. This is the laser which we use to excite atoms to the Rydberg state. So here you can see, so as I told that higher we go in the Rydberg state, the more exotic is the property. So we had measured this transition frequencies all the way to 125. We could excite the atoms to Rydberg state as high as 125 to explore their very exotic properties, which is very promising for quantum computing and quantum sensing. So here you could see our measurements of the transition frequency. So we saw very interesting phenomena with this Rydberg atoms. Suppose we put a magnetic field on the Rydberg atoms. 5 minutes. Okay. So what we could see is we could see an enhanced sensitivity to magnetic field when by changing the configuration of this exciting beams. And here you could see that we could see an enhancement of the sensitivity to the external magnetic field with Rydberg atoms. So this was very interesting result, and we could have a very good agreement with the theoretical modeling which we had done. So then in the last part of the talk, I'll come to Rydberg excitation in ultra cold atoms and how it's so promising for quantum technology. So here's our setup for Rydberg atoms in our lab for cold Rydberg atoms. We do experiments on cold Rydberg atoms here. So here we could see that we create Rydberg atoms in the cold atomic cloud, and we have this detection system to detect atoms in the Rydberg state. So this is our experimental schematic, and our experiment was the first and the only cold Rydberg atom experiment in India, and this opens up important avenues to do quantum technology with this cold Rydberg atoms. So here we had some interesting results on the cold Rydberg atoms, where we could see a complete distortion of the signal when we went to very, very high Rydberg states because of the very strong interaction. So the next step in our experiment, which we are in quite an advanced stage, is that to trap single atom in an optical tweezer. This is quite different from what I was doing earlier on Bose-Einstein condensate, where we had bonded a large number of atoms, but here we are trapping individual atoms in an optical tweezer. So here you could see we could have an array of this optical tweezer where we can trap individual atoms. So we have created this array of optical tweezer. The idea is to use the Rydberg blockade to create quantum entanglement between the Rydberg atoms and create fast quantum gates for quantum computing with Rydberg atoms. So we can control it very well. You can see we have even written the name of our lab, Quantum Optics with Rydberg Atoms Lab, with this array of optical tweezers. So we can arrange these atoms in any configuration as we want. So here we have the atoms already in the optical tweezer, and this is the importance of single atom trapping because we can do the physics at the quantum level. So Serge Haroche and David Wineland had won the Nobel Prize in 2012 for doing seminal experiments on individual quantum systems. So here you can see that array of our optical tweezer. We can make any kinds of array of optical tweezer. And till now, we have successfully trapped up to 9 atoms in the optical tweezer. The challenge is not to trap single atom, but to detect the single atom. So we are overcoming this challenge of detecting very small number of atoms. So till now, we have detected till 9 atoms here in this, and soon, hopefully, we'll be able to detect single atom for creating quantum gates with these Rydberg atoms. So the idea is to have this array of individual Rydberg atoms, create quantum entanglement between them, and create a quantum network of this array of Rydberg atomic qubits. So generally, we know that in a microscopic system, it follows single particle physics, and in a macroscopic system, it follows many body physics. But what happens in the intermediate regime, which is the mesoscopic regime? So Rydberg atoms, because of its giant size, is just perfect to explore this very interesting regime, which is the transformation from the microscopic to the macroscopic regime. So that idea is to have an atom by atom assembly to go from the microscopic to the mesoscopic regime and explore this very interesting regime of mesoscopic physics with Rydberg atoms. We can do quantum magnetism with Rydberg atoms by arranging them in a triangular or a square array. And also we can do quantum sensing with Rydberg atoms, because depending on which Rydberg atoms we choose, we can detect radio frequency, microwave to terahertz radiation with just the same versatile platform of quantum sensor with Rydberg atoms. So this is our schematic of the optical setup, and we already have quantum sensing with Rydberg atoms. Here you could see we could sense with very high sensitivity microwave signal with Rydberg atoms. 2 more slides. As you could see, with this versatile platform of Rydberg atoms, we could do quantum computation, quantum simulation, quantum sensing and metrology. We can also explore observational astronomy with futuristic dipole antenna. We can emulate complex quantum systems, and we can also do ultra-fast quantum dynamics. So this is a very important slide because it shows the group of people who had contributed to the work I had presented. So my PhD students and intern students who had contributed to this work. And I had very strong collaboration with theorist Shobhan Datta, who's in-house theorist, and Rajesh Nath from IISER Pune. So I come to the end of my talk. I had given an introduction to Bose-Einstein condensate and told about our quantum mixture experiment here in RRI, as well as quantum technology with cold Rydberg atoms in our experiment at Raman Research Institute. Thanks for your kind attention.
Questions?
Hi. So in the Bose-Einstein condensate equation, in the Gross-Petosky equation, we're ignoring the fluctuation term for dilute gases.
Yeah, because the atoms are so cold that we can safely ignore the thermal fluctuations.
What about a dense gas? You can't ignore over there. And what will the profile look like then?
Well, I mean, experimentally the profile looks as I had shown you, like the parabolic profile. So see, because of these fluctuations, you don't have a perfect, following of this BC phase transition graph. So if you had no fluctuations, it would, okay, I'll show you. Yeah. Yes. So you could see here, it's not following that perfect, graph, the theoretical graph for the Bose-Einstein condensate because of the residual thermal fluctuations. You cannot go to absolute zero temperature. So whatever the imperfections is what you see in this deviation from the perfect theoretical curve here.
Just one more question. In this imperfections, since the gas is not at absolute zero temperature, can I expect this profile to show, like this profile might arise due to some internal scattering?
No, so this profile actually is because of the strong mean field interaction. So that gives you the parabolic profile. So you see the harmonic trap bottom is parabola, right? So because of the strong mean field interaction, and this has a repulsive mean field interaction, I didn't go into much details before. It has a repulsive mean field interaction, and that's why it fills up the bottom of this harmonic trap. So that's why in a harmonic trap, the profile of a BC is a parabola. And we see it every time in all the BC experiments.
Okay, thank you.
Optical dipole trap is also known as optical tweezers. How it works?
Sorry, once more.
Optical dipole trap is also known as optical tweezers. How it works on trapping mechanism?
Okay. So what happens is that, as I had told you, in optical dipole trap, we have the laser beam very, very far away from resonance. There's hardly any photon absorption emission. So what happens is that in the laser beam, you have an oscillating electric field. Okay, so now this oscillating electric field induces an oscillating dipole moment of the atom. Now this oscillating atomic dipole moment interacts with the oscillating electric field to give what is called a D, which is the dipole moment dot E force. So this is the force which is actually, and this is actually minus D dot E if you have a red detuned trap. So atoms are attracted to the highest intensity point. Okay. Now if you focus a Gaussian laser beam to form the optical dipole trap, at the focus you have the highest intensity. So the atoms are attracted to this highest intensity point, and that's how they are trapped in this optical dipole trap or optical tweezer.
I suggest that we can ask more questions during lunchtime, okay? So because we are running a bit late. I hope you'll join for lunch.
Sure.
I request Professor Geeta to hand over a small memento to.
Thank you so much.
So good morning. So in quick succession, we have Dr. Saurabh Singh, who is also from RRI, but talking from a very different scale. Cosmology and radio astronomy is his areas of interest. He got his PhD from IISc and did his postdoc from McGill and has been here, I think, since his return. So please. Thanks.
So a very good morning to everyone. Of course, as our introduction, we are going to explore a very completely different regime from what you witnessed in the last 45 minutes. So this is essentially going to be from quantum to cosmos. And I thought I'll structure this in a more pedagogical way. So I'll mostly be talking about what we understand of our universe, right from its beginnings to what we see today. And in between, I'll keep telling you a little bit of a stories on how things were actually concluded and what is it we are doing here in order to address some of the still unresolved questions of cosmology. So as you know, cosmology is nothing but study of universe as a whole. So when we think about astronomy, we usually think about individual objects. You're studying a particular galaxy, you're studying a particular planet. But in cosmology, we are trying to understand universe as an entity, how it forms, how it evolves, what are the different stages of evolution, and how can we study them, right? So my talk would mostly encompass all these different questions. So of course, this is something that fascinates all of us. This is one of the pictures that we took in one of our field deployments in Ladakh, one of the best night sky I have ever seen, thanks to Dorje Yangchuk, who taught me how to do astrophotography. But then what you see around when you go to a clearer night sky, for which Bangalore is not a suitable option, you'll see a lot of stars. If you're lucky and the timing is right, you will see our part of the galaxy, Milky Way galaxy. You will see some meteors, you'll see some other stuff. So the natural question is, of course, how any of this was formed, right? And can we understand it from the first principles? And this is what makes it a very ancient field of study, right? This is not the 20th century that we are starting to think about it. Millennia ago, there are questions, beautiful passages like this, whence all creation had its origin, the creator, whether he fashioned it or whether he did not, he knows, or maybe even he does not know, right? So people have always wondered about where it all came from, right? But for a very long time, this was mostly an exercise in philosophy. But this is what changed in the 20th century and 21st century, where it's become more data-driven, more evidence-based. And that is what is going to be the focus of my talk. So you saw the picture of the galaxy in Ladakh, but we can do much better now. We can launch optical telescopes outside into Earth's orbits and even beyond to try to probe much deeper and therefore uncover fainter objects. Right? So what you see here is one of the deep field images from relatively recently launched James Webb telescope. Many of you may have heard the name. And what you see is just impossible to describe in a single hour. But of course, each point that you see is a galaxy, right? It's a conglomeration of stars, dust, gas. But then you see very unusual shapes here, right? They are not the very picturesque spiral galaxy or elliptical galaxy. You see warping of things. Any guesses from the audience what it could be due to? Sorry? Collisions of galaxy can change its morphology, but you see some very elongated warped structures. This is more than just collision. Mm-hmm. Sure. Right, so that is what we call as gravitational lensing. Thank you. So essentially, and this is something I'll come to it in much detail, that not all the matter in the universe is luminous, right? So there is matter out there that does impact the way light travels, right? And it can act like a lens and bend light. So what you are really seeing is an effect of light bending through those massive things, right? More about it later. But the idea is that now we have a much better understanding of what is near to us, what kind of galaxies exist, etc. And then that begs the question, which is not very intuitive, about the length scales we are dealing in this, right? So this is perhaps a very small fraction of a degree on the sky, right? And what the structures that you see are humongous, right? So before we go any further, I'll take a minute and just orient you to the kind of length scales we are talking here. So it's a very nice visualization. I strongly recommend all of you just explore it once yourself. It's called Scale of the Universe. And we start with roughly the size of our own human length scales, which is roughly, say, a meter. So Sanjukta in the previous talk went left of this. And this talk will cover the rest. Okay? So when you start from here, the smallest celestial object that you will start to see would be something like asteroids or moons of different planets. And one of the smallest is Phobos and Deimos. What are the satellites of? Great. They are essentially captured asteroids, yes. But then you can go beyond a kilometer, right? And you will start now seeing bigger moons. And what is the biggest moon in the solar system? Yeah. Ganymede. Ganymede revolves around which planet? Jupiter, right? Right. So Ganymede is actually bigger than Pluto. And that you will start to see around here, right? So we are already talking 10 raised to 6 meters, right? But this is nowhere close to what we deal in cosmology. We really can't even deal in terms of kilometers. We have to go much beyond. So you will encounter Earth, you will encounter planets, which are around 10 raised to 8, 10 raised to 9 meters. To us, they are all point objects, okay? So now we are in the territory of around 10 raised to 9 to 10 raised to 10 meters, which is essentially our known stars. So Sun is a very average star, right here. You can see it for the scale. And then we have some of the known stars like Sirius A, which is very bright in the sky. You would also probably see Proxima Centauri, which is the closest star to the solar system. But then I'll just fast forward this and try to zoom in into much bigger objects. And here, kilometers and meters stop making sense. We are talking about 10 raised to 15 meters, and just a human mind is not good enough to comprehend these. So we'll start talking in terms of what we call as light seconds, light minutes, light years, which is essentially the time that light takes to travel roughly 1 year, which is light year. And here we'll start exploring what we call as nebula. Has anyone heard about this before? So what are they? Anybody? Probably from people who have not answered anything yet. What's a nebula? You've answered, so I'll get back to you. Anybody else? You all know. I saw many shaking heads. Yeah. They're known as birthplaces of something. What are they? Sorry? Just prompt something. Sorry. You have, yeah? Okay. Yeah. So essentially they are very popularly known for being birthplaces of stars. And then you zoom out further. You will start now looking not just at nebula, but galaxy as a whole, right? So we live in Milky Way, which is a spiral galaxy, roughly around 10 raised to 20 meters, kiloparsecs, kilo light years, tens of kilo light years, in fact. And then galaxy is not the end. They are also clubbed into what we call as clusters of galaxy, which is the largest gravitationally bound object in our universe. Right? And then all of it, fast forwarded, makes what we call as observable universe. There is a limit to what you can see, and you cannot see beyond that. And that is essentially this observable universe. So essentially, this is all come from decades of investigation from starting from around 1500s to now, where we were starting initially to look at just the solar system, the moons, the planets, and then grew from there to start looking at the galaxy. Not very far off, we were debating whether there are other galaxies in the universe. This is talking about 1900s, right? 18 and 1900s. And then we realized that no, there are other galaxies, and there are even galaxy clusters. So this whole higher length scale problem is very recent, where we have started to realize how multi-scale is our universe. All right, so this slide is going to be the most important slides. If you are phased out, I request you to phase back in. And this is essentially cosmology in a single slide. So I'll spend some bit of time here. This is a schematic of how the universe started and where we are here. So we are currently at the right part of this plot. And what we saw earlier, we see stars, we see galaxies, we see galaxy clusters. And the age of the universe, as we estimate today, is roughly 14 billion years. Okay? And we'll get back to how we even understand this. But then we know that the universe couldn't possibly have always been like this. So we'll start from the leftmost, which is going back in time, right? Which is another beauty of cosmology, where potentially you can see the history, right? So the most widely accepted model of our universe is what we call as the hot Big Bang model, which is it started from a place of very high density, high temperature. And for a very small fraction of a second, from the Big Bang, universe expanded exponentially, right? That period, what we call as inflation, cosmological inflation, which is again very poorly understood, but we'll fast forward, and soon enough we start having particles, right? And these particles are very strongly interacting with each other in a hot soup of plasma. So we are talking about temperatures of around 1,000 billion degrees Celsius. But then we also now understand that the universe is not static, it is expanding. And when it expands, it's adiabatically cooling as well. So these first particles start to form nuclei. And then at some point, and by that some point, I mean roughly 400,000 years after the Big Bang, we have the very first atoms form. It's not that atoms were not forming before. Protons and electrons could still be captured and form atoms. But the photons were so energetic that they would instantly knock it off, right? So the stable atom formation wasn't there. But as the universe expands, the photons are now cooling down, and they are not sufficiently energetic to ionize it, right? So this is the first epoch which is instantly observable. And I'll get back to more details about this, when the very first atoms had formed in the universe. And this is predominantly hydrogen, with helium, with lithium. I think Dipankar has covered some bit of it in the nucleosynthesis. So that is all about the formation of the very first atom, which is still within the infancy of the universe. At some point, and again after a really long time, in fact, a few 100 million years, you have the first stars forming, right? So it's not that once the hydrogen forms, you start having stars and galaxies. It still takes a lot of time. And you have these structures, stars and galaxies forming, which are kind of also following what we call as dark matter. I'll get back to it later. And then another important thing that happened is this elusive component of a universe called dark energy took over. So till now, the universe was just expanding. At around 10 billion years, so in cosmological timescales not very far from today, it also started to accelerate thanks to dark energy. And that has resulted in the universe that we saw in the very first picture here, right? So what we see around us is in fact a history of 14 billion years with a lot of physical processes happening in between to get what we now see around us, right? So these are some different periods in the evolution of the universe, and my goal is to just give you a flavor of what we understand about some of these. It's impossible, of course, to cover everything here in the limited time, but at least with the telescopes that we have built over the last century, we do have a very good understanding of our local universe, right? So we understand the Milky Way, we understand Andromeda, we understand some other structures. So I would be very bold and put a tick here. Many astronomers would vehemently disagree with me on this. There are a lot of things to be understood, but then I want to go back and also see what we understand of the other epochs. And just to again reformulate this problem, because again, our brain is not very good at comprehending big numbers, if I were to collapse all of this into a calendar, right? So January to December, this is what we have. The cosmic calendar, took it from Wikipedia, where the 1st of January is the Big Bang, and we are at the 31st December, last fraction of the midnight, right? So the entire history of scientific revolution is the final second in this picture, while what other things I talked about, which is the Big Bang, the appearance of the first stars, the dark energy taking over the expansion, all happened within the first few months of this calendar, right? So I'll conveniently skip everything here, which also might be covered in other talks, and focus only on the first few months of this calendar. Okay. So if I were to rephrase what are the basic questions in the first few months of this plot, I'll try to compile it in a way, but of course this is not exhaustive. This is my own perspective of what are the big questions in cosmology today, right? So one is just the evolutionary aspect of it, which is, as I said, in the first few fractions of the second of the Big Bang, we had inflation. The universe expanded exponentially. We kind of don't understand how that can happen, and that's a very active field of research. There are lots of models one can propose. And then if you have a very uniform universe, potentially you can never form a star or a galaxy. There has to be some kind of inhomogeneity in the densities, right? If you have a perfectly uniformly dense thing, nothing can gravitate. It's a very event-less system. So there were, now we understand well, density perturbations. So we know universe is uniform but not completely. It has small perturbations. There are some regions which are slightly high density, some regions which are very low density. So the higher density ones now can gravitate more matter, which can eventually result in formation of stars and galaxies. But then what caused these density perturbations? If those weren't there, we wouldn't exist today. And of course, density perturbation is one thing, but taking that perturbation all the way to forming the first stars and galaxies is a different ball game altogether. So the next natural question is how and when did these first stars and galaxies formed in the universe? Something that my own research deals with. But then it also comes to the question of composition. What is our universe made up of? What we see is what we call as visible matter. We see stars, we see galaxies. But then now we understand that visible matter is a merely 5% of what we understand of the universe matter density, or the density of the universe. Most of it is what we call as dark sector. It's dark universe. 26% is dark matter. roughly 70% is dark energy. These are just words so far. I'll give a little bit of an idea about what these things are. And then, why at all do we have more matter, right? But when the Big Bang happened, there were particles, there were antiparticles. There is no possible reason why matter should dominate. And that's yet another problem, that why do we have this asymmetry between matter and antimatter? And then there is a one question which is more fundamental physics question of whether the laws governing the small scales and the large scales in the universe same, right? And that leads into things like quantum gravity. So there is a lot of things to explore here. Again, not possible to cover all of this into this talk, but I'll cover some of these questions that pertains to our cosmic history here. Okay? Any questions so far from anybody? Yes. Yeah. Okay. So we'll take that and then come to you. Yeah.
Good morning, sir. Sir, you mentioned earlier in the beginning that we consider universe as an entity, right? Sir, so does it has any definite shape? And if it has, so why we doesn't has its area?
Right. No, great question. A little bit of it I'll cover later, but the idea is what we understand of the universe geometry is it's surprisingly flat. Again, there is no reason for it to be flat. It could be curved. But then we can only observe a specific radius around us because of the finite travel time of the light. So that is what we capture in the term observable universe. So we understand that it's flat and that it has a very specific radius of, say, tens of billions light years. And that's about it that we understand of the geometry of the universe, right? So when I talk about it as an entity, I talk about it in terms of it having a structure and a history of evolution, not necessarily that we understand its full details altogether, because we have a limited area of observation. Okay. Yeah, you had a question? They do. Right. So it doesn't necessarily imply causality. In fact, when we start doing this cosmology, we start with physical laws first, and then see, based on what measurements that we have, how can we put them into a consistent framework. So I would say in terms of the sequence, we start cosmology with physical laws, and these can be from, at some scales, Newtonian gravity, some general relativity. And then understanding of, say, dark matter and visible matter and dark energy, we can put them in a coherent framework. So the composition, I would say, is more right now data-driven, while physical laws are more fundamental. Yeah. Yes, go ahead.
So given that the universe is expanding, there will be more density packed galaxies and matter.
Right. Yeah.
So from the two-dimensional photographs we have, can we convert it into a structure where we can see which direction the photo?
Yeah, excellent question, and I'll get back to this. Before this, another question? Yeah. Nothing much. Nothing much. You will have flip charges and etc. But the idea is any asymmetry, whether it is more antimatter or more matter, it's also a question of semantics. The question is, why does that asymmetry arise at first place? When you have particle production, you have particle and antiparticle, right? Why so? Yeah. Right, but that I think the question here is what creates those imbalances. So based on our understanding of particle production, for example, at a scale that we are talking about here, it's not immediately clear, though I agree there are people who are trying to understand these asymmetries in more details. Coming back to this very important question that you raised about are there preferential directions or regions which are highly clustered, the answer is unfortunately no so far. And the reason is...
Can you just repeat the question for some people? No?
Oh, sure, sure. Yeah, so the question is that if understanding of this Big Bang model, are there regions of the universe which are more clustered, which will have more galaxies, more stars, and therefore these images we can put in that context, right? And the answer is that the universe as we understand today is extremely homogeneous and isotropic. So when we talk about Big Bang, we do not talk about one point in the universe that had very high density and temperature. So if we ask this question, where did Big Bang happen? The right answer is it happened everywhere, because the entire space-time was confined to a single point. And so when it expanded, it is very uniform. And from all our observations, I would say most of our observations, we realize that there is no inhomogeneity. At large scales, we are talking about the scales of galaxy clusters, our universe is extremely homogeneous and isotropic. So there is no preferential direction in which things are inhomogeneous. Lately, there have been studies that are contradicting this based on the studies of galaxy distribution and their velocities. But largely, the picture still holds that our universe is homogeneous and isotropic, what we call as cosmological principle. But thanks for raising this question. This is a very important point going forward. All right. So we will now get started on addressing some of these questions. And just like the previous talk, I'll sprinkle over some of the Nobel Prizes in cosmology, and those will be the starting points of these different topics. So not necessarily in the order in which they were awarded, but 2019 Nobel Prize was in some way more fundamental. The person here is James Peebles, who kind of laid down the modern foundations of cosmology, right? So this is fundamental questions about the universe have always fascinated human beings, and James Peebles, his theoretical framework that he did, is the basis of our contemporary ideas about the universe. Right? And in particular, the cosmic background radiation is a remaining trace, and using his theoretical tools, Peebles was able to interpret these from their origins and also estimate the constitution of the universe itself. Right? So there are lots of words here. Cosmic background radiation, dark matter, dark energy, which are the constituents of this universe. But I'll get to that. But the foundational work was very much this particular recognition by James Peebles. Okay? So we'll start off with the first thing, cosmic background radiation, and then move on to dark matter and dark energy, which is very much the total talk. So, and in some way, I would say cosmic microwave background radiation was one of the first discoveries in cosmology, and a very serendipitous one. So just to revise, we are talking about formation of the first atoms. So in that slide that you see, this is around 400,000 years after the Big Bang. So within the first billion years or so, million years or so. And as I said, this was a very accidental discovery. So the idea is when the first atoms formed, soon after we also had this almost simultaneous where photons and matter kind of stopped interacting with each other, what we call as decoupling. So now the photons are free streaming, and these free streaming photons are what we call as cosmic microwave background radiation. The prediction of this was also made in the early 1900s, but then there were no experimental detections of this. And the detection came rather surprising. We had this couple of engineers, Penzias and Wilson. They were essentially making a communication system, so they were designing these horn antennas. And then what they saw, essentially what they measure is power, how much power is coming from a very specific direction. And what they saw was around 3 Kelvin excess. So Kelvin, well, astronomy is a very weird field in terms of units. We measure power in kelvins, at least in radio astronomy, so please pardon that. But in some way, you can convert it into more reasonable units like specific intensity. So what they measure, the power was a little higher than what was expected from horn antenna itself, the sky, some of the instrumental components that they had used. But then they were not able to resolve where is this extra power coming from, right? So I'll again put this question back to especially students, where you are measuring something like this, and you see something that is excess, unexplained. How do you go about confirming that this is coming from cosmic microwave background? That perhaps can never be the first guess. So what all can you think of that will help you convince yourself that this is actually cosmological and not something more mundane? And they were also not really cosmologists, right? They were designing a communication system. So what tests can you think of? Yeah, observing at different times of the day is a very valid test to do, which they did. There weren't many options back then. But yeah, that is another thing. You can test it from different locations on Earth, if that's what you are coming to at. Which also ties up, you can look at different directions and see whether there is a variation. So all of those things were done, and still look at the title of the paper, a measurement of excess antenna temperature. They made no big claims where it's coming from. In the passing reference in the end of the paper is like, there are people who say this might be CMB. But it was a very objectively reported paper, but it was very big. Now we understand that this is cosmic microwave background radiation, the relic of the Big Bang, which is kind of signaling when the first atoms were formed. And in some way, this is the farthest that you can really see. That's another Nobel. So Penzias and Wilson, because of their discovery of the CMB in 1978, were given a Nobel Prize. And it does say that the cosmic microwave initially appeared to become weaker as wavelength became shorter, but then they discovered that at around this wavelength, it was stronger than expected. And initially, of course, they thought that this is some local disturbance. In fact, they went up to the antenna, they cleared some of the pigeon droppings, which they thought might also result in such measurements, which is again an experimentalist mind at its best. But then after you have eliminated everything, this was left behind, and therefore this is cosmic microwave background. And since then, there have been a lot of such measurements. So you have now not just the measurement of the power, but how it's distributed across the sky, which is essentially measurements like COBE, WMAP, and Planck, which was launched in succession. And what you are seeing here is not just the mean power of the cosmic microwave, which is 3 Kelvin, roughly, but the variation. So this ties up with the fact that in some way, these density perturbations that I talked about result in the brightness variations. And this was also very remarkable because it also laid to rest a lot of other cosmological models, not just the Big Bang. So the left is essentially the black body, which is the power of the CMB monopole as a function of wavelength. This is the best black body known, most accurate black body known to humankind. And on the right is a capture of the perturbations on the CMB. So this is not 3 Kelvin, but the fluctuation around the 3 Kelvin, what we call as the power spectrum. So this was enabled by experiment COBE as one of the first space-based experiments, which led to yet another Nobel Prize. So this is in 2006, where Mather worked on the spectrum of the CMB, so essentially demonstrating its black body at a fixed temperature, while George Smoot looked at the anisotropies, which is this plot, and again it validated a lot of what we understand of the early universe. So putting it all together, just from the study of this radiation, now we understand the composition of the universe, dark matter, dark energy, the age of the universe, saying that Big Bang model is one of the best descriptions so far, and so on and so forth. We can get into the details. But now I'll focus on these two components, the dark matter and dark energy, which is the most dominant part of this energy density budget, right? Radiation, in fact, is a very small fraction of this, but it does inform us about these things. So first slide was here. Just to recap, we are here. We'll be covering these ones. So I'll start with dark energy. And it's actually it's one of those discoveries which was completely unexpected. Because when you look at cosmology, what you will realize is it's surprisingly simple. The math of cosmology, at least what we call as the background kinematics, is very simple. So in fact, it was much of a surprise when we understood that it is actually driven by dark energy. Okay, so this goes back to 1900s again. People were expecting what we call as a static universe or a steady universe. But then Edwin Hubble started looking at distant stars in other galaxies, and for which there was a possibility to understand the distance. So the x-axis is the distance, and the y-axis is the velocity of these stars. And what he found is the farther the stars are, the faster they are moving, right? So in some way, this is similar to having a lamp here. You kind of know what the intrinsic brightness of the lamp is. You put it on Andromeda, and you again measure what the brightness is. Based on the reduction in the brightness, you can tell how far it is, right? That's basic philosophy here on this plot. Though I'm sure it is very bold move to fit a straight line here, but he did, and then it turned out that that straight line was actually a good gamble, because it is indeed a flat line, a straight line, which is farther the object, the faster it moves. In some way, what it tells us is universe is expanding. Now, since 1930, we have other ways to measure this. So supernovae, in some way, these are the objects where we have something called white dwarf, which are end stages of some stars, and when they accrete enough mass, they can explode, what we call a supernovae 1A. And we know the intrinsic brightness of these objects. So if we measure it at a very far distance, we can estimate what's the distance between that object and us, just based on the brightness. So this has been done very meticulously in past few decades. So what you see is the magnitude of these objects. So each point in some way is one such observation, and the x-axis is a metric of distance from us. And then this is when it struck us, because Hubble with his very limited observations was confined to this region. But when we extended it to farther objects, what we saw, if you don't have this dark energy, the object should be much closer to us. So at a given redshift or distance, you should have a brighter object, which is basically, again, astronomy being weird units, lower numbers are brighter, higher numbers are dimmer. But then what we found is these objects were consistently dimmer. They were farther than they should be. So there is something that is pushing it away. And that pushing it away is nothing but dark energy. So now what we understand of it is it comprises 70% of our universe, and it is repulsive in nature. So it works against gravity, and it pushes the objects further away. And honestly, that's all that we know of it. It's rather embarrassing that we don't understand 70% of the universe. And again, this was a remarkable discovery led by multiple scientists. So this was 2011, where we saw that there were two independent groups that looked at these supernovae and realized that universe is not just expanding, it is accelerating. And that acceleration is driven by dark energy. And when you come to the theoretical formulation of this, it gets even weird. So it has a very interesting history, where Einstein was looking at the very famous equation of relation between the space-time tensor and the stress-energy tensor, and which are kind of related. We can't get into the details of it, but then it was giving him a universe which was not static. And back then, static model of the universe was the most popular one. So he ended up putting this constant, lambda. And later, if you trust Gamow, Einstein remarked that this was perhaps the biggest blunder he has ever committed, because there was no reason to put it. He just wanted a steady universe. But so it turns out that this is required to explain dark energy. So there is a constant in this equation. But then if you want to theoretically predict what that number should be, it is 10 raised to 120 times higher than what we see with our different measurements. And this is perhaps the highest discrepancy across sciences. I don't think we'll have a number bigger than this in any talk. So it is, again, a very fundamental problem that we kind of know about dark energy from observations, but we do not have a very consistent theory that can explain how it arises. And with that, I'll move on to the very next part of my talk, which is to do with intervening. So I have 10 minutes, and I'll try to cover this part now. So we now understand the formation of the first atoms, thanks to cosmic microwave background radiation. We kind of understand, well, not fully, but we understand what is dark energy doing. It is in some way accelerating objects, pushing each other away, and the fact that it is repulsive and roughly 70% of the universe. And there are experiments that are trying to, of course, understand these things better. But now I'll come to something which is more intuitive, which is matter, right? So radiation and dark energy is done. Matter is, we know, gravitational, right? So we understand these things better, which is required to understand how the first stars formed, right? So matter comes in two parts here: visible matter, stars, galaxies, these things, and then dark matter. So dark matter is not same as dark energy, of course. Dark matter is still matter. It responds to gravity. In fact, most of the stars and galaxies that we see around us were formed because of dark matter. in some way they create the skeletal structure in which the baryons follow. But so far we don't have a understanding of how it interacts otherwise, not just gravity. And this came again in the last century, where we were looking at velocities of objects in our galaxy little far. So what we understand just from the Newtonian gravitational principle is, if you have a mass centralized, say, into a certain radius, we can predict what the velocities of the object would be far away, right? So gmm over r squared will be equated with centripetal force, which is mv square over r. And you will expect a curve like this. So as you move farther from the object, your velocity should fall. What was observed was in fact opposite. It actually goes up and kind of plateaus, which means that there is mass not just central, but much extended beyond, which we are unable to see, but it is responding gravitationally. And this is what was termed as dark matter. Vera Rubin played a very significant role, and it's still a matter of debate that she should be awarded Nobel Prize. She should have been awarded Nobel Prize for this discovery. But anyway, the point is that now we understand that there is matter much beyond the luminous matter, what we call as dark matter. And if you are wondering what is this matter, you are not the only one. And honestly, there is no answer to this question. So there are all possible theories on what dark matter could be, from ultralight dark matter to axions to even something which is of the order of black holes, what we call as primordial black holes, of some solar masses. So the mass range is very high. And there are experiments which are trying to understand what is the most potential candidate for dark matter, right? And then there are several. The fundamental ideas of these experiments are that assuming dark matter also interacts something beyond gravity, suppose electromagnetically or something, then once in a while it will produce a signature in terms of a photon and electron which can be picked up by our detectors. So of course you need a very large volume for these experiments because the probability of interactions are very low. And there are these experiments, I don't have time to get into the details. They have not detected a very reliable candidate, but they have put very strong limits of what it cannot be. So the exclusion of different masses and cross sections is what we have right now. 5 minutes, great. 5% of the matter. Okay. So matter, dark matter is definitely the most predominant one. But what we understand of astronomy actually comes from this, right? The visible matter. And in some way, I would want to focus on the formation of these visible matter, which is the first stars in galaxies, which is very much part of my research. So if I again go back to that slices, I'm talking about a few 100 million years after the Big Bang. And that epoch is called cosmic dawn. So this is the first time that a source of radiation was formed in the universe, which kind of laid the background to everything that we see, including us, right? We couldn't have existed if not for this. So we understand for now, they were formed roughly within the first billion years of the Big Bang. So just to again recontextualize it, age of the universe is 14 billion years. And initially they were formed in very local pockets, which then expanded, merged with each other to form the large-scale structure that we see around us. But then there are lots of questions even in this visible matter that we do not know, right? For example, were they very different from what we see things around us, right? So, for example, when I see sun, were these first stars more massive than the sun on an average? And a good way to create a riot in a conference is ask this question, because there are different groups who have very different theories about how the first stars were formed. Correspondingly, their masses might be heavier or lesser. What about the luminosity? Were they brighter? And a very similar question is what impact they had given on their mass and luminosity information about their neighboring, right? So it's not just one star forming in isolation, but this is a pack of radiation which is changing the large-scale structure of the universe. And one of the most important things that it did is it emitted a lot of UV photons. And these photons are very good at ionizing hydrogen gas, right? So as you know, the ionization energy is how much for a hydrogen atom? How much energy do you need to ionize a hydrogen atom? Yeah, some electron volts. Any number? 13 point? Good. Yeah, speak up. So there are these photons generated by the first stars and galaxies, which can ionize the entire universe. In fact, they did that, and we currently live in a universe which is completely ionized. And of course, did they live long, right? So compared to a solar lifetime, were these first stars some way short-lived or long-lived? A lot of questions exist for which we really, even for the visible universe, don't have answers for. So my group here wants to address this. And the way to do that is, of course, the most fundamental way is you go out, build the most sensitive optical telescope and look at the first galaxy, right? Impossible. Our current limits of sensitivities would not allow us to do that, given these objects are very far and very faint. And in fact, we understand that these objects were also very small, what we call as dwarf galaxies. So they are anyway very dim. So that is not going to work out. We have to think of something else. And one of the things we can think of is, instead of looking at one galaxy or two galaxies, we look at the hydrogen gas itself. We understand that the hydrogen is most abundant element in the universe. So can we then look at the integrated emission from hydrogen atoms at these kinds of time scales, right? The first few 100 million years after the Big Bang. So in the 1950s, people looked at what different radiative phenomena we can look at from the hydrogen atom. And one of the ways was the spin flip transition. So within the ground state of hydrogen atom, you can have the spins of the electron and proton parallel or anti-parallel. And any phenomena that can change this can release in emission of a photon. So this is popularly called as 21 centimeter photon, because the wavelength is 21 centimeter. And this was reported in the 50s, where it was detected from our own galaxy. So we now have this observation coming from our own galaxies. As a matter of fact, that is one of the fundamental ways in which we could study the velocity of objects beyond certain radius, by looking at these photons from our own galaxy. And now we have also observed this photon from other galaxies, right? So this is a nearby galaxy. What you see here is in the optical wavelengths, and what you see here is if you map the same object in 21 centimeter wavelengths, right? So what it tells you is the luminous content of this galaxy is restricted while the gas is distributed. Can I have 5 minutes? Thank you. So can we then look at a much larger structure than just the luminous matter using this? So in our local universe, we have very successfully demonstrated this. Gauri-Bidnor Observatory, which is just 80 kilometers from here, from RRI, we have built a horn antenna which can, in real time, show you what the 21 centimeter wavelength is, the brightness is in Milky Way. It's a very popular thing and very educative thing to do. But then, can we now detect this from very high distances objects, right? So we're talking about being able to detect this from the very first stars and galaxies. So just to give you a very brief slice here, the highest distance that we have gone to detect this is somewhere here, right? So we have seen it in our galaxy, we have seen in other galaxies, but we have never been able to push this frontier for 21 centimeter photon because of the sensitivity, right? One of the highest redshift detection actually comes from GMRT near Pune. And what we want to do is detect this from here, from the very first stars and galaxies, which in turn can tell us a lot about what's happening in the intervening part between the first atoms and the current universe, right? And this is all about our research. Of course, there is a lot of challenge, and that's why we are doing this, because these 21 centimeter photons coming from very early parts of the universe are not the only things that you receive when you build a telescope, right? And this is, of course, in radio wavelength, so you'll have to build a radio telescope. You have other galaxies. You have your own Milky Way galaxy, unfortunately, which is very bright. Then you have ionosphere. You have human-generated radio interference. And then you have your own experimental systematics. And everything here is orders of magnitude brighter than the signal that you're looking for. They can be somewhere between 100,000 to 1,000,000 times stronger than the signal of interest here. And that's why this is a very active field of research. A lot of people are trying this. The signal is looking something like this. This is just one of the models. I don't have time to get into the details, but we are measuring the intensity of this line at different distances, which can be translated to different frequencies. And this exercise has been going around since the early 2000s. This signal has never been detected by anybody in this world. And Saras experiment here is the only operational experiment in India doing this, across with some other 5-6 experiments around the globe who are trying to understand this. So we have ongoing experiment called Saras at RRI that is trying to understand the first stars in galaxies. And we have a proposed space-based mission called Pratyush, which is also exactly the same science goal, but in the orbit around the moon, because it also blocks a lot of interference that is very susceptible to our ground-based experiments. So it had its own history of operations. It was started by Ravi Subramaniam here back in early 2000s. And since then, it has undergone a lot of transformation in terms of design, in terms of location. So this is Ladakh, this is northern Karnataka, and this February we deployed it in the Arctic station, where India has a station. And the idea is to then gather this data and see whether we can say something meaningful about the properties of these first stars and galaxies. So with that, I'll just try to say that we are trying to understand this, but broadly, this is a field which is driven extremely highly by data, right? So it started off as a philosophy. There were theoretical foundations, but then eventually, whether it is cosmic microwave background, observations of dark matter effects, observations of dark energy effects, which has led to a very rapid increase in our understanding. And this is where we'll be heading to. So with that, I'll conclude and take questions. Thank you.
Some questions?
Thank you, sir, for the talk. So I have a question about, you mentioned dark energy as being a repulsive kind of accelerative force in nature. So if we have, for example, observation of n number of objects, do we know, like, if the acceleration direction, what is it relative to, if there is a center from which that acceleration is emerging? Like, is it from n minus 1 object to n, or is it all to each other? What kind of interaction that is?
No, that's a great question, and it kind of ties up with the first question. That is, we do not have a preferential direction in the universe. So there are experiments like DESI, which are very meticulously mapping every single galaxy in its field of view and trying to do exactly this, build a 3-body map of how the things are moving. And what we find is that there is no preferential direction. Essentially, if you consider yourself to be the center, everything at large scales around you is moving away. So, but this story will not change if we had an observatory in Andromeda. There also, statistically, we will observe the same phenomena, which is everything is moving away.
What if we subtract both of those accelerations?
So if the universe is homogeneous and isotropic, it should be statistically negligible, right? So universe is essentially same from different points of observations. That is one of the underlying philosophy of cosmology. It is being challenged by some studies, but it has not been confirmed yet. Yeah.
Somebody else?
I think there is a question.
But isn't it true that the solar system itself is zooming at an incredible speed away? So we are moving, the components of universe are moving away, something is moving forward, and there is black matter and there is dark matter. Yeah. So how do you put everything together?
Right, no, this is great. So there are lots of frame of references because everything eventually is moving. So when we even do these kinds of measurements, when we map out the motion of the galaxy, part of this motion simply comes because we are not in a static frame, right? So Earth moves, Sun moves in a galaxy, galaxy moves. So we have very accurate corrections for these things. So idea is you kind of subtract for the what we call as the dipolar motion simply because we are moving, and then see whether something is remaining beyond that. So in some way we do have accurate understandings of our own local motions, and then the question is, are there anisotropies on that top of that motion? So when you look at CMB, for example, cosmic microwave background, most of the studies conclude that once you subtract off our local motions, it is isotropic. But then lately, especially with the galaxy surveys here, we have seen that there might be anisotropies, but they are not confirmed yet. But then it also begs a question, if it's real, are we again talking about something where the early universe versus late universe things have kind of changed?
Somebody else? Okay, so we can, you want to have one more question?
So So, is there a scale that has been observed at which the effects of dark matter continuously or like abnormally stop, or is it a continuous gradient at which you kind of observe it?
So again, talking about length scales, this is not observable at a length scale of planets and solar system. Gravity, of course, can explain everything. So dark matter effects are seen in a galactic scale away from the center. So we're talking about a few kiloparsecs and beyond. When you go to even higher, like galaxy cluster scale, it is very obvious that dark matter plays a very important role. So we have not accessed any scale where, especially in the larger side, where we have not seen it. It is there. And now what we understand is the entire density profiles of these structures are driven by dark matter. So they have to be there. And baryons comprising such a small fraction just fall into those potential wells.
Okay, so I think we can have more questions during lunchtime. Let's thank the speaker, and I request Professor Geeta to hand over this memento. So thank you all the speakers and the two speakers, and we have a coffee break now until 12:15. Yeah. part of the other team, part of the team. Geeta I met, and she will vouchsafe. When she joined here 23 years back, 2003. So the time the speaker today was there, and then she worked with him. Kind of that time. Okay, anyway, so I again invite Professor Geeta to introduce the speaker and chair the session.
It gives me great pleasure to introduce Professor Nanjundaya, whom it looks like I've known him for a long time in some strange circumstances. He is currently at the Center of Human Genetics and is working developmental biology, evolutionary biology, theoretical biology. I think in that order, I'm not quite sure, he'll clarify. He got his bachelor's from Bombay University and went on to do his PhD in Chicago. And then he joined Indian Institute of Sciences, went for a brief while to TIFR, and then came back here. I just wanted to inject a personal note here because I think it's largely because of him that I was finally impelled to go and follow my interest in evolutionary biology. He was very encouraging in many ways. So I appreciate that. Thank you and welcome. Please talk.
You can stay here. Thank you very much, Professor Geeta. Thanks to Professor Suri as well for having invited me here. I will begin with 3 quotes, which I hope will set the scene for what's going to follow. 3 quotes by 3 distinguished people, and I better get this right. One goes, "Innovation Bharat ke DNA mein hai," and this is by our Prime Minister, Mr. Modi. "Innovation Bharat ke DNA mein hai." The second quote goes, "This country has people in it who are bad because there's something very wrong with their genes." This is President Trump of the US. And the third quote goes, "For 40,000 years, the DNA of all people in India has been the same." This is Mr. Mohan Bhagwat, the head of the Rashtriya Swayamsevak Sangh. Now, the interesting thing about these 3 quotes is that they illustrate the 2 features I'd like to bring out in this talk. One is DNA, or genes. In some sense, they mean the same thing. These are words which have entered the common vocabulary to mean lots of things. In fact, they mean different things to different people, and you are free to decide, excuse me, you're free to decide what it means for you. Secondly, these 2 words are used almost always metaphorically to mean whatever, to stand for whatever there was in the speaker's mind. Sometimes they are used literally and in the correct manner. In fact, of the 3 quotes that I just read out to you, the one by Mr. Bhagwat is the one which is literal, meaning uses DNA in a literal sense, and correctly. Now the question is the content of that quote right or wrong? In other words, has the DNA of all the people in India been the same for the past 40,000 years? That's a very scientific statement, unlike the other 2 statements, meaning that it's testable. And most of the evidence tells us it's wrong, but in some sense you could think that there's an element of truth in it. As you will see in today's talk, this notion of the selfish gene has the same kind of property associated with it. In some sense, you can think of it as true, but in many other senses, it's also not true. This, of course, is not a literal, to be taken literally, the phrase selfish gene, metaphorically, but still, you can see that in some senses its interpretation is valid, in other senses it's not. So let me begin now by telling you that the talk is really centered around this book, but I won't be speaking a great deal about the contents of the book. Rather, I'll go into what lies behind those contents. The book itself, by the way, became a bestseller when it was first published 50 years ago, 1976, has remained, I understand, a bestseller since then. It's gone through many editions. These editions, as happens often with books that are controversial or raise a lot of questions, these editions have tended to soften the language used in the first edition. I will ignore these subsequent clarifications and this and that by the author, Richard Dawkins. I will stick only to the first edition, and that's partly because of laziness. I've not taken the time to go through all these other editions in preparation for this talk, and partly because this whole thing has its genesis, this talk has its genesis in a question which was put to me by a friend, which is, what did you think of this book, The Selfish Gene, when you first read it, which was when it came out. Then Bangalore had a really fine bookstore, the Premier bookstore, and I remember going there and purchasing the book at the urging of my colleague, Professor Madhav Gadgil, who many of you here, of course, would know or at least recognize. So I stick to that edition of the book. And we'll try and figure out what it means. By the way, the cover picture itself is interesting. It's by someone who is both a distinguished artist and a distinguished behavioral biologist, a person by the name of Desmond Morris, who has also written very popular books in biology, which are worth reading till today. So that's the outline. Evolution and genetics underpin biology, but it's not easy to define the word gene. Natural selection, which is central to evolution, implies placing individual reproductive interest above all else. That's where the word selfish comes from. Genetics is at the heart of evolution, and it's tempting to look at evolution from the viewpoint of genes. I'll try and tell you a little bit about what that means. Now we come to the last 2 points, which are really the talk proper. A gene-centric view of evolution can mean several things, one of them being Dawkins' selfish gene. And you'll see there that this is where a bit of hedging comes in with regard to the use of the word selfish, and you will have to decide for yourself whether it's appropriate or not. The last point is one which I think many people have thought of. It has troubled me in particular because of the area of biology I happen to work in, which is the evolution of social behavior. And I'd like to try and persuade you of what I feel, which is that the inappropriate use of words which have common and understandable meanings in ordinary human discourse, the inappropriate use of those words in a biological context has actually played havoc in biology. First point. Okay, so what's biology about? It's this. It's what you see on the screen. So it's the entire panoply of life on Earth. On Earth, that's the only kind of life we know, and in all its huge, enormous diversity. What is the extent of that diversity? Very hard to say. In terms of this common unit called species, maybe there are 100 million different kinds of species. So that's much larger, of course, enormously larger than the number of naturally occurring elements, or even if you include artificial elements, much, much larger than that. And I believe also much larger than the number of recognized molecules in organic chemistry, where you can get diversity by simply adding one more CH or one more CH2. Even there, you don't come up to this 100 million figure. The point is the following. So this is the problem of biology. This picture, how do you account for it? Sometime before Darwin and Wallace, which is before, roughly speaking, 1858, the idea was getting crystallized that diversity could be explained, and by explained I really mean in excruciating detail. I don't mean just in terms of a broad overview, but in terms of the actual properties of those things. A bit like what the periodic table tried to do. Say this thing lies here because it has these properties, or of course the other way around. Okay, so the idea was crystallizing around, let's say, the early 1800s, pre-Darwinian days. Already there by the time a person called Lamarck wrote the first modern book on evolution. The idea was crystallizing that all of this could be made sense of, this diversity could be made sense of by arranging it in a tree type of topology, which you see on the screen. And the topology was meant to indicate that similarities and differences in living forms, please allow me to repeat, the only forms of life we know are those that are allowed, around us, I mean, right? You, me, the trees, plants, frogs, fishes, everything. Anything that came before is a matter of conjecture. Okay. So the claim made was that this diversity can be understood only in terms of this tree-like topology, where similarities in forms today indicated recent common ancestry, and a great difference in forms around today could be accounted for by saying the ancestry extended much further back. So you had a ramifying tree, and this is the familiar tree of life. It doesn't look like a tree this way, of course, but it has the topology of a tree, as you will see immediately. The problem was, however plausible this looked, how to account for the tree. Where did the tree come from? And that's where Darwin and Wallace came on the scene with this revolutionary finding called the principle of natural selection. And they said that this tree comes about as the result of a whole lot of natural processes. By the way, the word natural selection, the phrase natural selection doesn't imply there's some mother nature doing the selection, but natural selection in the sense of natural law, in the same way that you would talk about a physical law or a chemical principle. It's natural in that sense. Okay. So they said that patterns of common descent, in fact, are what lie behind these differences and similarities. And this ramifying picture comes about once you accept a particular theory, which, it's interesting to note, was proposed essentially on what one would today call theoretical grounds, meaning a lot of suggestive evidence, right? Reasoning, sometimes extrapolating from the evidence, obviously in a logical sense inappropriately, so making guesses and so forth, and then proposing that there were certain principles that lay behind this thing called natural selection, which led to evolution, which meant change, and it's the end product of that change that you're seeing now. This was the assertion that they made. And there's something called the principle of continuity, which is important to emphasize. It's not going to be part of my talk, but worth keeping in mind, which roughly says that you can go from any one of the living forms that you see there on the top. Please remember there are 100 million of those. Okay, so obviously can't show all of them here. But any one of them, and by displaying them on your, putting them on your paper, take a pencil and go from any one form and go to any other form without leaving the paper. That's the claim that's being made. So in some sense, there's continuity. That was the Darwin-Wallace principle of continuity. Okay. And it turned out that this principle of natural selection at one stroke explained a huge number of things about biology, about the living world. And to this date, the best way of seeing what it explained at the time and how well it did so is by reading The Origin of Species, the book in which Darwin put all of this down. It's a very readable book, and I strongly recommend all of you to pick it up and go through it. It became a bestseller in its time, which is astonishing considering that it's also considered, at the same time, the founding book in evolutionary biology. It's something like the Principia of Newton, which would never have become a bestseller. Impossible to think of it, but this one did. Right, so what is natural selection? Natural selection, again, I draw your attention to the word natural, happens in nature. Natural selection simply says, and the wording here is mine, simply says that there are certain properties which are followed by living matter. So this is the way in which one has now grown to think of plants and animals and microbes and everything with which the word life is associated. And the reason for thinking of it as living matter is because there's growing realization that the laws of physics and chemistry themselves explain a great deal about the weird forms of things, behaviors that you see in living matter. Okay, so Darwin and Wallace said, living matter exhibits variation. That, of course, you could have seen in that first picture itself, enormously different. But these differences that they were speaking of were not simply what was illustrated in that slide, but what you might call ramifying differences going backwards, by which I mean these big groupings, which are called phyla, for those of you who remember, which were illustrated there on that picture, they are very different. Now these phyla are made up of subgroupings. You can give them different names, families, orders, this and that. People have different things. They differ among each other. Then you have something called a genus, which is closest to something like an objective grouping. They differ among each other. Within a genus, you have species. They differ among each other. Species are made up of individuals. For example, in this room, I see only a single species. All of us are individuals. We differ from each other. So differences occur at all scales in biology. This is the point that Darwin and Wallace made, please remember. Secondly, some of these differences have the property of what is called heritability, which is they're passed on from parents to offspring in a way that depends on the biological makeup of the parents and offspring, in a way that reflects the biological similarity between parents and offspring. Because children get a lot from their parents. Children get money, for example, from their parents. They get language from their parents, right? The particular language they speak. But this is not what's being referred to here. Something which can be tied up with that biology. What that biology means needed a lot of time to get clarified. Secondly, I beg your pardon, thirdly, correlated with these micro differences and the extent to which these micro differences are heritable, meaning can be passed on from parents to offspring, you get differential reproduction. So some aspect of these differences in some individuals enables them to have on average more children than some other aspect of the same trait in a different individual. Please remember, these are assertions, right? So these are, since there are three of them, you might try and say they are the equivalent of Newton's 3 laws of motion, just the number 3. But the point is that they are testable assertions. This is something that keeps getting forgotten. From these assertions, it's very easy purely logically, knowing what you know of biology, it's very easy logically to show how that picture in the first slide came up, how you get diversity. It's not a straightforward matter. When I say very easy, people spend their lifetimes over that and still have been doing it to try and understand the details, but you can do it. So at least in terms of principle, you can do it. But whether these assertions are correct or not is a different matter. What you can say for sure is that if one or the other of these assertions, one or the other of these statements is wrong, evolution by natural selection cannot take place, which means either evolution cannot take place, or if it does take place, it cannot be by natural selection. And we have examples of that as well. But for the moment, for this talk, we will assume that we are talking about evolution by natural selection, where these principles are followed, which, by the way, happens to be empirically validated in a huge number of cases. But do keep in mind, there are interesting cases, many of them, where this is not true. Okay. So the upshot of all of these things, assuming that are true, is that these traits, which are hereditary, heritable, show two types of changes, right? They show constancy in the short term, so no change at all, and they show gradual change in the long term. So in the short term, children are like their parents, as far as this goes. In the long term, however many great-grandchildren are different from those first parents. So both of these can be explained successfully by the principle of natural selection in accord with what you see in the living world. Right. Now, there is a big jump between the propounding of this principle of natural selection in 1858 to what biologists call the modern synthesis, which is the kind of, for the physicists and people, students of physics in this audience, it was something like the post-Newtonian developments in physics, which finally set the stamp of approval on what Newton had done, work involving the work of a great many experimentalists as well as theorists. So the modern synthesis, which hard to put a date on it, sometimes one says 1940, finally came to the conclusion that evolution works largely via a combination of natural selection, which is, as I told you, a logical consequence of certain properties, and chance effects on account of many things, including demographic factors, population sizes and so on, which we won't get into. Professor Mukunda reminded me to remind you that there's a very fine book by the French biologist Jacques Monod called Chance and Necessity, which in fact is about precisely these two aspects of natural selection, the chance aspect and the seemingly necessary aspect which follows later, which means it's a logical necessity of certain properties being followed. Right. Now, the modern synthesis did something else. It said, yes, this is good. We put, as I said, our stamp of approval on this as a valid explanation for biology in the large sense. And it went on to add, what lies at the heart of all of this is this thing that we call genes. A point made by the side, which is, I think, appropriate in this hall in particular. There are many aspects of biology, including evolution, I've already mentioned this, which do not need natural selection to be invoked for their explanation. And one of them is this interesting brilliant blue color of the Indian roller bird, which is a very common bird around us. And the colors here, it turns out, are not due to pigments. Pigments are either protein molecules or products of protein molecules in some sense, and can be ascribed to the working of genes, again in some sense, let's not get into details, and therefore could be explained as products of natural selection. But these colors, it turns out, are due to birefringence, so they are a purely physical phenomenon. And the story behind these colors is fascinating. They were first elucidated by C.V. Raman, probably in this hall. I don't know whether he spoke about it here, but it's interesting, Proceedings of the Indian Academy of Sciences, and it's counted as a landmark paper now in showing that you could get non-pigment based colors. So there's an example of physics directly playing a role in evolution. Okay, now something else, and I think it's important to realize there's a physical explanation for things, and there's a selectionist, meaning biological explanation for things. And it's worth keeping in mind that the spirit of these two explanations is very, very different. And that's illustrated by this cartoon. So the question behind this cartoon is, why did the apple fall on Newton's head? Straightforward question. And the answer, which Newton gave in some sense, and all of us know is true, is because of the gravitational pull of the earth on the apple. So the earth pulled the apple. Of course, the apple was also pulling the earth and so on, but anyway, ultimately Newton's head came in the way. Simple answer. See, you could cook up a selectionist experiment which is not facetious at all, except that it's wrong. The explanation is this. In the old days, much before Newton, of course, apples used to fall in all directions. But only those that fell on earth took root. The seed germinated and you got plants. And since this business of falling in different directions was a heritable trait, only the ones that fell to earth left behind progeny, which is what we see. Of course, Newton still came in the way, but that's a different matter. Now, the interesting thing about this explanation, which depends on natural selection, is that A, it is scientific, B, it is testable, and obviously you can't now test with apples which could go elsewhere, but we have good reasons for thinking that's not the correct explanation. But it's a physical explanation. The first one was a physical explanation, and this is a biological explanation. You see their spirit is very, very different. Good. Point 2. Here, again, if you don't mind, I'll go by a pair of cartoons because they make the point better than anything else that I've seen to show why it is individual reproductive interest beyond all else that counts in the principle of natural selection. So this is the cartoon. I must thank my friend Bayram Hoshmanzadeh for this. He put it together. So there are two members of the same species running away from a tiger, and the tiger obviously has strong interest in catching them. And one of them tells the others, we can't run faster than him. Basically trying to say, it's no use. Then the second one says, I don't want to run faster than him, I want to run faster than you. Right? So this is the principle of natural selection. What counts is not simply reproductive interest, but differential reproductive interest, which is why these micro differences that I just mentioned earlier become important. So keep that in mind. Individual reproductive self-interest. You might like to put the word selfishness on this, maybe not, that's up to you. I've been trying to find out when the word first entered the literature in this context. I've not been successful because I always seem to find something before what I thought was the first usage. So if anyone knows, please let me know. Right. What are these things called genes? Okay, quick history of genes. They begin with Mendel, who was trained as a physicist, please remember, and Mendel's work, which established what we call classical genetics, sometimes also called modern genetics to distinguish it from molecular biology, was very much a physicist's experimental undertaking. He did something which was unprecedented in biology but routine in physics. You have to do it in physics, which is he prepared the system. You know, this is a little bit like Galileo's testing the law of falling bodies by using an inclined plane, making it as polished as possible, using very, very polished balls, making sure there was no other disturbance, no earthquakes in Pisa at that time, that kind of thing, right? Entirely artificial situation, of course. But then he tests how long it takes for these balls to slide down as a function of the angle, etc., etc. Mendel did something like that. What he did was to take these pea plants, which he had decided were suitable for his purpose. So you see there's some pre-thinking which goes on with it, and then prepared them. So what he ended up with are plants which don't exist in nature at all, in the sense that what you would now call their genetic makeup was engineered by Mendel. Engineered in the classical traditional way by what's called inbreeding. Many generations of inbreeding. So he got what are called pure lines, genetically pure. Now it's really like using, microbiologists do this routinely. You always work with purified cultures. So advantages and disadvantages. He purified his plants. Then he crossed them, found out that there were traits which could be passed from parents to offspring. Here you see height. But in the passage from one generation to the next, there were strange numerical ratios that cropped up. And these are ratios that, again, I suspect all of us have heard of in middle school or high school. They go like 1:1, 1:2:1, 1:3. And he grew more ambitious after that, 9:3:3:1. You can see that there are simple compoundings of binomial ratios where you have to add some things to get, for example, 1:3. 1:2:1 you recognize immediately. Mendel was also trained in mathematics, specifically in statistics. And by looking at these ratios and by putting together a huge number of experiments, so actually making use of statistics, this is much before the t-test and this and that, just looking at the numbers, he realized that they must contain something in them. The fact that these numbers were as close to simple numerical ratios as possible. By the way, if you go back to your history of science, exactly the same kind of reasoning that John Dalton used in coming up with the atomic theory. Simple ratios. So Mendel uses this. He said the simple ratios must mean something. And he reached this extraordinary conclusion that these things must mean that behind the hereditary traits themselves, there must be something particulate in nature, which combines one from each parent, right? And therefore, which is present in 2 copies in each parent. So you might almost say he invented genetics from mathematics. This is one of the few examples. There are a couple of others. One of the few examples I know where mathematics actually led to a genetic discovery or a discovery in biology. So that was Mendel and Mendel's genes. And the astonishing thing is, Mendel's work itself lay in obscurity, was not picked up by anyone. It was picked up by some plant breeders, this and that. You know, they said, yes, there's this person, Herr Mendel, in this monastery who has done interesting work, blah, 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 blah. But curiously, the very thing that we would credit Mendel with today, namely his ability to see that you have to prepare the system, right, was held against him by botanists. They said, look, I mean, these are not plants that we see anywhere in nature, and who has come across these funny ratios? We've been crossing plants all the time, and the children are invariably a medley of their parents. And this man says, these offspring, these children resemble their parents in every respect except height. That's crazy. That never happened. So obviously he's done some cooking up, not cooking up in the sense of fraud, but you prepare the system carefully enough, it can give you any result you want. But these experiments of Mendel were rediscovered in the strangest possible way in the year 1900 by a number of people, Cermak, Correns, and de Vries. And they were discovered in this odd way too. They were, unlike many people these days, meticulous in looking for whom to cite when they wrote up their papers. And all three of them, in very carefully looking through the old literature for anything that it might have to do with their work. By the way, in their work they had rediscovered Mendel's laws, and they were obviously very excited, but they were also very good, very, shall we say, honest scientists, and they said, let's see whom to refer to. All of them landed on Mendel's paper, which was in this obscure botanical, in fact it's a journal of plant hybridization, not even botany. And they said, my God, this is what I've done. But they were honest enough to cite Mendel, say he did this before us. So, and as a result, it's interesting, they're as famous as Mendelists, and justly acclaimed for what they did. That was 1900. In 1915, this book came out, published by a bunch of people from the US, T.H. Morgan and his students, The Mechanism of Mendelian Heredity. And I can't think of any other instance in science, and I'm probably reflecting my own ignorance when I say this, I can't think of any other instance in science in which a field began 1 year and was completed 15 years later. So what we call classical genetics is there. There were embellishments later, many of them, and some of them we'll speak of, but the field was done. Extraordinary achievement. And in fact, this was really revolutionary in every sense of the term, and closed the book on a field. It seemed to suggest that these Mendelian particulate entities hypothesized by Mendel were real, and so this gave them the mark of reality. They were associated with these things that you could actually see in cells called chromosomes. So you could not only say there are these particulate entities, but you could say that's sitting here. And in many cases you could say this one is to the left of that, that one is in between these two, and so on. So you could actually prepare what are called genetic maps, which is in fact what a great deal of that book is about. Subsequent development in classical genetics went ahead with this. So I'm just listing names and references. These slides are here with the Academy. Any of you who want can look up the references later. Fairly soon it turned out that you could deal with these entities in the way you deal with chemical things. So you could take something out, inject it somewhere else, and find a trait being transferred. Remember, what you were injecting was presumably a soup of chemicals, right? And in this case, that soup seemed to contain whatever the origin of that hereditary trait was. The phenomenon was called transformation. So this was the Streptococcus bacterium, which came in two varieties, infective and non-infective. And the infective variety, you could show, manifested its infectiveness via something that you could inject. So that's one thing. Then, curiously, there was this another intervention by a physicist which stimulated many people, though not biologists. It's interesting. Schrödinger gave a series of lectures in 1943 titled What is Life? By the way, again, an extremely readable book, strongly recommended to all of you. It's also available in an online version, but please don't read the online version, read the book. Good for the mind. Okay. There, he started exploring what this word gene might mean, what this mysterious carrier of heredity might mean. And Schrödinger said, look, maybe part of its mystery is because its working depends on laws of physics. Schrödinger was a physicist, and he knew ultimately everything has to work according to the laws of physics. He said it may depend on laws of physics which are still unknown. So trying to follow through on that discovery is a way of following through a new kind of, starting with a new kind of physics. And that set a lot of interest going. In 1953, I think this really was the defining moment for the bulk of physicists as well as non-physicists, biologists. Watson and Crick came up and said, aha, this is the gene, this is DNA, the genetic material. So it's the form of a chemical, name was DNA. DNA was known for a long time, but they said this is it. And of course in science, however much conjectural reasoning leads you to a conclusion which seems inevitable, saying it's here, showing it in front of someone carries kind of strength of validation, which other things don't. So DNA turned out to be the gene. There's something called a genetic code through which DNA exerted its effect. So DNA, and this had been predicted by Schrödinger, seemed to do what it did. Remember, ultimately, Mendel and the plants, tall versus short. DNA seemed to do what it did by making use of an intermediate step which was entirely arbitrary, meaning expressible in symbols. And this is something which has remained of interest for a long time. Where does this arbitrariness come from? But that transition is symbolic as far as we can tell, and the transition takes you from DNA to what are called proteins, which are the building blocks of all living matter, which also have enzymatic activity, which is interesting. So they can make other kinds of things which are neither DNA nor proteins, basically build bodies. So proteins build bodies. But the step through which DNA does this, it turns out, has at its beginning this symbolic correspondence, which is called the genetic code, which takes you from DNA to proteins. I'll leave the last part for later in case anyone has questions. Now, gradually it turned out that these things called genes, please remember I'm using genes and DNA as synonymous. Turned out that these things called genes can do different things. We've already seen that they can make proteins and therefore build bodies and therefore in some way convey heritable traits. Some other genes, it turns out, do nothing else but honest to goodness chemistry. They just sit there, nothing symbolic. They take part in chemical reactions which are useful in deciding what element of heredity is transferred, when, how much, etc. So these are regulatory molecules, not so much informational molecules. DNA does that as well. Then, much before the main body of this story, which I'm going to develop, it turned out that in some cases, in some places, these genes can also jump around. So what you see is the common Muskinjoda maize, cob, right? These grains, at least in the variety that Barbara McClintock worked with, very often exhibited these strange changes of color. Remember, in the same generation, so basically what she's doing is Mendel's experiment, but instead of getting something systematic, she's getting something which seems to have gone haywire. She interpreted this already because something was known of pigment production. Remember, I told you, ultimately due to protein action. She interpreted this correctly as meaning that the genes which are behind this pigment production must be unstable, and even went so far as to say the gene seems to be here at some point of time, here meaning here on the chromosome, then it seems to disappear, later it seems to come back. So it shows that genes have other aspects to them other than simple making proteins or regulating protein. All of this formed the background of what was to follow. I think the critical input into understanding Dawkins's use of selfish in the selfish gene came from 2 or 3 different kinds of lines, and I'll illustrate them here. I think 2 of them are actually mentioned by Dawkins in his book, probably not this. So this is the familiar case of the peacock and the peahen. The peacock looks flamboyantly colored, the peahen looks more sober. Remember, both of these are animals which are members of the same species, different sexes of both, live in the same place, eat the same food. same kind of lifestyle you would imagine, other than one being a male parent and the other being a female parent. Why does this cause or lead to such a striking difference in their appearance? Because if you say that plumage and elaborate tail feathers that the male has are in some way of advantage to the male, enable the male in some way to be more successful than males without it at having children, well, then they're good for the female too, because they have nothing to do with reproduction per se, quite obviously. And similarly, all kinds of things. You can see the number of differences. The male also exhibits this extraordinary dance, which I think many of us will have seen. Why doesn't the female also dance? Because the dance is in some way good for the male, must be good for the. So ultimately, the answer to this turned out to be fairly humdrum. It is that it is to the advantage of the female's reproductive success, to the advantage of the female's reproductive success, that the male have these traits. It's a slightly unusual way of looking at things, okay? So what is of advantage in me is something in you, kind of thing. And it turns out that that's a really rather nice line of argument, interestingly initiated by Darwin to begin with. It's called sexual selection, the entire, and it's spawned the whole area of biology. The point for us though is that it works indirectly. Then there was this huge big puzzle, Dawkins spends a lot of time on this, the puzzle of apparent altruism. In many living organisms, there seem to be cases of individuals seemingly giving up their lives or being doomed to die without having children. Now that is, in the sense of evolution by natural selection that I have already presented to you, that is impossible. So if you are a proper believer in natural selection and someone says this happens, your correct answer is I don't believe it. Unfortunately, it does happen. Happens in many, many species, in many, many organisms, most spectacularly in what are called the social insects, ants, bees, wasps, termites, right? And in these social insects, you have the additional embarrassment, or natural selection has the additional embarrassment, that the bulk of the population of an insect colony is made up of individuals who are sterile from birth, cannot have children. Now, if you cannot have children, there's no question of passing traits along, and the thing is sort of self-referential impossibility, right? But this trait of sterility is being passed on. In a sense, their enforced celibacy is heritable, which it shouldn't be at all. I mean, by definition shouldn't be. But it is there. How do you explain it? So this is one other element which Dawkins expands on his book. By the way, the explanation itself came before the book was written. It was by a person called Hamilton, who really is one of the founders of this entire field called sociobiology. The other one being a person called Trivers. Hamilton and Trivers set the stage, but Dawkins made it popular very successfully. So, puzzle of apparent altruism. Remember, the conventional explanation of this is very straightforward. All these sterile insects are working for the sake of the hive. They are behaving altruistically. It's because of them that the hive or the ant nest is successful. It's able to forage successfully. It's able to keep nasty predators away, wasps away. It makes sure that if there are any fungi around which are being used for food, they don't grow stale, right? And invite bacteria which later harm the hive, etc., etc. They feed the young ones. Enormous range of activities, behavioral activities, all for the good of the hive. That's quite obvious. So it's the same kind of argument that you would use in a human society, where the behavior of individuals is, in many cases, for the good of the society as a whole. The reason it fails here is because you already said you want to depend on natural selection. Yeah.
So if I take two sterile members of the same generation, what would we know about their genetic variation?
Okay. Okay. No, that's an interesting question which we can take up later. For all practical purposes, no genetic variation.
So they're clones?
That's the point. They're not really clones, but you can take it that they are like clones. They can be clones, by the way. Okay, so there are cases in which they can be clones. One clue to how this might happen also came, in fact, that partly answers your question, also came through this realization that there must be some kind of indirect selection operating here. Remember, in the case of the peacock and the peahen, there was indirect selection acting on the peahen via her husband, via the peacock, right? Some kind of that thing might be happening here. Turns out now that this explanation, and I'll tell you in brief what the explanation is without going into the algebra, which is really quite straightforward, but still. This explanation depends on the curious fact that in some of these social insect colonies, in fact in the ants, bees and wasps, males are born from eggs laid by the mother which are not fertilized. So you might say sons never have fathers, they only have mothers. Daughters, on the other hand, have both a father and a mother. Now it turns out, using this elementary algebra which is illustrated on the screen, those of you who are interested can look it up later, this in itself is enough to show that the consequences, well, the consequence can be something very, very strange. It can be that it's more advantageous to a wasp or an ant or a honeybee, more advantageous to any one of these, to persuade her mother to give her one more sister than to reproduce herself. This is bizarre. Here it turns out that this can happen. Okay, so this is one case in which indirect selection seems to work. Now this form of indirect selection was used as a clue. This doesn't happen in every case, I must tell you, though this is rather nice as an illustration. This form of indirect selection, or the possibility of this form of indirect selection, was used by Hamilton, whose name I've mentioned already, to say that you could get selection for altruistic, seemingly altruistic traits acting on an individual who behaved altruistically, but actually to favor reproduction in someone else. And this someone else here, of course, was his mother, the queen, who kept on reproducing, right? So this apparent altruism masked what you might call selfishness. Now I'm coming to the end. Yeah. Ah, okay. Thank you for telling me. And it's a good thing that I'm coming to the end of that. So now, this kind of picture in which it appears that genes, by moving in all kinds of ways, right, can lead to evolution by natural selection without the reproductive interests of the individual carrying those genes being directly implicated. This kind of picture was metaphorically termed by Dawkins to illustrate that genes are selfish too, not just individuals, as at least one of those two people running away from the tiger was, but genes can be selfish too. So this is where the nomenclature of selfish gene came up. Now, if you try and explore this in somewhat more detail, what the possible implications of the word selfish can be, you can end up with three different interpretations, the last of which is Dawkins's interpretation ultimately. See, one interpretation is trivial, which is to say, and biologists have known this for a long time. There was a person by the name of John Bonner, who, by the way, also spoke in this auditorium once, 30 years ago, 35 years ago. He was foremost in pointing this out. We think of ourselves as we are here, right, individuals. The mental image we have always is of people, or for that matter plants or animals or anything, as snapshots frozen in time. Of course, we realize that's not always the case. So we were children once and we are grown up later. But still, it's a series of snapshots. So someone took a photo when you were young, and someone now with a mobile phone takes a photo when you are much older. But you are just you, like you. Bonner pointed out that individuals or organisms, or to go back to that earlier phrase, living matter, is really a cycle. So in other words, we are creatures who exist in space, so to speak, whatever, as well as time. So there's a continuum involved in this concept of living matter or living organism. And the continuum being a cyclic process from what are called germ cells or reproductive cells through embryonic development, through adulthood, to reproduction in turn, and then germ cells again, being a cyclic process, entirely up to you where to begin the cycle and where to end the cycle. So it's perfectly valid to look at natural selection in the way Darwin and Wallace did, or would have if they had known of genes. It's valid to look at natural selection as natural selection is a means for individuals to transmit traits across generations by using their genes as vehicles. No individual crosses a generation by definition. But you can do this sneakily this way by letting your genes carry your message across. So genes are vehicles for natural selection. Dawkins said, well, fine, perfectly right, I have no argument with that, but why don't we instead think of people as vehicles used by genes to go from generation to generation. Equally valid if you have a circular loop, you can begin from anywhere so long as you close the loop. So that's one way of looking at selfish gene, which simply involves a change in perspective. Okay? See, just as conventional evolutionary biology said people act selfishly, it so happens that their genes are transmitted in the process. You could say, no. Genes act selfishly, it just so happens that people are not transmitted, but the traits are transmitted. So perfectly equivalent matter of semantics. The second point is more serious. The distinguished statistician and geneticist R.A. Fisher put this best. You know, Fisher was a student of, again a student of physics, and he was a student of James Jeans, who at least some people in the audience will have known as a great popularizer of science. Fisher's ambition, or at least one of his ambitions was to try and prepare a proper quantitative theory of evolution. He knew it had to be statistical simply because of this huge amount of variation that you see. So his kind of idol was thermodynamics. He said, can I come up with something like the second law of thermodynamics, which encapsulates evolution by natural selection? And he did come up with something. It turns out, under obviously rather restrictive conditions, but they're interesting. One of those conditions he needed to impose was that in going from generation to generation, genes act pretty much by themselves. Each gene acts by itself in going from, this is called the property of additivity for those of you who want to know the technical term. So it's basically like saying that the sum total of all the properties of all the genes can be decomposed into properties of each gene separately. Remember, that's a contentious point, it's testable. But if you can do that, turns out that you can actually come up with an expression whose time derivative is guaranteed to be positive. And of course Fisher, because of the history of language in the field of evolution, called this fitness. He said fitness plays the same role in evolution as entropy does in thermodynamics. But that's a very interesting area of subject of study in its own right. The last thing is the one that we are interested in, selection possibly acting on genes per se, throwing the organism out of the window. Okay, does that happen? If that happens, then the thing is really selfish. Turns out that there are cases that can happen. This I've already illustrated. Life cycle can begin with anything. This is Fisher's equation. There's no algebra in this, but Fisher has a lot of algebra and calculus. Additive genetic contribution. This is the kind of thing which the last thing touches on. So this comes from observations of the following kind, which is you have two groups of organisms. One is conventionally called, let's say, okay, let's forget that, group A and group B. Both of them exist in nature. right? Both of them are males and females. In this case, they are flies, by the way, as you can see on the screen. The difference between them is the following. In one group, when a male mates with a female, she lays eggs. The eggs develop into children, whatever, young flies. They have an approximately 50-50 ratio of males to females, boys to girls, right? Mendel's ratios, 1:1. In fact, this particular experiment is used even today in class to teach Mendelian genetics. But in group B, it turns out, in some cases, there are only sons born, no daughters. In other cases, only daughters born, no sons. Bizarre. Otherwise, to all outward appearance, the individuals in the two groups are the same. Turns out that the reason for this is that in some groups, for a underlying physical cause which is understood, the following thing happens. Remember, sex determination in these flies, as in us, depends on an X chromosome and a Y chromosome. Sometimes they don't need the Y, but for the moment we'll pretend X and Y. So X and X gives you a female, X and Y gives you a male, right? Sometimes it happens that when a male reproduces, remember the male is XY, and if the male has read Mendel's papers, it knows it has to produce X chromosomes and Y chromosomes in a 50-50 ratio. Sometimes that X chromosome shoves the Y chromosome away. By the way, that really happens, meaning there are factors on the X which prevent the Y from taking part in fertilization. So the male produces only X, only has daughters. In other cases, very worst thing happens. Male produces only Y, only has sons. So there are actually cases where these selfish genes do appear. Finally, and I really am ended here, this is the last slide. See what has happened here, what happened actually with the publication of Dawkins's book, and even slightly before Dawkins's book, with the publication of equally famous book called Sociobiology by a person called guitar, the name good God, Wilson, Edward Wilson. Something happened in the field of biology which was new, except that this sort of thing happened when ideas of eugenics were gaining currency after the period of the First World War and thereafter, of course, Hitler's time and so on. Which was the following. So the strange thing which happened was the following. People were attacked fairly strongly by others whose credibility in the field was just as good as those that were being attacked. But they were being attacked for saying or doing experimentally things which were dangerous, socially dangerous, I mean. Except that in this case, it was not so much doing anything in the usual sense, but in the use of language. So this business of using words like selfish and altruist, as we have seen, which gradually slid over from being used in humans to being used to other organisms to being used for genes. This usage was looked upon as dangerous because it seemed to portray a view of living creatures, specifically of human beings, as somehow being under the command, if you wish, or control of their genes. So two of the three quotes I read out in the beginning, in fact, actually seem to illustrate that. It's in your DNA. You can't do anything about it. So you can see the social, possible social and political implications of this. Dawkins made it worse for him. Oh, by the way, those words have gone on. So in my particular field, cheating is common. Noble, believe it or not, is common. I should also tell you, I don't work with humans, I work with amoebae. Amoebas. So you think of a noble amoeba, a cheating amoeba. Forgiving has come in. So the whole thing has gone wide. Now my point is, the people who are doing it are obviously doing it tongue-in-cheek. They are not stupid people by any means. But they seem to think, look, we never have any fun, we never make anyone laugh when we write our papers, now let's do that. Except that this use of words has now taken on, since Dawkins taken on connotations which have really been bad. Okay, now Dawkins made matters worse for himself. So for example, in the first edition again, he calls organisms, including us, refers to them in terms such as a selfish machine programmed to do what is best for his genes. Now, that's also factually incorrect. The notion of genes as programs is actually wrong, I mean in terms of computer programs and so forth. That's a different matter. But you see, this kind of language seemed to be tailor-made for a kind of mindset which was totalitarian, which said people, if you engineered people sufficiently well, not a tendency that has gone out. I mean, those of you who are following the literature with what's happening with human genetics research these days know this is an undercurrent. If you can engineer the people sufficiently well, you can get what you want. And then look at this, we are survival machines, robot vehicles. By the way, by we, he refers to us here in this room. We are survival machines, robot vehicles, blindly programmed to preserve the selfish molecules. See, now the molecules have become selfish. Selfish molecules known as genes. So this kind of thing landed him in very, very hot water indeed. And led to the book being assessed not so much on its merits, of which there were many, or on its demerits, which were also there, no question of that. I mean, it's not that everything he said there was correct, but because of the language it was used, which was a great, huge big pity. So he pretty much dug a hole and jumped into it. And other things, so the publishers decided to add to Dawkins by saying the book describes savage competition, ruthless exploitation and deceit. I think the book would have been a bestseller even without any of these things, because it's one of the finest examples of popular science writings that I know. Lots of things in it that are true, lots of things in it that are not true, implications which are true, implications which are not true. But unfortunately, all of it has got lost in the noise surrounding his use of words. So to end with, I would just say this, and this is something that not too many people feel going by the literature, which is you have to be very careful using words like this in biology. Thank you.
So maybe we can have a couple of questions, and then afterwards we can have more questions during the lunchtime. So somebody? So maybe even not a couple of questions, is it?
Thank you, sir. Plants and animals have traits which one doesn't have, mutually exclusive traits. So when you drew the tree of life, it always started with one stem and then split into two. And what was that one stem and why these don't intermix?
The original stem at the beginning?
Yeah.
That's a matter of much debate. We still don't know. Because we don't know it, we have given it a name. It's called LUCA, Last Universal Common Ancestor. Lots of speculations on what it might be, but we still don't know.
Okay, thank you.
So, fantastic and fascinating talk. Just one query, that would it be correct to say that one might have accidentally produced a system which behaves like a living system, but without having genes, that system wouldn't have the wherewithal to propagate and be almost immortal at the level of species sense. So it is therefore the genes which drive not only multiplication but also cause the biodiversity, and hence is essential to a living system.
That's an interesting point. See, most people are agreed that there are two features associated with life without which the thing wouldn't be called alive. One is what we might call maintainability, being around for a long time, which involves not just being there but also repairing yourself constantly, because the second law is always working against you. So maintainability. And the second thing is what's called replication. Now, replication is not just copying yourself, but copying yourself in a way that enables your copy to copy itself. Okay. Now the question arises, are genes essential for either of these? Today, they're essential for both. No question. Genes in this particular chemical form, molecules of DNA, or there's something called RNA which is similar, which can serve the same purpose in other organisms. But could you come up with an entirely different kind of chemistry? So for the moment, let's say you think of chemistry, which could achieve these two ends. And there are many people who are working along those lines, think that might be possible. In fact, there's some fascinating work which has been carried out recently by a person called Shashi Tutupalli at NCBS and ICTS in this city. He has built on work done by Ranganayaki and Bahadur, also as it happens about 50 years ago, where they used inorganic chemicals, so it's a cooking recipe basically, inorganic chemicals to come up with something which can actually form compartments, so a body in some way, but with this compartment, it can replicate itself and maintain itself. So there may be forms of what technically could be called life without genes in the sense we know them.
Thank you.
Okay, so far there have been lots of questions, and maybe this particular time people are hungry perhaps, so we can proceed for lunch and we can ask many more questions. Will join us. Thank you for all the morning session speakers, and thank you, Professor Geeta. I just request her to give a memento, present a memento to Professor Nanjulaya.
Thank you, Geeta. Thank you.
So let's meet here at 2:20 or 2:20. I hope, like yesterday, your digestion doesn't take over now and then you fall asleep. Um, I hope, I just wanted to ask you, most of you have brought you scissors, yeah, for this afternoon session. Okay, so I've welcomed Professor Indulekha to chair this session.
So good afternoon and welcome to the afternoon session. We have got Professor M.K. Matthew. As he describes himself, you can see professor at large, like barrister at law or something. He's going to talk to us about plants, that's what he says, even though if you look at his website, it will say he works on potassium channels, whatever they are. He has come through IIT, IISc and spent time in the US, after which he came to settle down at the National Center for Biological Sciences of the Tata Institute of Fundamental Research in Bengaluru, and now he's going to speak to us, sharing his wisdom and knowledge. Professor M.K. Matthew.
Thank you. I'm not too sure about the wisdom part of it, but I really have to thank Resonance for getting me to be a part of this outreach program, because over the past day and a half, I have learned an enormous amount. Sorry. Yeah. I would also like to thank them for timing my talk. You see, following Professor Nanjundaya is an extremely tough ask. Yeah? And I'm hoping that the lunch break would have helped a little bit, yeah? So that the comparisons would have been forgotten to some extent. Okay? So what I'm going to talk about is about crops, salt, drought, survival. Not survival, not quite in the same way as Professor Nanjundaya talked about, but important for our survival as well. Yeah? And what I'm going to do is, well, many of the talks have been overviews, which have been extremely useful. I mean, if they had not been overviews, I would probably not have understood them. Yeah? But I think it is also important that you get some idea of how a scientific problem is addressed. I mean, that you recognize that this is an issue, you make hypotheses, maybe you don't make hypotheses, maybe you just do experiments and see if a hypothesis will develop in the process of looking at all of the data. Yeah? But whichever way you do it, you end up with some conclusions that you can put out to the world at large, and that's part of what we're going to do. We'll do a little bit of an overview, but also this. Yeah? So you'll understand why I have put it as a 6,000-year story. And I'll start with drought. See, the monsoon this year is about 40% deficit as of now. Yeah? So this is a very troublesome possible scenario facing a lot of people in this country in the foreseeable future. Now, the problem with drought is, of course, it's difficult to live without water, right? And if it's difficult for us, it's even more difficult for a plant, because you can walk down the hall and pick up a glass of water. Plant can't do that. It's got to get whatever water is available for it right there. And the way it does is that it takes up water and nutrients, yeah, through the root. That's by using an osmotic balance, right? So there's osmotic gradient which drives fluid into the roots. But if you've got no water there, of course you've got no fluid to take up. And in addition, whatever fluid there is going to be so concentrated that the osmotic gradient is going the other way. Yeah, water is going to leak out of the root rather than you're being able to take up from the soil. So these are some of the issues that a plant has to face if it's living in that kind of condition. Yeah? So that's the problem with drought. Yeah? You can't do that if there's no water, and the osmotic gradient works the wrong way. But I'm going to spend the bulk of my talk talking about salt. There's a huge problem with salt. There's a lot of land, cultivable land, which is becoming too salty for agriculture, and that means all of that is going out of production. And why is it a problem having salt in the soil? Because the cytosol is high in potassium. The outside is low. The cytosol is low in sodium and high sodium outside. So now, if you've got high sodium from the medium, which is around there in the soil, if that gets into the cytosol, that's toxic, and the cells die. And if your cells, the root die, the rest of the plant dies. So you want to avoid getting too much sodium out. And we'll see how crop plants deal with it. I'm not going to talk about cacti, for instance. Cacti have worked out certain strategies which you can't ask a rice plant to do. In the same way as mangrove plants have worked out certain strategies. You can't expect your crop plants to do that. Now this is a rather old map. It shows you areas which are affected by salinity. And what you see is that there are large parts of the globe where salinity is a problem. This is something I got up also from the FAO, saying that something like about 50, well, this was in 1918, so now the numbers are going to be higher. But a large fraction of irrigated land is affected by salinity. And the estimate is that over 50% of arable land. So arable land is land that you can cultivate. Irrigated land is cultivable land which is irrigated. That's the difference. And that's going to be 50%. So that's going to be a serious problem. Right? So, and how is this brought about? This is in large part, for the irrigated land at least, the problem is that you're irrigating it with water which you got from a river somewhere, ultimately. And this water has come from mountains. It's got a little bit of salt in it. It doesn't taste salty, but it's not like distilled water. And that water, some of it will evaporate, some of it will be used by the plant and it will be transpired out. Bottom line, the water goes away, the salts stay. So nothing's going to happen in a year or two, but over decades, the soil becomes saline. And then if it gets too saline, plants don't grow. So that's the problem. So now immediately you might think, that's a modern problem. We'll just sort this out. It's not that modern a problem. So here's a paper. The first big cities, what we would call cities in those days, were in Mesopotamia. And there was this huge, there was big civilization in Ur, there's big cities in Ur and Uruk. And they survived for hundreds of years and then suddenly sort of, they're gone. And one reason for it, at least this is the reason that is put forward by Jacobson and Adams, is that the soil, it was being irrigated by water from the Tigris. And over time, the land became saline. They could no longer grow wheat, so they switched to barley. Barley can tolerate much higher salt than wheat. And when barley could no longer grow, that's it. So this is a 6,000-year-old problem. And it's about time we figured out how to deal with it. The real way to deal with it is soil remediation. That is, you get soil and you try to remove the salt from that soil. And there are departments of soil engineering which are trying to figure out how to do that. No immediate short-term solutions. The medium-term solution may be to grow plants which will give you food, generate grain, even under moderate salt conditions. So how do you go and develop a plant like that? And remember, we are not talking about cactus, something like this. You're talking about rice and wheat and barley also for that matter. So you can look at, one way of doing this is that you can take two varieties of the same plant. Say two varieties of wheat or two varieties of rice, and one which can tolerate fairly high concentrations of salt and the other which cannot. And you ask, what does the salt-tolerant variety do that the other guy does not? And then you figure out how it does it. Steps along the way. So I'm showing you what, that's above this concentration of salt is considered saline. It's about 20 millimolar sodium chloride in the medium. And you can see that just about everything that we are interested in, bread, wheat, rice, by the time you get to be moderately saline, these guys don't do very well. Rice, unfortunately, is extremely salt sensitive. But a lot of us eat rice, particularly in South India. So how do you deal with this? Well, one way is to look at wild varieties of rice. This is a variety called Porteria, and people in the Swaminathan Foundation are working on Porteria. Porteria does something interesting. It can grow in moderately brackish water. It takes the salt, pumps it out into salt hairs like this. You can see these droplets like salt, and the salt then drops out. So salt goes up, but it doesn't stay in the cytosol, it's just dumped out. Now you can't teach your cultivated rice to do this. That's difficult. So you're looking for a variety of rice which is cultivated, but which can tolerate salt. And it turns out rice is a much better plant to work with for this than wheat. And the reason is that in this country, we've got a huge variation in rice varieties. So this is just in the northeast. You can see all these different rice varieties are there. None of them are particularly happy in high salt. Northeast is really not a problem with water. There's plenty of water, not much salinity. So it's a good place. But a place where rice is cultivated and has to face salt is in Kerala, where a lot of rice is grown in the backwaters. So this rice is then subject to pretty near seawater. This poster says paddy in seawater. It's not quite seawater, but it's high salt. So this variety called Pokali is really the gold standard for surviving high salt. So what we did was to say, okay, let's take that variety and let's take high-yielding varieties like the Green Revolution varieties and ask as to whether they handle sodium differently. And what we did was we grew both Pokali and IR20. IR20 is a Green Revolution variety, very high-yielding. Pokali is the salt-tolerant variety, not particularly high-yielding. And you can see that there's very different tolerance to salt. And if you take a point like this, you can see that you can get concentrations of salt where Pokali is quite happy, no problem, and IR20 is quite miserable, but not dead. That's important. If it's a dead plant, no information. So then we asked, let's grow these guys up and see are they handling sodium differently. So in the roots, same amount of salt in both varieties. But in the shoot, I'm not showing you the data because it's complicated. In the shoot, there's considerably less salt in the Pokali shoot than in the IR20 shoot. Okay? So, the shoots have much less sodium than the shoots of IR20. Or there's another variety that we look at, this Jaya, that's not as salt sensitive as IR20. It's also a high-yielding variety. So clearly, there must be some mechanism which prevents the sodium from going up into the shoots. So that's what I've indicated in this circle over here. So how is it that you do this restriction? So remember, fluid is going in driven by osmotic pressure. Yeah? That's going into the roots. So it's water, it's goodies, it's nasties, everything goes in there. But at some point, you're going to say, only the goodies are going to go up into the shoot, and the nasties, no entry. Yeah? How do you do that? Yeah, so that you need to look at how control exerted over what goes up in the shoot. So for that, you need to look at what the root looks like. So that's a cross-section of a root. And there's two ways in which fluid can go up into the xylem and then get transported up into the shoot. One is that it enters the root, enters the cell. That's driven by osmotic pressure. It goes into this cell, goes from cell to cell to cell, and ultimately gets into the xylem. But that leaves the absorbance. You want to take up goodies from the soil, from this fluid, right? And the only portion which is exposed here to the fluid outside is this little bit. All of this surface is unexposed to the soil. So fluid actually goes in between the cells, in the interstices between cells, and there it can go into cells at each of these points. But now you don't want this to get loaded directly into the xylem. Instead, you have a barrier here, which is a waxy barrier. It prevents water from going straight through. And the fluid that actually gets in has entered cells. So there's some selection process in the process of what goes into the cell and what's left out. So only the goodies come in, and that's sent in. So this barrier, this waxy barrier, so we've stained that waxy barrier, it's stained yellow, and you can see that there are gaps in this barrier in rice roots. So it's not perfect. It does some block of the fluid from going in directly, but there are gaps through which this fluid can come in. So we asked, is there a difference between the amount of fluid that gets in Pokali versus IR20? And it turns out there is. What I'm plotting over here is the wax. We can extract that wax, measure it. And what I'm plotting over here is how much fluid has bypassed that barrier and gone into the xylem. And you can see that there's much more suberin, this wax, in Pokali, that's a round figure though, compared to the IR20, and correspondingly, there's a lot more bypass that's going through in the IR20. So we could then plot a lot of this data. So this is this bypass flow, and what I'm plotting over here is the total amount of sodium in the chute. Now it's no longer, So what you can see over here, different types of experiments, all the data is sort of combined into two groups. And what you can see over here is that when you have very low bypass flow, there's very little sodium in the chute. And if you were to do something which I do not recommend that you do, but you can try this, you just extend it. And what you find is that at zero bypass, there's almost no sodium going into the chute. So if there's no sodium going into the chute, you're happy. The plant survives very well. So this is something now that there are several labs, consortia more than labs, that are trying to find rice varieties that, and wheat varieties also for that matter, that can deposit this suberin out here, and thereby reduce the amount of sodium that goes up and make the plant salt tolerant. Now we'll go back here. We said this is what, if you take the plant which has just been grown in happy medium, normal medium, and this is the state that there's high suberin and low sodium uptake, low suberin and high sodium uptake in IR. Now, we subjected these plants both to mild salt stress. We put a little bit of salt, enough for the plants to feel unhappy, but not enough to kill them. So after a 1 week period, we did this experiment again, and what you see is that now the amount of sodium that's going in, even into the IR20, is a lot less. And the reason for that is that you've got a lot more of this waxy barrier which has been deposited out there. So the mechanism by which it is being reduced is, this supports the hypothesis that the amount of sodium going up is regulated by this wax. But what it also tells you is that the genes for making this waxy barrier are there in the IR20. You don't need to make a transgenic plant. The genes are there, they've been turned off. And they've been turned off because you're selecting for a high-yielding variety. Making all this wax and stuff takes a lot of energy, and that energy is not going into making grain. So now there are labs that are working on how you can persuade the high-yielding variety to make a little bit more of this wax. You don't want to make as much as this, because you still want it to be a high-yielding variety. So things have to be played around with. But more importantly, you want to figure out how to turn on these genes without pouring a lot of salt into the field. That would be a disaster. Right? So you've got to figure out, are there small molecules that you can apply to the plants which will get them to make this waxy barrier. So that's good. We figured out how to stop sodium from going up to some extent. But remember that even in this case, there is some sodium which goes up. A lot of sodium outside. Reasonably good job keeping it out, but not perfect. How many of you are watching the World Cup, by the way, football? Yeah, good. Yeah, you stayed up till 1 o'clock? Yeah, good. Yeah. So, both goalkeepers were fantastic. They stopped a lot of shots on goal. Neither of them was perfect. There were a few that went through. And you could say the goalkeeper was unfortunate in one case, but yeah, that's a different matter. But the point is that they were not perfect. If they were perfect, there would be no fun watching football. So some sodium will go through, and will get into the chute. And in that case, you can ask the question, will the Pokali cells in the chute be able to survive that little sodium which then goes up? The problem is, how do you do this experiment where you can look at the cells and the cell survival? The way we chose to do it is that we isolated the cells and we grew them in culture. And when they were in culture, we put in a dye where that's the dye. The dye goes into the cytosol and not into the vacuole or the nucleus. So you're looking at cytosol only. And this dye, the fluorescence of this dye increases when sodium is added. There's a problem with this dye. You need UV to excite it, so we use 2-photon excitation in a microscope, which is now fairly standard technology. And this allows you to look at sodium in the cytosol alone, not the rest of the chute, everything else. So these are images where we false colored the images. So that's 20 millimolar sodium, that's 100 millimolar sodium in the cytosol, right? So if you take the control, unstressed Jaya, unstressed Pokali, all the same, very low sodium in the cytosol. The moment you go to 100 millimolar sodium, nothing goes up in Pokali, but pretty high sodium in Jaya. 150, it's worse, but Pokali, no problem. You need to go up to something like 350 millimolar sodium before the Pokali cells give up. Yeah, ultimately, you hammer things, they'll give up. So that's what you see over here. And that's the plot. You can go up to pretty close to 300 plus. Yeah, this is about 300. Yeah, you can go that high in sodium, which is sea salt. Yeah? And it doesn't leak in. So what we can now do is another experiment, which is the results of which have been inferred. The experiment has never been done before, not before. We did it a few years ago. But it has been inferred that high sodium in the cytosol kills cells, yeah? Plant cells in particular. But we are now able to generate conditions under which we can vary that sodium in the cytosol, no proxies here, it's actual cytosolic sodium. And you look at survival, and you see that, no surprise, low sodium, high viability. Out here, high sodium, low viability, and Pokali does a lot better than Jaya. No surprises there. It's just substantiating something which is in the textbooks, but not directly demonstrated so far. All right, what's the basis of this? Well, we can look at how fast sodium goes into into these cells. See, the sodium that's in there, it's a steady state. The measurement that we're making is a steady state. Yeah? So that's a reflection of the rate at which sodium is going in and the rate at which sodium is being kicked out. So it could be either that the influx is very different or the efflux is very different. Which is it? So we were not able to measure the efflux directly. So what we did was we blocked the efflux so that neither cell is pumping out sodium, but we then looked at how fast sodium was leaking in. And what you can see here is that these are Jaya, and you can see sodium rushes in very fast. Within about 10 minutes, it's all in. Yeah? Whereas in Pokali, it takes well over an hour. It's of the order of 2 hours to get in. So it's almost an order of magnitude difference in the permeability to sodium between Jaya and Pokali. So can we try and tease out what underlies this difference? Yeah. So the thing is that we know it's something which is leaking in, right? Sodium is charged. It can't go across the lipid bilayer. No way. Okay? So there must be some transporter through which the sodium is coming into the cytosol. And there have been a number of suggestions in the literature as to what the identity of this or these transporters are. And what we did was we tested them one by one. Yeah? And it turns out that every candidate transporter is present in both Pokali and in Jaya. So we don't know. Yeah. It's present. Okay. The other possibility is that it's present, but it behaves differently. Yeah? So for instance, what is all these candidate transporters, there's no transporters across the plasma membrane which are selective for sodium. They're all supposed to be for potassium, because plants like to take up potassium. But their selectivity is not great. Okay, the animal potassium channels are much more selective than the plant potassium transporters. So you could ask, are the transporters for potassium not so selective in Jaya and much more selective in Pokali? That's a possibility. We were not able to test that, unfortunately. But in Puerto Rico, the rice that I showed you where there's salt glands made and it drops off. And I also told you that people in the Swaminathan Foundation are working on that. We collaborated with them for a bit, but we couldn't get too far with it. And after I retired, they collaborated with a group in France, and they were able to show that the major transporter in Puerto Rico has characteristics that are different from those on the IR20. Not hugely different, but a little different. Is that enough? I don't know. That is a paper which should be coming out fairly shortly. Okay, I showed you an image of drought, right? So that's a major problem, and we don't have a wild type cultivated variety of rice which is highly drought tolerant, unfortunately. But Professor Shashidhar in US in Bangalore has bred a variety of rice which he calls aerobic rice. And it's titled BI33. There's a couple of different names for it. And he calls it aerobic rice because rice is very water intensive. Okay, it takes you 5,000 liters of water for a 1 kilo yield of grain. Okay? That's not sustainable over when you've got serious water problems. And there's no transplantation required. And in his test plots, he's got wheat, rows of rice, and so forth. Watered exactly the same. So that's good. And you get good yield and taste comparable. So that's it. So there's this variety which does well under drought, and northern Karnataka is highly drought prone. The variety has been released there, it's doing very well. So that's a success story on that. The problem is that plant breeders select for a phenotype that they're interested in. And so the phenotype he was interested in was being able to grow with very little water in the soil. How it works is a different problem. So what we tried to do was to ask as to whether the mechanisms that were used by BI33, what are those mechanisms? And are they different from the ones that Pukali uses to survive in salt? You might imagine that there would be orthogonal, completely different sets of adaptations which are made in these two cases. So we did the experiment. We just took both Pukali, BI33, IR20 and Jaya, grew them in salt, and what you can see is that BI33 doesn't do too badly in salt. And when we did the same experiment with a drought stress, Pukali doesn't do too badly in drought. So there's some similarities. They're both not too bad, and show you the data. So here's salt. What we're looking at is photosynthetic efficiency. That's important as to how much sunlight they can utilize. And that's under salt. And you can see that the aerobic doesn't do great under salt, but it doesn't do as badly as the high-yielding variety. Yeah? And similarly, under drought, Pukali doesn't do as well as the aerobic variety, but it does a whole lot better than the high-yielding varieties. So we asked, what are the differences out here? And and remember, what you're doing is, we want fluid to be taken up. Now, if there is no water in the upper layers, because the soil dries out from the top layer, you can go further down, there might be water there. So what these plants do is that they make very long roots. Yeah? So they go very deep into the soil, and they're basically looking for water deeper down. And hopefully they find it. Yeah? So the other thing that they need to do is that in order to be able to take up the fluid from the medium, if the medium is highly concentrated in all of this stuff, yeah, then the osmotic gradient will be from in to out, and water will go out. So the driving force should be reversed, which means that you want to put in osmolytes into just small molecules, proline, bunch of other things, yeah, which can be put in here. And what you can see is that both these guys do pump in their roots, a lot of osmolytes into their roots, and because of that, they do relatively well. Now there is a an issue here. If you're going to take roots that go very deep into the soil, once you get more than a meter deep into the soil, you're reaching areas of soil which have got relatively low oxygen. It's not quite hypoxic, but it's lower oxygen than at upper regions. So you need to make some provision for you to get oxygen from the surface down into the roots. So what these plants do is that in the roots, that's Pokali without any stress, Jaya also, IR20, but as you apply stress, this is 100 millimolar sodium chloride, what you see is there's a lot of these cells die off. Yeah? So they make a passage down which air can go down. That's very good. You get air to go down, and it gets air down to the root tip, and those cells then are happy, survive well. Yeah? But there's a problem. Yeah? Because you've got a tube, your root is a tube, yeah? And you're pumping air down this tube, and it's porous. Right? So the oxygen will leak out. Not much of it will reach all the way down into the root tip. So what these plants have done is that in addition, so just the same sort of waxy barrier, they deposited those barriers on the outside of the roots. So now oxygen can't diffuse out of the root. It isn't lost to the soil, but it does get down as far as you need to go. So this is where we don't necessarily go into this. This is just a summary of all of what I have shown you so far. But the essence of it is, what are the adaptations that are made? So in the case of sodium leak, this is coming from the Pokali work, you reduce sodium leak into the xylem by making these barriers, these waxy barriers. And the better the waxy barriers are, the less sodium goes up into the shoot. And so you are protecting the shoot from the toxic sodium going up. But if the cells are in fact nonetheless exposed to sodium, remember the root cells are all exposed to high sodium. They're exposed to the soil, and you want them to take up nutrients, the goodies from the thing. So you don't want to block them off by making waxy barriers on the outside. Yeah? So then what you're doing is you're reducing sodium leak into the cytosol by reducing sodium permeability of the plasma membrane. We don't know how they do it, but it's clear that they do. We have data not only from looking at sodium directly in the cytosol, but we've measured potentials by sticking in electrodes, which are again, which you can interpret in terms of sodium permeability. And again, that's gives data which is comparable to 1 order of magnitude difference in sodium permeability in the two. Yeah. For drought, the idea is that you make long roots which go in deep and look for water. In some cases, the roots spread out and look for water in the neighborhood. Most cases it goes straight down. And part of that we think, or a lot of that we think, is because we do these in containers, which are cylinders. Okay, so they can't spread out. But if you do plant them in, you find that they also spread out. Okay. And in order for you to get long roots, you need to have oxygen going down. So you make these Ehrenkeime, yeah? And that allows you to send oxygen, and you make a waxy barrier out there to prevent loss of oxygen to the soil. And finally, you make osmotic. You make osmolytes, or you accumulate osmolytes from the soil. There's plenty of osmolytes in the soil as well. Yeah? Glycine betaine is sometimes present out there. Yeah? And you pump them into the roots so that the roots are able to take up fluid, even when that fluid is highly concentrated. Yeah? So that's that's the story. Yeah. I've left out all of the details. Okay. But that's the story in large part. And it's the work of many, many people. So these are the folks. Veena is the person who's done, she was a postdoc in my lab, and she's now a professor in the University of Agricultural Sciences. The others have gone on, they're all doing postdocs or independent faculty positions in various places. I've been fortunate to have students from the University of Agricultural Sciences work in my lab towards master's or PhD, as the case might be. These are all students who've got degrees by working in my lab. Collaborators, Utpal in IISc, Jitu Mayer in NCBS, Lucas Schreiber. All the waxy barrier work was done in Schreiber's lab in Bonn. And Kalika Prasad and IISER Trivandrum. Abdul Karim was the student involved. None of this work could have been done without the assistance, it's really the assistance and mentoring of faculty and students at the University of Agricultural Sciences. I have to admit that I have never taken a biology course in my life. Yeah? Not in school, not in college, never. And what little I have read, I have utilized. At the time we started this, I hadn't read anything in botany. Yeah? So plants were completely new to me. These folks taught me and helped me and my lab to set up, to do these experiments. I didn't really talk about the work which was done at the University of Tokyo. And there were images, all those 2 photon microscopic images. I just showed you one image, but I showed you. Yeah, that was done in the Central Imaging and Flow Facility at NCBS. Thank you, and questions?
Questions?
Why is Pokali cultivated considered organic by default?
Pardon?
Why is Pokali cultivated considered organic by default?
Well, I don't know if it is necessarily organic. The Pokali cultivated in the Pokali region in Kerala is organic, but you can grow it anywhere else and you can add fertilizer and pesticides and so forth. It's just that in that region they grow it organically.
Yeah, okay. Can you pass?
Thank you, sir, for the talk. So, most genetically modified plants, I think they've reported to have high intake of water for high yielding varieties. So, if you are conditioning those plants in higher salt concentrations, they grow more waxy barriers. Does that, I think there's a less intake of, does that affect the intake of water and the yielding, the yield of rice from that plant?
So these are actually 2 completely different properties. So what you're talking about is water use efficiency. Okay, so how much water do you need to take up in order for the plant to grow and to make grain and set it up? Okay? That is not necessarily related to its ability to survive in high salt. We haven't looked at water use efficiency.
Sir, actually I wanted to ask, the salt airs you talk about, is it acting just like the hydrothodes?
Similar, essentially, yeah.
Does rice plants have hydrothodes?
Not these guys, no.
Okay.
Great talk, sir. I don't have a question relevant to the biology. I just was wondering, are the graphs usually this nice? Like,
what do you mean?
So in all the graphs that you showed, the curves could be, I guess, extrapolated pretty easily. Like the data was following a really nice trend. from my limited experimental background, whenever I do physics experiments, I can never seem to get a straight line or any of the patterns that I'm supposed to get. Your experience, are the graphs in biology usually this nice?
No.
Okay.
No. It so turns out that in that particular set of experiments, it's not just that, I mean, linear plot is very easy to extrapolate. There's no, as to whether it will remain linear in the region which you are extrapolating to, we have no information. Is it valid to make a linear extrapolation at that point? Yeah, we don't know. That's why I said I don't recommend doing that extrapolation. In the other case, it was a curve. I haven't fitted it to any function. That curve was drawn by eye. Draw it by eye. You can pass it through, as long as it's a smooth distribution, you can always pass a nice straight curve through points, even if it looks like an elephant. Oh, they're noisy. You saw the you saw the error bars. The error bars are pretty substantial, but the error bars are much smaller in those graphs because this is 3 years of data. Yeah, so there's many experimental points which have been averaged into many experiments which have gone into each of those points.
Does this sodium and potassium ion, can we compare with sodium and potassium ion channel in human body, their functioning? In a sense that...
so the sodium, there are no sodium channels in plants.
No channel. I mean process.
There are potassium channels in plants which have a structure based on sequence that is reasonably similar, which is probably almost identical, possibly, to voltage-gated potassium channels
Yes.
in animals, in mammals. But we haven't done those experiments. The structure has not been determined. We have done electrophysiology on them, and there's something fishy about them. Okay. So there are potassium channels in mammals which are called delayed rectifiers. They're called rectifiers because at the range where these channels are open, they are voltage dependent. Okay? So at minus 80 millivolts, they're closed. At 0 millivolts, they're open. And over the range where they are open, the direction of potassium flow is outward. So they're called rectifiers. But if you change the concentration of potassium outwards, outside, under the same voltage regime, potassium will flow in. A plant rectifier, it's called a rectifier because it's got the same sequence homology. Yeah, so it's because it's a sequence homologue, we call it a rectifier channel there, potassium. There, the voltage range over which it opens shifts if you change the outside potassium concentration, so that it is always outside. Yeah? Now, how it does that, we haven't figured it out as yet.
Okay.
So there are things broadly similar, behave differently.
Just wanted to ask, this suberization of roots in deep soil, without a similar thing happening in the topsoil, can it lead to hydraulic redistribution? Water being taken up from the deep soil and distributed out into the topsoil. Trees are supposed to do it.
I don't know actually, but what we have observed is that the waxy barrier is there all the way through. It's not that the top is unsuberized.
Okay, thank you.
Okay, so thank you so much, and I'll request Professor Indulekha to hand over a small memento to Professor Matthews.
have Professor Shubhabrado Bhattacharya from ICTS TIFR Bengaluru. He works on condensed matter physics, strongly interacting systems. So he started out on his science career from Presidency College, on to IISc, then to the Americas, the continent, the European continent. So he has got all the collected knowledge and experience of science from all these places. Professor Shubhabrado Bhattacharya.
Okay, so let me start by thanking the organizers, and I'm really very happy to be here talking to all of you. And I'll be trying to tell you a story which might sound somewhat disconnected to things that we have heard since today morning, but is actually part of the same problem. A different aspect of what I'll point out is the many-body problem. So, so the connection that I'll try to start off with, which you would immediately connect to, is your smartphones that all of you, I guess, carry with you. And as I was discussing with some of you over lunch, the question that you might want to start by asking yourself is that the smartphone that you're carrying is made out of many different things. Okay, the processor is made out of some material, the screen is made out of some other material, and things like that. So the question that you can ask is that why was a particular material chosen for to make the screen and a different material to make the processor and things like that. Okay, so we will try to ask how does one go about doing things, and what is the physics that is involved in trying to decide ultimately in a factory what materials should we use to assemble a particular part of a smartphone. And we will see that this is actually the physics that is related to it is actually one of the central organizing principles of the nature, and we'll try to understand some bits of it and go beyond that. Okay, so this is what I'll say quantum phases of matter, and I'll try to tell you a bit more about that in the next half an hour or so. But please stop me at any point you have a question. I fortunately don't have a syllabus to complete. Okay, so the question that I'll keep on harping on is, what are quantum phases of matter? Okay, so let's get things that we are somewhat familiar with out of the way. Start with the idea of phases of matter, and this is something that we keep on learning from high school, etc. The canonical example being various phases of H2O molecules. So the two well-known phases are ice and water. This is a solid phase, this is a fluid phase, and the thing that we must realize is that both these are made out of the same H2O molecules. Each molecule contains one oxygen and two hydrogen, which has a certain shape, and even though they are made out of the same assembly of these molecules, they have very distinct properties which cannot be attributed to any of the participating members of the assembly. It's a property, the property of ice is a property of the entire collection of these molecules, and the same goes for water. So if I take out one molecule of water from ice or the fluid, the water, I won't be able to find out the difference very well. The properties are, in the sense, attributed to the entire assembly. Okay? So these kind of properties which are really properties of things being put together, and it's not a property of independent members that make up that assembly, are called emergent phenomena. Okay? And all kinds of things around us are manifestations of various kinds of emergent phenomena. We heard various talks for biological systems, etc., and the cosmological systems, various structures across the universe. So all these are basically examples of many things put together, and they build up various kinds of evolving structures which can be characterized under various kinds of emergent phenomena that we would like to study. So they are all over, all around us at various scales. Okay? So another example which you may or may not have heard, but I find it very striking, is this tip of pencil which is made out of graphite, which is really layers of carbon, and when you write with that pencil, these layers stick to the paper, and that's how they make a mark on the paper, and that's how we call, that's what we refer to as writing, and that's what we do. So these are sheets of carbon, but the same carbon atoms can be assembled in a very different way to form diamond, okay? Which has, I don't have to tell you that the lead of the pencil, the property of that is very different from that of diamond, but it's the same carbon atoms, okay? Just assembled in a very different way. So this is another example of a striking example of emergent property, and here again the property cannot be attributed to individual carbon atoms, but to the entire assembly, whether the assembly makes up these graphites or diamonds. Okay? So this people have appreciated this over a very long time, but it was put together in a very nice form in this very persuasive article in early 70s. 70s was a very important period for various areas of science, as we learned also in the morning in context of biology. All the genetic things were, the outlooks were put together in a nice form. So it's the same decade. That's how science, I guess, progresses. We have many things coming together, and there is a big progress. So Phil Anderson, who put together this fact that these emergent properties are really properties of assembly, provocatively pointed out that more is different, in the sense that if you put few things together, make many constituents and put them together, and the property of the entire assembly is very different from individual members or that make up that assembly. And so, and phases of matter is one particular manifestation of this emergent phenomena when you put together many things like carbon atoms or water molecules, and you get various phases. Okay? So this is what is one manifestation of emergent phenomena that we would like to study. Okay? So the question is, where should we start? It sounds like it's an impossible task. We have like 100-odd elements, and we can put like zillions of combinations together, and it looks like that it's a hopeless task to figure out what happens. Okay? So we have to look for underlying organizing principles, which we can then apply to different settings. Okay? So let's try to ask, what are the organizing principles in trying to understand what kind of emergent phenomena can arise. Okay? That itself is a daunting task, but that seems to be a problem that we can try to address, or try to even understand the meaning of the question and hopefully make some progress. Okay? So this is a part of what is called the many-body problem, and it essentially means that you just put together many constituents and try to, and they are interacting, and you try to understand their properties. Okay? So let's first ask, what does it mean to specify the many-body problem? Okay? So in other words, what are the ingredients of the many-body problem? There are, again, many ways of saying the same thing, but essentially you have to say three things, okay? Give or take. First, of course, you have to say what makes up that many-body. What are the constituent members, water molecules, carbon atoms, etc. So the constituent degrees of freedom, okay? So that's almost obvious, and so then what one has to basically say that given these degrees of freedoms, what are the constituent structures of the microscopic laws that govern these degrees of freedom? You know, Newton's laws, quantum mechanics, whatnot. So you have to say what are the generic structures of those laws, and those go under the name of symmetries, which I'll briefly discuss in a moment. Okay? And finally, you have to say that given those rough structures of the microscopic laws, how are these degrees of freedom actually interacting with each other? So if I say these three things, or if anyone says these things, one has basically specified what many-body problem one is dealing with. Okay? So let's start with degrees of freedom, and this can be as varied as this picture suggests. It can start with clusters of galaxies, etc., and one may want to study their dynamics, as we heard in the talk in the morning. One can be interested in dynamics of flocks of birds, etc., or DNA, or some particle soup that one is interested in. Okay? So all these are valid examples of many-body problems, and for each of these, I can write down the second and the third step and try to understand the collective behavior. Okay? So the common thing is that there are many constituents. So what I'll try to tell you about this talk is about a particular set of things, which is somewhat related to Sangyukta's talk in the morning, is about materials where we put together elements of different kinds. Okay? So in other words, we'll be interested in trying to understand emergent phenomena in materials. So henceforth, my degree of freedom would be elements that live on the periodic table and electrons and ions of various kinds. Okay? Questions? Okay. So given that degree, given that I have those degrees of freedom, let's try to focus on the second step, which is like the generic structure of the microscopic laws, which goes under the heading of symmetries. So you see that one of the things that we learn in high school, the Coulomb's law, if you take two charges, the charge Q1 and Q2 separated by a distance r, they feel a force which is Q1, Q2 by r square into r hat. R hat being the vector along the line separating the charges. Okay? So it has some particular value. You can put Q1, Q2, and r square, and you get some form. But what you see is that it always points along this vector and is only proportional, only depends upon the distance between two charges. It does not matter where these two charges are. In this the part of the room or that part of the room, as long as the distance, the vector distance remains same, the force is same. Okay? So I'll say the same thing in a more structured way. I'll say that the force is invariant under translation. If I take two charges here and I translate both of them rigidly to this point, there the force does not change. Okay? So the force is invariant, or the force is symmetric under translation. So I translate the two charges rigidly, the force does not change between them. Okay? So microscopic laws of nature are filled with such generic structures that they're invariant under certain transformations, and those transformations are called symmetry transformations. And in this case, the example being a continuous translation symmetry. I can translate by arbitrary amounts as long as I translate them by rigidly, and this force does not change. Okay? And one can give more systematic mathematical structures to such transformations, and one arrives at the concept of a symmetric group, which is essentially the whole list of such transformations that keep these structures invariant. Okay? So in spite of the fact that whether it's proportional to Q1, Q2, or twice Q1 into twice Q2, this structure is more rigid than the form itself of this force. Okay? Okay. So that's the second important structure, and finally, the final the step is actually trying to say how the particles that I put together interact with each other, and it might look very complicated. The exact form is not very important. You say you either write down the force equations, Newton's laws, or if you want to do quantum mechanics, you write down some Hamiltonian, which is the quantum analog of the same thing, and you basically say that if I have 2 particles or 5 particles or 10 to the power 23 particles, all of them interact in this form, and the first term is the kinetic energy and the second term is the potential energy, and this is it. Okay? Okay. So the main point is that whatever the system evolving under this force law or Hamiltonian, the dynamics treats the configurations which are symmetry-wise related equivalently. This is very important because the dynamics does not distinguish between 2 configurations which are symmetry-wise related, and this is the reason why all the molecules in this room do not cluster to one point, because on an average it remains uniform, because all these configurations are related by symmetry, and it typically chooses configurations, it typically treats configurations which are related by symmetry, and unless I do something special, which I'll come to in a moment, all the air molecules remain uniformly spread out through this room. Okay? So I've now given you a recipe which goes under the name of, in research parlance, it goes under the name of a Landau recipe after the Soviet physicist Lev Landau, who basically emphasized that these are the things that one needs to specify. But now one can go ahead and study these systems. Okay? Good. So let's try to do that. Okay? So the next question that we must now say that, okay, I have a specification of my many-body system in the sense that I have said the ingredients. How do I now progress? Okay? And remember, the goal is not to go and look for one particular material and find out everything about it so that I don't know anything about the next material. So the goal is not to go material by material, but to understand the generic organizing principles. Okay? Okay. So the generic organizing principles comes from laws of thermodynamics, which says that if I take such a system and cool it down, I mean, Shamgupta said fantastic things of the cooling down the mechanisms and technology. So suppose I try to cool the system down to very low temperatures. Okay? So irrespective of what the system is made out of, thermodynamics says that it must decrease entropy. Okay? So then the question is that all the organizing principles that I must have must follow the same basic structure to be in accordance with thermodynamics, that they all must allow decreasing entropy as you go to lower temperatures. Okay? So what happens is that a fluid which is disorderly, okay, has a higher entropy, and as you cool down the system, the entropy is released by ordering. Okay? But you see that if I do that, if for the fluid, if I average over all the configurations, say I think about, pick out one of these molecules and look at its trajectory, it's going to be all over the room, okay? So if I average over the trajectory, it would fill up the entire volume, okay? But if I take a crystalline solid, okay, take one of these atoms, okay? If I keep on averaging it, looking at it, it would roughly remain at the same position and it would never fill up the room, okay? So the averaged out positions of a fluid covers the entire volume, or if I average over, it would be like a constant density, okay? And on the other hand, if I look at the density of the atoms here, it would be no atom, blip, no atom, blip, okay? So it is not uniform. So what has happened is that in the process of decreasing entropy, what I have done is that I've gone from a translation symmetry invariant state to a translation symmetry broken state, where the density of the fluid used to be uniform, but once it became a solid, it is no longer uniform. So this basically happens that the system decides to get rid of entropy by breaking the symmetry that the underlying microscopic laws had spontaneously, okay? So this was one of the central organizing principles that was discovered by several people, including Lev Landau, and this goes under the name of spontaneous symmetry breaking, and all the things that we are familiar with, crystals, magnets, etc., we can understand it using this principle, okay? So one can go and ask various things and try to understand what is the particular symmetry that's broken, and we will get an answer. And this is a very well-developed field. In fact, all the kinds of things that we use stems back to these idea of spontaneous symmetry breaking. Okay? Yes. Huh? Yeah, so there is, the liquids and gases are not really different phases of matter, okay? So they are same phase of matter, it's just the density can continuously change, okay? Yeah. Okay, but here is the twist, okay? So these electrons and ions, the electrons that make up a magnet or the ions that make up a crystal, okay? They are quantum mechanical objects. Okay? So what really do these cartoon pictures mean? Okay? Is it just like a meaningless cartoon that one is drawing? Or what physics sense do they convey? Okay? As we saw that the cartoon picture of the crystal is really conveying this broken symmetry that the density is not uniform. Similarly, what the magnet is, this picture of a magnet is saying that on an average, all the spins of this electron are pointing in the same direction. So they have some physics associated with them, but what really is the essence of this picture, and why do this picture make any sense at all? Okay? So let's try to understand this, and in the process we will discover a very important organizing principle that has been of late much attracting a lot of attention. Okay? So let's take a step back. Let's try to understand what is classical and what is quantum in like 2 minutes. Okay? And then we can discuss this after the talk. Okay? So the classical description, suppose you have like zillions of classical particles. So for one classical particle, what you want to do is specify its velocity, that's momentum, and its position at any time, and then solve Newton's laws to track the particle's position and momentum at a later time. Okay? So if you have two particles, you specify the position and momentum of the first particle, position of momentum at the second particle at a time t, and then solve Newton's laws to get it at some later time. If you have 10 to the power 23 particles, you might be very hard pressed to solve this, but you can carry out this exercise in principle. Okay? What it really means is that out of this humongous list of 10 to the power 23 positions and 10 to the power 23 momenta, you can always single out, even though the particles are identical, you can always single out your favorite particle, which shall say the first particle, okay, and try to follow it in the background of all the rest of the particles, okay? So this is, in a sense, you can always locally describe the system in spite of all the other things that might be present, okay? So this locality of description is intrinsic to classical mechanics, okay, in this particular form. Whereas in a quantum mechanics, one is not dealing with positions and momenta in the same way as classical mechanics, but one is dealing with wave functions. So you solve some wave equation like the wave equation for water or something, but and then you calculate the position or momenta by solving some integral like this. So this is a complex number which obeys superposition principle. This is the wave function, and once one has the wave function, one calculates some integral or the expectation values of dynamical variables, and that's how quantum mechanics goes, okay? So again, one can discuss this in great detail, and but this description then plays an inherent limitations on how closely you can follow individual observables, okay? That goes under the name of uncertainty principle, and that provides an inherent limitations on the sharpness of quantum description, and this is very different from classical mechanics, okay? So that's already at one particle level, but this really becomes very acute when I have many degrees of freedom. So when I have many quantum particles, unlike the classical list of momenta and position, here I still have a single wave function, which is now a function of all the position of the particles and time like this, okay? And this wave function is not a product of the description of the first particle, say, by this first function, the second particle, the third particle, and so on and so forth. So this generic function is not a product of individual functions, each of which describes one particle at a time, okay? So this is the major barrier, and this is why, in the sense that I introduced local description, quantum descriptions are non-local, okay? And one can make this more precise by asking how non-local a particular quantum description is in the sense of the locality of descriptions that are introduced in context of classical mechanics, okay? So one can quantify this, and this quantification of the measure of quantumness, which is this sense of non-locality that I just introduced, has a name, a quantum entanglement, okay? There are more precise ways of doing this, but roughly one wants to quantify how non-local, how non-product-like are these wave functions. So the product-like wave function would be like the wave function for the first particle, the wave function for the second particle, and so on and so forth. So generic deviations from this product-like description is a measure of quantumness that one can try to quantify. Okay? Good. So one can go into descriptions. I won't go into this, but one can really take various kinds of quantum states and try to describe things. Okay? So for example, if I have a big box of particles, okay, I have if this was a classical particle, as I said, that I can choose one particle and choose to follow it. So it has this local description. But if I have a quantum system where I cannot follow a particular particle, the best I can do is that I can divide that system into different parts, for example, two different parts, A and B, and ask that how does the description of A and B are related in this non-product sense. So I'll write down the description of A, I'll write down the description of B, or in other words, a wave function for part A, wave function for part B. But if I write down the wave function for the entire system, I would take the entire wave function minus the two product wave function, and if it was a classical description, roughly that difference would be 0. But as this difference grows or becomes more and more non-zero, my system would naively behave more quantum mechanically. Okay? So there are ways to do this, which we can discuss after the talk, but this is what is one way to measure quantumness of a system. Okay? So what happens is that the crystals and magnets that we discussed are really almost product-like states. Okay? Or in these cases, the difference from a product state is really very small, and in essence, what one is describing is a product-like wave function for crystals and magnets, which is why these classical pictures make sense. Okay? This realization is at the heart of the humongous progress that has been made in material sciences on the basis of this spontaneous symmetry breaking that goes under the name of Landau-Ginzburg-Wilson paradigm, which I guess you would learn at masters and things like that in a physics course. This is one of the central paradigms that one repeatedly applies and uses to make all kinds of things, materials, etc. And this essentially works because the kind of wave functions that one is dealing with are almost product wave functions. Okay? So all the kinds of things, the magnetic memory, the processors, the MRI machines, which uses a superconductor, etc., are basically given by wave functions of this humongous quantum mechanical system, which are almost product-like. That's why we can get away by drawing cartoon pictures of the kind that I was doing and still be able to describe the physics, essential physics. Okay? Good. So that tells us, sets up the question that is it all that our nature around us has to offer? Okay? So in a way, what this way of releasing entropy by producing almost product ground state gives us some classical states, even though the underlying degrees of freedom are more quantum mechanical. Okay? So then the question that we can ask is, are there other more quantum ways that humankind have since discovered? Okay? And the answer seems to be yes, that we have a new set of phases which we don't completely understand right now as I speak, but this is where we would like to develop our understanding to create a generic framework of these things. Okay? So the quantum way of doing the same thing. Remember, we always have to be, we always have to obey the thermodynamics, so we always have to get rid of thermal entropy. Okay? So one way of getting rid of the thermal entropy that we just discussed is breaking symmetry in the sense of going from fluid to solid, crystalline solid. But it turns out that there is another way of increasing, decreasing entropy, which is increasing entanglement, okay? Which is increasing non-quantum, the non-classicalness, or making the system, keeping the system quantum. So choose one wave function which is not a product wave function, and that way we get rid of the thermal entropy. Okay? So these, when we do that, essentially we get states which are not product-like states, okay? And these are what have been dubbed recently as quantum phases of matter, in the sense that even though the magnets are also quantum in the sense that individual electrons are quantum mechanical, they require quantum mechanical descriptions. But in the high school, when we draw the field lines of a bar magnet or the bar magnet itself, we just draw lines to denote the quantum spin, which is an inherently classical object. That's all that was good because of this. Okay? But now, the quantumness survives to the macroscopic level. So I cannot draw simple pictures like this. I have to be careful in doing those things. And these have been dubbed as, wherever this happens, these systems have been dubbed as quantum phases of matter, as opposed to quote unquote classical phases of this kind. Okay? So now one needs to characterize things not in terms of symmetry breaking, but by trying to understand the quantumness or the non-classicalness or this property of entanglement which captures the non-classicalness. Okay? And this is the new organizing principle that has been discovered over the last 30 years, and it's one of the frontiers that is seeing a major development across disciplines of physics, traditional corners of physics, from quantum field theory to various branches of mathematics and statistical mechanics. The idea is to find an answer to the question, how can I characterize patterns of quantum entanglement, okay, or this non-classicalness, okay? So there are many examples, including the most famous example being fractional quantum Hall effect, which was discovered in 80s. And these things are, we don't have, so you see that I don't have pictures for this. So I won't go into generic discussions of what these phases are. Anyway, we don't know the complete picture. But I'll tell you in the next 5 minutes or so, what are the startling outcomes of once you start thinking about phases which has lots of entanglement, okay? And that's where I'll stop. Okay, good. So for this, I'll devise an experiment which is a real experiment in the sense that we do this almost every day. Okay? So it is taking a system and trying to add an electron to it. Okay? This is the experiment that we perform whenever we switch on a light or something. Okay? We start a current. Okay? People who have done Ohm's law experiment in undergrad labs have done a canonical version of this, but no, this is not a major. Okay? The only caveat is that the current that the switch, when I close the switch, the current that I want to drive is a very small current because I want to put one electron. Okay? So apart from this, it's the same thing that we do when we switch on light or something. Okay? So this is the kind of experiment that and these are the kind of experiments that are repeatedly done. You're familiar with the Institute of Science, which is down this road. There are very fantastic labs where these kind of experiments are done for different materials. Okay? So this is not something that I am cooking up from my figment of imagination. Okay? Good. So let's first do this most simple thing. Okay? Take empty space and try to put an electron in it. Okay? So, one can solve this problem quantum mechanically, and what one gets is that the energy of this electron in this empty space, empty space is some zero material. Okay? So it has energy. Okay? So if I change its momentum, okay, that's P, this is the mass of an electron, I'll get some energy, so for P equal to 0, say this energy, P equal to 0.1, this is an infinite set of energy levels here, continuous. Okay? So that's the thought experiment. Okay? So this, I guess, is fine. Okay? Let's now try to put an electron in a magnet. Okay? So I take an electron, I have this magnet, I just slowly put it inside the magnet. Okay? So this is what I like to do, and what it does is that once I try to do that, the electron immediately goes and feels the neighborhood of the magnet and aligns its spin along the neighborhood. Okay? So suppose it goes and sits there, and this neighborhood, all the electrons are sitting with their spin up. It goes and sits with it there with its spin up. Okay? It's not important that it sits with spin up, but you see that while adjusting itself to its surroundings, it retains its identity in this very important way, that its spin still remains half, okay? And its charge still remains E, which is like this 1.6 Coulomb 10 to the power minus 19, whatever that number is in SI units. So you can go and measure this, okay? So this is because the underlying wave function that describes a magnet is almost a product wave function, almost classical, okay? So the electron goes and sits as if you are just adding one more entry here, okay? Up or down, whatever, okay? So since it retains its identity, okay, you can also pull out that electron fairly easily. Okay, 2 or 3 minutes, I'm almost done, okay? So you can pull out that electron almost without any problem, because it was locally sitting there, retaining its entity, and you can just pull it out without much problem, okay? That's like taking the current out, the wire that leaves your bulb or something. The same thing, try to put an electron in a crystal, okay? So once you try to do that, contrary to putting it in empty space, now what happens is that because of the crystal, the energies are not really continuous, but they divide up into some set of energy levels, then there is a gap, then there is some set of energy levels. These are called bands, okay? And it's a basic example. Now, once you put in this electron, okay, you, depending upon the material, etc., there are other electrons in the material. They can occupy all these energy levels, and electrons being fermions, they cannot go and sit into that same level. So this extra electron can either go and sit here, or here. In some material it would go and sit here, and in some other material it would go and sit here, depending upon what other electrons are doing. But so if it goes and sits here, if you try to put more current, it cannot move, because there is an energy gap, and it behaves like an electric insulator. And this, I'm going fast, I can explain this in more detail after the talk. But if it sits here, it can access these states very easily, which are close by, and it behaves as a metal, okay? But you see that whatever may be the case, the wave functions are really product-like, because there were more electrons wherever, and this extra electron goes and sits either here or here, so which is like adding one more part, okay? So it's, and similarly, you can take out that electron, since it's almost product-like, you can take out that extra piece, and this is why the current works so well. In fact, the wires that we choose, the copper or the silver wires, we choose in such a way that the wave function is as product-like as possible, so that I can put in the electron as easily and I can take it out as easily, okay? This is one of the considerations that goes in, okay? Good. But now, let's try to think about putting it in one of these entangled things, okay? One particular example of this entangled quantum phase, the most well-known, is what is called a quantum Hall system, where you take some material, in particular gallium arsenide, and then another material, which is aluminum gallium arsenide, and stick them together, and at the junction, you get a bunch of electrons, and you put a magnetic field perpendicular to it. Okay, so you have electrons, and they are stuck to this level, so they are very strongly interacting. So this is one of the things that people found out is where this entangled phase is realized. So when it is realized, so I put in an electron in this. I had a wave function which was not a product wave function. So this extra electron goes, and this is the wave function which is not of this form. Okay? So the electron does not just gets added to the system trivially. As soon as this happens, the electron no longer needs to retain its identity, okay? Or its quantum numbers are no longer bound to remain as that of an individual electron. And in this case, what happens is that the charge of the electron fractionalizes in rational integers, okay? So rational fractions, okay? So the charge of the electron gets, the single electron sort of splinters into n charges, each of which carries 1/n of the electron charge. More weird things can happen because these depends upon the particular non-classicalness of these states, okay? But this is what happens. And once this happens, if you now measure the resistance of this system, okay? So forget about this. This is a very famous experimental result. You would see that if you look at the resistivity, okay? So this is resistivity as a function of magnetic field that you have turned on. There are certain places that this resistivity goes to 0, okay? So these resistivity goes to 0 in these places at integers, okay? 2, 3, 4, okay, of the magnetic field. But then there are places where this resistivity goes to 0 at these fractions, 3/5, 2/3, okay? There is, this is 1, okay? So all these things, 2/5 here, okay? This is that splintering of electron, okay? So one can go and understand the physics, and if one tries to explain the experiments of this kind, okay, and tries to understand why does this thing goes to 0 at these particular values of this magnetic field, okay, the only way to explain is this, that the wave function that describes this whole system of electrons is so entangled that when you put in an electron, it is not like adding trivially an electron like in this case, okay? The electron just mixes with all other electrons at the same time and loses its identity, and once it loses its identity, its quantum numbers can change in a very particular way that's dictated by the entanglement of the system, okay? And this is the kind of physics that people are trying to understand for various reasons. A, the manifestation of quantum mechanics in a macroscopic setting. B, whether these classes of things are interesting in their own rights. And it seems that there is a whole class of technology that can be built, some of which are, there are proofs of principle, and people are working on it actively to convert it into more usable form, okay? But at the heart of it is the second organizing principle, just like the broken symmetry drives all the technology that we use right now, okay? This is the organizing principle that one needs to find more about and then try to find out whether they can be of any use. So all these questions remain open and from various points of views, and seems to be something that constitutes one of the major problems of our times. Okay. With that, I'll stop. Thank you.
Yeah. Questions? To ask? Yeah.
Hello, sir. Great talk. This is related to the first half of the talk when you introduced this. In a many-body system, there is the symmetry group associated. So my first question was, can you give some interesting examples for when this group is finite? And the second question is, does the study of finite groups in any way come into the physics here?
Yeah, absolutely. So, for example, you can ask that I showed you one crystal pattern, which is basically the crystal of salt, common salt. Okay, you can ask the following mathematical question: how many periodic patterns that you can make in any dimension d? Okay, so that's like classifying the group, the point group symmetries and the space groups, and the number in 3 dimension is exactly 230. Okay. So this has been classified for a long time. Now, that's a very important piece of mathematics. An equally important and interesting piece of physics is that all these 230 types are realized in nature. Okay?
Thank you.
More questions?
So very interesting talk. Now, this fractional quantum Hall effect is two-dimensionality because the layer between gallium arsenide and the other layer is two-dimensionality important? Can it fractionalize in 3 dimension?
It can fractionalize in 2 dimension, but not of this kind. Okay? So there are other examples called quantum spin liquids which show fractionalization even in 3 dimensions.
The reason I asked, I mean, this is we know that ITC superconductors,
yeah.
Mostly the 2-dimensionality is important.
Yeah.
The 3rd dimension, the hopping is difficult.
Yeah.
So could it be that the quasi-charged particles have fractionalized charges so that
Absolutely.
the electrostatic repulsion is lower, so it is easy to form Cooper pairs?
Yeah, so the theories like this have been proposed over the ages, over the last 30 years. Again, I showed Phil Anderson's picture. He was one of the people who suggested these kind of things. It's not clear that we have the experiments agreeing with all the fallouts of this theory. So parts of it agree, but we don't have a consensus experimentally whether, so for example, things like the fact that it is driven by magnetic fluctuations, etc., that would fall out in case of ITC goes through. But there are other fallouts, like you would see certain aspects of the vortex physics. I mean, I'm using technical terms now. If this is coming from fractionalized phases, that experiments don't find that. Okay, so it could be, and that provides a lot of explanations to the phenomenology, but the experiments have not completely been at agree with this.
Because when you increase the density, some of the superconducting, room temperature superconductivity is showing up in high dense region, like sulfide material. So in this case, if you increase the pressure for the fractional Hall effect, is pressure, does it modify the fractionalization?
Okay. I don't, so most likely these sulfides are not these fractionalized objects, but I can tell you about something which is only like 4 months old. Okay. So in a class of materials, I showed graphene. There is now moire graphene, where okay. So there are things called moire dichalcogenide bilayers. They're right next to a fractional 2/3 Hall effect. a superconductivity has been found. Okay? This seems to be the best example of what we called anion superconductivity. I can tell you more about this, but this seems to be the most interesting and thing that's sort of making the community jump up and down right now. Yeah.
Other questions? Yes.
Just a comment there, the Cooper pair is made out of 3 of these 2/3 anions.
Just the the probability associated with the wave function, it goes non-Kolmogorovian in different ways in different systems? Like
what-
probability going negative or, probability of independent events adding up to.
So these are normalized things because the probability current is associated with the particle current. So the conservation of probability is like the conservation of number of particles. So the wave functions are all normalized wave functions. They have a L2 norm. They're square integrable.
Any more questions? Did you mention that this is a group of order 230, something like that?
Yeah.
Which group is it?
So this is the classification of space groups. So yeah, so you take all the point group symmetries and take a product with translation and you classify that.
Thank you.
So R3 cross whatever.
So, any more questions? Okay. In that case, let's thank the speaker once again, and I request Professor Indulekha to hand over a small memento. And I thank Professor Indulekha as well as the 2 speakers for these 2 talks. Now we have a break, after which we'll have a hands-on presentation, and we need volunteers after tea. So please be ready to be called.
Yeah, so maybe you can take turns coming up because we have a few minutes. So everyone needs one sheet of white paper. Maybe it's good to get into pairs. So everyone knows one of their neighbors? Yeah? So we can start passing out actually. So we'll pass out papers. Then we also have tape. So every two of you can have one tape. You can share the tape. 2 people for 1 tape. Same with markers. So every 3 of you can share 1 marker, if possible. So we don't have too many markers. So can we give these so they can share? So 3 people can share 1 marker. And anyone need scissors? Raise your hand if you need scissors. I can pass out some scissors. So, yeah, 1 sheet per person. You can take more later if you need. Right. Yes. So, how many? 3. Here you go.
1 tape for 2 people.
Yes. So just 1, 2. Okay. Yeah. Scissors. Raise your hand. Okay.
1 per 3 persons.
Yes. And scissors. How many more? You can take these.
1 per 3 persons.
Okay. You can actually give these behind you to those. Okay. Oh, thank you. Oh, okay. It'll be easier. Okay. Okay. If there's extra sketch pens, we can maybe do 2. Sorry to change. Yeah, 2 people can share a sketch pen too. Maybe it's okay. I think we have more than we need. So, yeah, if they need. Yes. Scissors. How many? Okay. Extra scissors. Yeah.
Okay,
Scissors you can share. Yeah. Okay. I think.
Yeah, you have a color mic.
Yeah, I think that's. Is this working? The color mic?
I can just fix it. Working, no? Yeah, 1 sheet for each, but 1 tape for 2 people.
We still have? Okay. So we can.
Right.
Yeah, we can give them out, I guess, if there's anyone who wants. So.
1 sheet on. Not right now. Yeah, take.
Yeah. Please. You should also.
Just pass it on slowly. No hurry.
Yeah, everyone in the front row also can take paper, sketch pen, scissors. We have enough for everybody. So.
There may be. You want? Yeah. Yeah, you want?
Scissors,
Do you want?
Yes. Right. Yeah.
It depends on whether you think it's fun or not. Yeah. You want? What is planning to do? Huh? Yeah, I'll come solo one. Huh?
Okay,
I
testing.
think 1 paper for each is
the mic working? Or it's not? Okay. Maybe. I can also use this, I guess.
All of you got a piece of paper at least? Tape. Okay, tape for 2 people. 1. Sorry, bro. Who wants tape? Yeah.
Okay. And we do have some extra sketch pens, so we can give a few more out if people need. So.
No, you want tape?
in the front row, if you guys would like. And then it's a sketch pen. Oh, you, okay, great. And yeah, there's some extra sketch pens. Few extra sketch pens here. Yeah. Sure. Extra sketch pen. And
she can give later on.
you can pass one down. Pass those down. Yeah, a few extras.
Okay.
And
Don't worry about it.
yeah, a few extras. You can share these with the people behind you.
Already he had earlier, no? Stomach, this thing.
You can share these down that way. One last. Who wants the last one?
But don't worry, just have to be strong. Just
Okay.
to go ahead and attend to it.
So,
Yes, attend to it, yeah. Don't worry, just go and attend to it. Okay. Everything will be okay. See you then, huh?
how do I? Ah, is this working?
I'm just wondering, so whether to call for the electoral board meeting. He can't, yeah, he will be attending only in the morning. The electoral board, anyway, electoral board, he's not part of. I thought he will meet editors and meet your people also. So you need something for special like it?
You can share the sketch pens.
No, I'll just ask him.
Scissors.
Okay.
There's one.
So tomorrow you're
Might be one or
practice
two
in the
left,
evening,
right?
Afternoon. So some part of
And maybe the two of you can share scissors and see if there's some sketch pens floating around you can use.
he'll attend some part of the thing. So schedule you can send. 9, yeah, 9:30. 9 tomorrow, yeah, 9 is up. But shorter this thing. Tomorrow's session. 9 o'clock we are starting, I think. Those talks by editors. Yeah. So we'll just let people settle down a bit.
Yeah.
Because I think she works for a resonance and her she has twin children. One of them has high fever, so I asked her to just go back.
Okay, that's good.
So all of you have tape. Okay, half of you have tape, actually. I mean, every half of you. Yes?
Go. Sketch pens are all done, but I'm sure you can find some near you. Oh, you got one. Oh, great.
We have Vijay Ravikumar with us. He's part of the Brain Gain of India, born and brought up in the US, Rutgers University PhD, and then comes to India, works as faculty in Chennai Mathematical Institute, shifts to TIFR, then becomes puppeteer, actor, and then shifts to Asim Premji University, and now he's here with us to share some magic, and we don't know what he'll do next year.
Thank you
Professor
so much.
Vijay Ravikumar.
Thanks so much for the intro. It's really an honor to be here. I'm really happy to be part of Resonance. It looks like an incredible program. So thanks, everybody. Small correction, I did a postdoc in TIFR before I went to CMI, so I didn't, but anyway, that doesn't matter. So, we're going to talk today about geodesics on surfaces. So I'm guessing, how many of you have heard of geodesics before in some class? I'm assuming nobody has for the purposes of the talk, but I know some of you may have. And we're probably going to talk about it a different way than you've seen before. How many people have taken a class in multivariable calculus here? Okay. We're not going to use any of that, but I'm just curious. Has anybody taken a class called differential geometry? Okay. Again, we're not going to use that directly, but what we're doing ties in very closely to what you've seen in differential geometry in a very different way. But again, none of that is required today. This is not for math people in particular. So I want to start with just a story, a simple story or example about a hungry ant. So, as you all know, ants are very, very good at finding the shortest path to food. Especially if you live in South India in the tropics, if you drop some food or some sweet on the floor, within a few minutes, ants have found it, and they've also created a very nice pathway that seems ideal in many ways. So let's try and determine the shortest path in a few cases. So here's the first case. Let's say that we have a box. There's a laddu on the top of the box, in the middle of the top flap of the box. There's an ant right here in the center of this side flap. So what is the shortest path from the ant to the laddu? Can anyone tell me? So what do you mean by straight? What should it do? Can you tell me? Perpendicular to the face? How does that, can anyone else describe it? Anyone else want to tell me what's the shortest path? Yeah, yeah. Uh-huh. Walk straight up and then turn and go straight. Okay, like that, horizontal. Exactly, that's right. Simple, right? Let's make it a little more complicated. Let's put the laddu, let's imagine you've kind of, smacked the laddu onto the edge of the box. It's stuck there. The ant is still in the center of the space. How does the ant, what's the shortest path the ant should take? Yes? Oh, okay, interesting. Any other ideas? So she's saying the ant should move towards the corner and then straight. How many people think that's right? That's a very good idea. Okay, so basically, let's try unfolding the box and let's see what that looks like. So you're saying this, right? Walk to the corner and go straight. What does that look like on the unfolded box? Notice, how did I unfold the box? This hinge here, I opened it. This top part, I opened it up. So I've unfolded the box. And this path you described, what does it look like over here on the unfolded box? It's going like that, right? So is that really the shortest path? How can we improve it? Exactly. So on the original box, what will that look like? Something like this, right? So actually, that's the shortest path in this case, not what we all originally thought, which is kind of surprising. So we have to be a little careful. We have to unfold and then see what the straight lines are. Here's an even slightly trickier one. Now the laddu is in a really weird position. It's on, does everyone understand? It's on kind of the back side of the box. That's why it's kind of hidden. It's on that side, but it's also close to the bottom. So I've given dimensions now. It's no longer in the dead center. It's kind of halfway along that bottom edge of the box, but 1 centimeter up from the ground. And this is now a 12 by 12 squares on the sides of the box, and it's 30 centimeters across. So, and the ant is similarly positioned on this flap, but on the top instead of the bottom. So now, how can we find the shortest path now? Any guesses, or is it just very complicated? Yes? That's a good idea. We can try unfolding it. Now, the one little thing to keep in mind, there's actually multiple ways of unfolding it. Earlier, I only showed you one way, but there's actually many ways we could unfold the box. So just to throw a few ideas out there, there's actually many, many ways, but I'll just show you a few ways. So this is one way of unfolding the box, where, what have I done? Just try and visualize it. What's happened here is this flap has kind of gone up, and this flap has also gone up, and that's why we're seeing this kind of top row, right? Can everyone see that? So this is one way of unfolding the box. Here's another way. What have I done here? Can you see which cuts I've made to unfold the box like this? Can anyone tell me which cuts have I made? Which edges have I kind of sliced open in this case? Nice. You can kind of see from the ant's orientation, right? The ant is facing up. So I've opened up along this hinge, right? And I've cut the other edges. Over here, the laddu is here, so I've kind of opened this like a cabinet. I've opened it up along this hinge, and the others are sliced, right? What about this one? This is kind of funny. This is kind of more funky. How have I unfolded this one? Which edges have I made into kind of hinges? So here the ant is being folded up, the laddu is being folded down, right? Oh, great. Okay. Yes, this is good. Okay, does that make sense? And finally, I'm just giving you another one. There's actually even more than this, but just for right now, I'll give you one more. Here, I've opened the ant like this, but the laddu has opened down. So all of these are some simple possibilities, just permuting the different possibilities. So what which one is the shortest path? Well, honestly, here, it's hard to know intuitively. We kind of have to calculate. So we have to draw a straight line on the unfolded box. Here, well, okay, I gave you the answer, but it's just simple arithmetic, right? 1 centimeter up, 30 across, then how many down? 11 centimeters down, so total of 42 centimeters. This one here, what is this going to be? Well, we can use Pythagoras, right? So what is this leg here? That's, yes, this is 11, right? No, not 11, sorry. 10. This part here is 42. Is that right? 30 plus 6 plus 6, yes, 42. So 42 and 10, right? So that is what? Okay, I'll tell you. I put it in my calculator before. It's something. It's already, it's more, so it's no good. That's no good. But what about this one? So this one, what are these legs? This leg here? This leg here is 30 plus 1 plus 1, 32. This leg here is? Yes, 24. 32 and 24. This, if you put into your, some of you might know, it's 40. It's exactly 40. So we seem to have a winner, right? This is better than this and this. And it's kind of a nice path in a way. I mean, it is kind of neat. Surprisingly, this is actually not the best though, because this one here, what are the legs? This leg is, again, 32. This leg, sorry, not 32, 37. This leg here, 17. No. Is that right? 15. Sorry. 37 and 15. So if you plug those in, we actually get 39.9. So slightly less than this. So it's not a very elegant solution. It's just guessing and checking, but we see that it can be more complicated than we might think. That's the only lesson here. And that the way of unfolding can matter a lot when you're trying to find the shortest path. So the big definition for today is a geodesic. A geodesic is a path that is intrinsically straight. So this is a definition that might be different from definitions you've seen before. You might have seen it as a locally distance minimizing path, a locally energy minimizing path. Today we don't need to get into all of that. They're all equivalent, but we're really going to think of it as a path that's intrinsically straight on a surface. It's always moving straight. So on the Euclidean plane, geodesics are simply straight lines, and we've all worked with straight lines before, right? But a question I have, since we're moving into things beyond the Euclidean plane, like this box, is it true in general that a geodesic between any 2 points is always the shortest path between those points? Is that true? Yes. You're saying that it may not be true. Okay, we'll get to the second part. The other thing you said, we'll get to it in a second. But why is it not always the shortest path? So we have an even more immediate counterexample, which is what we've just seen right here, right? These are all intrinsically straight paths. They're all moving forward. The ant is never turning left, never turning right. The ant is always marching forward. That's one way to think of a geodesic. The ant is always moving forward. It's never turning. Or if you imagine yourself on the surface riding a tiny bicycle, you're just always pedaling. You're never turning your handlebars. So that's a geodesic. And all of these are geodesics by that definition. They're all intrinsically straight, but only one of them was the shortest path. So already, without getting into spheres and stuff, great circles, we have a counterexample here, which is that in that case, we see a geodesic may not be the shortest path. But you brought up an interesting question. Is the shortest path between 2 points always a geodesic? So you said that yes, it is. Anyone else have ideas about that? Yeah. Locally shortest, interesting. So, okay, so you're saying maybe a geodesic may not be but no, the question is the shortest path always a geodesic? The second question. Is the shortest, given 2 points on a surface, let's say I give you a path, which I tell you is guaranteed to be the shortest way to get from point A to point B. Is that going to be straight? Is it going to be intrinsically straight?
No, I'm saying there are maybe more than one shortest path.
There might, well, yeah, that's a very good question. Could there be more than one shortest path? What do we mean by but if there's more than one shortest path, like on a sphere maybe, still, do they have to be geodesics? Yes. So, okay, I think everyone's intuition here is good,
the shortest path on any reasonable surface is a geodesic in some sense. When I say reasonable, I mean a surface that you have it that's not missing pieces. So you could do something very stupid. You could take the Euclidean plane and just subtract a point. And that's still a surface with some boundary. And then, you know, the shortest path between 2 points whose line goes over that missing point is no longer valid. So there you've constructed a stupid counterexample. In general, if you have a smooth manifold, something called a smooth surface, then it will be true that the shortest path between 2 points is always a geodesic. And for our purposes today, we'll assume it's true. The shortest path will always be a geodesic. But the big lesson so far today is that a geodesic may not be the shortest path. That's what we've seen so far. So I want to look at other more interesting surfaces now. So let's go to the sphere that you mentioned. Can anyone describe the geodesics on the sphere? I think you alluded to it. Does anyone else here know what the geodesics on the sphere are? These are the paths that are intrinsically straight. That's what a geodesic is for us today. A path that is locally or intrinsically straight. You're never turning, the ant is always marching forward. Yeah. Great circles. Nice. Nice. So one way, if you don't know that, one way to check what a geodesic is a very simple test you can do. So I have a sphere here, and because a geodesic is a path that's always going straight, where the ant is always marching forward, we can generate geodesics very easily using a strip of a thin ribbon of paper. Now, you can't do this with a string. You have to use a ribbon of paper because paper has a very nice property that if I start it somewhere and start moving it forward, it can't bend left or right. It's guaranteed to go straight by the material properties of the paper. So a thin ribbon of paper is an amazing device for generating a geodesic, for revealing a geodesic. So it's a very useful device, and you can see if I can pick a starting point, I can pick a starting direction, and I can kind of launch my geodesic. I just keep its base point fixed, and I start moving it forward. And it's very important here, you just see where the ribbon wants to go. You don't try and influence it. You just let it go straight. It wants to go straight, you let it go straight, and you see what kind of curve it ends up creating. And what kind of curve is that? What kind of curve do we get? We get what you just described, which is a great circle, or a great circle. And what is a great circle? Well, it's a curve that divides the sphere into two equal parts. It's like the equator, right? So in this case, if I position it like this, it looks like the equator. So this is a very nice way of creating a geodesic. So maybe can I get a volunteer to come up for just a second? Because there's a misconception I want to clear up very quickly. So I need somebody to hold the sphere for me, just to help out. So, yes. So I know this is something maybe you all know, but in case it's often confusing to people, why is it that when we see the Earth, we see these lines of latitude and lines of longitude, right? So are the lines of longitude and the lines of latitude, are they geodesics? Can anyone tell me? Can somebody raise your hand and tell me? I can't see who's... Yeah, what did you say? So that's a good point. So no, I mean, the lines of longitude are, the lines of latitude are not. And you can see that very clearly if you take, suppose this is the equator here, and suppose you try and draw a line of latitude starting here. So I'm starting it with its initial kind of direction vector is in the direction of that line of latitude. But now as I start to smooth it out and see where it wants to go, it just wants to go down, right, and create a great circle. It doesn't want to go around that line of latitude. So you can see very clearly why those lines of latitude are not geodesics using this technique also. So this is going to be useful for us. Thank you so much. This is going to be useful for us as we go forward because we have to distinguish geodesics from non-geodesics. And this is a very good test for that. So a sphere is a very symmetric kind of shape. Before we do our activity, I want to just also show that this method can work on any surface. It doesn't have to be a sphere. It could be something that's that's less regular. This is not so interesting. I was hoping to find something more interesting. The shopkeeper convinced me to get this. He's from Kerala. Apparently it's called Kerala cucumber or some kind of velorekai. It's a very, very good in sambar, apparently. So but you can use this on any surface. You can start your geodesic in any spot, choose a direction, and just see where the ribbon, see where it wants to go. And it'll be guaranteed to move on a geodesic. Notice it may not be a closed geodesic. It may not even have finite length. It might just keep going and going and going forever. We don't know. The great circles had finite length. It kind of came back to where it started with the correct starting direction. That may not always happen, but but in this process you can get lots of interesting geodesics on any surface. So this ribbon method is quite spectacular that way. It can really get you. You can really generate any geodesic on any surface this way. Maybe as an aside, has anybody ever heard of the theorem of the three geodesics? I'm guessing no. But there's a theorem that a mathematician, Poincaré, he conjectured in 1905. So his conjecture was that any surface that looks kind of like a sphere, which is homeomorphic to a sphere. It's like a sphere that you stretch or kind of morph without cutting it, without kind of making a hole in it. Any surface like that is guaranteed to have three simple closed geodesics. And in the case of an ellipsoid, you get exactly three. So this is a nice theorem that had a long history because it was only proved in the 1980s. But for example, this is kind of like an ellipsoid, so you can actually construct those three geodesics on this shape, for example, and see what those are. They're basically going to be the three principal axes. So, but unlike the sphere where you have infinitely many great circles, right? Infinitely many simple closed geodesics, on an ellipsoid you'll only have three. And on some surfaces, which are not, so you'll always have at least three, but you may have only three, that's all. So, sorry, that's just an aside for the people who are more interested in some of the history of the math. But I want to turn our attention now to some surfaces that we can build and work with right now. So cylinders and cones. So for our purposes, we're going to imagine that these surfaces are infinite. There's no boundary. So when we build a cylinder, it's just a finite portion of an infinite cylinder. When we build a cone, it's just a finite portion of an infinite cone. That way our geodesics don't have to hit a boundary. They can keep going and going. So that's just something to keep in mind. I'll remind us of that later. So the question I want to ask is, how do geodesics on cylinders and cones compare to geodesics on the plane? How do they compare to straight lines? So let's start by constructing a cylinder, a cone, and some geodesics. So everybody has these materials, right? Or you're sharing these materials. If anybody needs something, you can raise your hand. We'll give you what you need. But what I want you to do, I'll just give you instructions quickly. So you have your A4 sheet. First step is cut 3 ribbons on the long side of your A4 sheet. These are your geodesics. They're going to help you create geodesics. So cut these 3 ribbons. Fold the remainder of your sheet into 3 parts and cut along those parts. So you want to get 1/2 like this, and then 1/4 and 1/4. And this, you're going to make this big rectangle into a cone. You're going to make this small rectangle into a cylinder, and you're going to keep this for later. You'll need this later, but not right now. So, sorry, one last thing. And then finally, you can color the ribbons with a sketch pen if you want. Into one color, different colors, it doesn't matter. So that's just for fun. That's not essential, but it'll help us see the geodesics on the surfaces. Yeah, so raise your hand if you need something. We can try and bring it to you. What do you need? A4 sheets. Okay. Oh. Oh, more? Okay. Yeah, 2 more, ladies. Yeah, if there's any doubts or you want any help, me or somebody else can come and help. So, one piece of advice, don't make your geodesic ribbons too thick. So I'll just show, this is a little, if this is going to be 2, that's fine. If you're going to split this in 2, that's good. But on its own, it's a bit too thick to really to be easy to use. So. Actually, this is nice because you can, geodesics on the Mobius strip are also quite interesting. So you can look at geodesics on that as well. Yeah. You're asking about cutting it. Yes, 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 yes. Okay, okay, yeah. I know, yeah, he was asking what happens when you cut the... We also, yeah, that we can, yeah, we can. Yeah, I got it yesterday. So have you had it? Used it before? This? Yeah, I've never tried it. Yeah. That's good. That's so good. Actually, that's up to you. Either one's fine. Yeah. Cone is tricky. Yeah. Cone, any way of making it is fine that you've learned in school. But if you want, yeah, you can do it. Yeah. Anything is fine actually. However you. Yeah. Yeah. Just try to make sure it has a vertex. I mean, it has a point. Yeah. So. Tape. There might be. Yeah. Yes. Yeah. Yes. In the sense, it doesn't matter. If you want, yeah, you can actually just, yeah, the boundary of the cone doesn't matter. In the end, it's an infinite cone. This is just a finite piece of it. If you make it circular, it's nice. Then you can sit it on the desk or sit it on the desk. So, but if you don't remember how to do that, then you can make just a, yeah. Yeah, so if you remember how to make a circular cone from school, you can do that. So everyone's finished their geodesics, looks like? Okay. Do you want help with the cone? Yeah, so I think, so one thing you could do, I mean, yeah, you could, if you're doing a circular cone, you could cut a circle like that and then put it together. So if you, that might make it a little easier. Otherwise you could also just do, yeah, you could also do this and then just tape it here. Okay, yeah, that also works. So maybe, here, I can hold it if you want. And, let's see if we have extra tape. Yeah, there's some tape here. That might be. Always difficult to get it started though. Okay, actually, can we use that tape? The tape? Oh, this one also has the same issue though. Oh no, it's. Yes. So I think what she was referring, she meant like a cone with a circular base. So yeah. Yeah, so basically if you first cut, so for example you'd have to cut it like that to make a circular, yeah. Oh, did I leave my clicker? Here it is. Yes. One cylinder. Keep this sheet we'll use later. So just you're done. That's perfect. That's perfect. Okay, so some people are getting done, I think. How many people have finished their cylinder? Cone? How many people have, okay, so keep working on the cone. I'll start giving the next instruction so people can start moving forward. But do finish your cone. So I want to just remind us of the definition of a geodesic. And I'm going to modify the definition slightly, just slightly. So I want a geodesic to be a maximal path that's intrinsically straight. So for a true geodesic, just like a line, the analogy is like a line in R2, in the Euclidean plane. It just keeps going and going. It doesn't have an end. It won't. A geodesic segment is a finite portion of a geodesic. But a geodesic on its own it might be finite, it might be infinite, but it should keep going. It should not abruptly end for no reason. So it's a maximal path that's intrinsically straight. It's continued as far as it can go. So the question I want to ask right now, and maybe you can, if you're not done with the cone, it's okay, but let's look at the cylinder first. We'll do the same with the cone. But what do the geodesics look like on the cylinder? Let's use the geodesic ribbons and see what types of geodesics we can create. And I guess the same with the cone. What do the geodesics look like on the cone? So let's explore these two questions for the next few minutes. And once you guys have some examples, you can show us what kind of geodesics you get. So right now it's a very vague question. We're going to ask much more specific questions in about 2-3 minutes. But for now, just see what do your geodesics look like on the cylinder and on the cone. And you might sometimes, it's nice to have 3 hands or 4 hands for this. 2 hands is sometimes not enough, so work with your partner if you need to. One person can hold the object or hold down, and then you could smooth out the geodesic to see where it goes. Sometimes it's useful to have a 3rd hand. So. That's a very good question. Can you try and answer it? That's a very, very good question. Okay. Ha. So if it's crossing itself, I mean, just imagine it like a parameterized curve, like an ant moving. So if it crosses its path, it can still keep going. So that shouldn't be the end. It should keep going and going as long as it is straight and as long as there's still surface to go on. So.
Is the end defined by the starting point?
No. No. I mean, again, this is not a geodesic segment, it's a geodesic. So even there's no starting point in that sense because we can also play it in negative time. I mean, so the geodesic should, you can continue it indefinitely in either direction. So. The cone is difficult? You could maybe do a circular cone then, it might be easier. So, nice. Yeah, so this one will keep repeating. So this is a closed, what we call a closed geodesic, like a great circle. Nice. Some very nice cones I'm seeing. And some very nice geodesics. So, interesting. So, has anyone produced a geodesic on a cone yet? Yeah. Okay, let's see. Nice. Interesting. So it's curving around and okay. Interesting. Okay. Nice. Yeah. Mm-hmm. No, so all of this depends on the metric of the surface. So you'll get it if you, so right now we're using the standard Euclidean metric on the surface. If you use a different one, the geodesic will still be the straightest path according to that metric. So, yeah. It's still the straightest path according to that metric. Not compatible with which metric? Okay, that's a good question. I'm not sure about the answer. I'll have to think. But I think even there it should be. So we may have some assumptions like that we need to make. But anyway, we can talk about this more later. Yeah. Yes. Closed in, you're, that's right. Yeah, that's right. Yeah. Okay, so I want to give so I've seen some examples on that side. Anyone else have an example of a geodesic on their cone or cylinder that they want to show us? Any interesting examples that people have found? Okay, actually lots of interesting examples that I'm seeing. Okay, nice. I'll give it, let me ask some slightly more specific questions and then maybe we can use these examples. So I want to review some properties of geodesics that you already know from going back to your school days probably. Because these are properties of geodesics that we know from the plane, from the Euclidean plane. Properties of lines, essentially. So the first property is that there is at least one geodesic through any 2 points. right? This is the property of lines in the plane. Not if, this is not, I'm not claiming this is true in general, but this is a property of lines in the plane, right? Everyone's familiar with this, right? There's a unique line through any 2 points. That's something else we learn in school. So let's translate that into the language of geodesics. I'm just saying geodesic instead of line. There's a unique geodesic through any 2 points. So again, we have to ask, is this true? Does this continue to hold for the cylinder and the cone? Another familiar property that we know of lines is that two lines meet in at most 1 point, right? In the plane, if you have two lines in the plane, they may be parallel or they might meet, but they're going to meet in at most 1 point, right? Another property, all lines in the plane have infinite length, right? There's never a line with finite length. Another property is that a line segment always gives the shortest distance between 2 points. That's another property of lines in the plane. And finally, a property we learn in school is that a line never crosses itself. We never have a line that somehow manages to cross itself. So these are all properties of lines. Which of these hold for geodesics? Do these still hold for geodesics on cylinders? Do they hold for geodesics on cones? Which of these hold? What's happening here? So are there any properties that no longer hold? So using these models you've made, let's spend just a couple more minutes and see, can we find counterexamples to any of these? Are there any of these that no longer hold? Yes. The fourth one. So all geodesics have infinite length. Did anyone find a counterexample? For a cylinder, you said, you can do a horizontal geodesic. That's a nice counterexample. That's right. So we have one there. Any other counterexamples to these properties in cylinders or cones? Infinite length. So that's what, yeah, exactly. That's what. So what's the counterexample? In cylinder. Okay. What about cone? So let's focus on these three properties. I think these are the three that are going to be the most interesting for us today. So let's take these three properties and find any counterexamples. Or, so I'm just relisting the properties here. 2 points. So can you find 2 points with multiple geodesics between them? Can you find a finite length geodesic? Can you find a geodesic that crosses itself? And can you do this on the cylinder? Can you do this on the cone? So when you've constructed an example, try and come and show us. And if you don't believe an example exists, if you believe the property really does hold on the cylinder or the cone, then explain why you think that's the case. So you already have a okay, so he has a self-crossing on the cone, if everyone can see. There's an example of a self-crossing on the cone, but you can try and make your own as well. Yes? So, yeah, we can show. And I think, did you have? I thought I saw. You, show? Oh no, you had one, right? Okay. You got rid of it, okay. Yeah, I saw it earlier. That's a nice one. It's just hard to see because it's white, but yeah, but otherwise it's nice. So, yeah, so quite a few of you have found self-crossings on the cone. Yes. So this is, what's your name? Sorry? Sankal. Sankal. Did I get it right? Oh, sorry. Sankal. So he has a self-crossing right here on the cone. Maybe, yeah, thanks. I actually have a slightly bigger version of that here. So, 1 second. Oops. Yeah, so this is, I just made a model before just so people can see, but you can get a self-crossing on the cone, like you saw. In fact, sometimes you can even get multiple self-crossings. You can get a geodesic that crosses itself once, not once, but twice. So one question you could ask is, and again, this is just a bonus question, how many self-crossings can you get? That's just a bonus question if anyone wants to think about. How many self-crossings can you get? You can get one, you can get two maybe. So that's something to think about. But you can get self-crossings on the cone. So that's a very useful counterexample. So that's a way that geodesics on the cone are very different from geodesics on the plane. What about the cylinder? Can we get, yes? So I'm not saying it's only 2. I'm just saying that just like he produced self-crossing, you can also manage to produce one. Maybe you can manage to produce one with 2 self-crossings. Maybe 3, maybe 4. So it's something to think about. Can you keep doing that? I'll leave it as a question. It seems like maybe you can keep doing that, but one has to think about it and try it and experiment with it. So what about the cylinder? So this is nice. So we saw a geodesic with self-crossings on the cone. What about the cylinder? Can we get self-crossings? Cylinder, no. What, can you give us a short explanation why you don't think so? That's a very interesting point. If you unroll the cylinder, the geodesics will be lines, and then we're... Okay. Nice. Nice. So, what about finite length geodesics? Did anybody find a finite length geodesic? I think I saw one on the cylinder. Somebody showed me, right? Did you? You showed one right there, right? If you can just hold it up, we can see. So on the, yeah, exactly. So yeah, a few people have made finite length geodesics on the cylinder, just a horizontal geodesic like this, right? That slices it like that. So that's very nice. In the cone, did anybody manage to find a finite length geodesic? So that's a good question. So you might think, so first of all, just like on the sphere, remember, the lines of latitude were not geodesics. So something very similar happens here on the cone. You might initially think, oh, let me try the same thing I did on the cylinder. Let me do a horizontal geodesic. That doesn't work. It's going to immediately start going up or going down. So you won't get one that way. That's a good idea. Maybe you can get an elliptical kind of orbit. But you should try and do it and see if it works. And if anyone can do it, I'll be very impressed. So it's again, it's something that seems intuitively plausible, but you have to try and do it and see what happens. Yes. So okay. So here we're imagining these are infinite cylinders, infinite cones. If we introduce a boundary, then, but I don't. For that reason, I don't want to do that. I want to work with the infinite version. Yeah. Okay. So I want to also look at this last question. This is going to be especially important for us now. Did anybody find 2 points with multiple geodesics between them on either the cylinder or the cone? You did. Can you describe it?
No. If you have 2 points,
Huh.
at different heights, you can reach it either one way or the other.
Okay, nice, nice. You can go, if you have your cylinder, he's saying that you can go around it in either direction. So, okay, this is not a cylinder. But if you imagine a cylinder here and you have 2 points diametrically opposite, or even just literally diametrically opposite, you can go around this way, go around this way. But that's a good example, but they're both part of the same geodesic, both those paths. If it's literally diametrically opposite. If we raise one, then we actually get two completely different geodesics that connect the 2 points. So that's a very nice example. So it is certainly possible in the cylinder at least to do this, find 2 points with multiple geodesics. So I want to, because we don't have that much time, I want to move on and see how we can, actually going off of the idea that, what's your name? Suhir. What Suhir described, can we find a way to actually count all the geodesics between 2 points? And can we find a way to kind of in a more precise way, formulate arguments about the number of geodesics? So at the same time, it's very useful to just play with this ribbon because a lot of things that seem possible, we don't really know till we try it. In fact, with the cone, we won't actually have any finite length geodesics. It feels like we should be able to do what you described, this elliptical orbit, but if you try it, it's going to come back, even if you manage to get it to come back to where it started, the angle is going to be wrong. So it's going to keep going in the wrong direction. So it won't really work. So suppose A and B are 2 points on the cylinder. How many geodesics can we create between A and B? That's the question I want to look at for the next few minutes. And let's try drawing these geodesics between A and B on our cylinder. So I want to introduce an idea that's helpful, something he mentioned, which is a covering of the cylinder. So an N-sheeted covering is something I'll introduce in a second, but first I want to introduce a one-sheeted covering, which is what most of you already built. So a one-sheeted covering is just the unrolled version of the cylinder. If you cut the cylinder along a cut line and unroll it, we get the one-sheeted covering of the cylinder. That's what this is. And notice that in the unrolled version, we have a sort of a copy of this point A, a second copy of it. So, because both those corners kind of get identified when you glue your sheet back together. So, you've already constructed a cylinder, and you can, on your cylinder, you can imagine a point A, maybe along an imaginary cut line, or the actual cut line that you used to glue. And you can imagine a point B. How can we find the two geodesics that were just described? So he just described two geodesics connecting A and B. Can the one-sheeted covering help us draw them carefully? How would we do that? Can anyone else tell me? So if we want to now draw, if you imagine cutting open your cylinder and then drawing on it, how would you go about drawing two geodesics connecting point A and point B? Does that question make sense? So once it's flat, exactly, you can connect A to B here, but we have another copy of A, right? So we can connect A to B from here. And then if we re-roll it, we'll see exactly the two geodesics that he described, one going in one direction, one going in the other direction. And you could even use the ribbon test to verify that these are really geodesics. So but what if, are those all the geodesics we have? I heard some people say no. And the reason is that we can do an N-sheeted covering. So we can do a two-sheeted covering, for example. So suppose you take two sheets now, and you sort of roll it up, but you roll it up twice. So you double it, right? Now, you can mark the points A and B. Imagine you're using transparent paper, right? So you're literally rolling it once and twice around itself. So now we have, when we unroll it, this two-sheeted covering of the cylinder, we have 1, 2, 3 copies of point A. We now have 2 copies of point B. And how many geodesics does this allow us to draw on the cylinder? So take a minute to, just take a moment to check, and in 30 seconds, you can announce your results. So we have the two geodesics from before. We still have this one, and we still have this one. But what additional ones do we have now? So total, how many? 6. Can anyone tell me the 6? Do you want to tell me? Let's say this is A1, A2, A3, B1, B2. Sorry. A1, A2, A3. And similarly for B. So you're saying just connect this to all 3 of these, and connect this to all 3 of these. Is there any redundancy? So we have some redundancy because we did this line, right? And we also did this line. So we have some redundancy. So how many geodesics do we have here? We have 5? 4. We have 1, 2, right? So yeah, we can connect B1. We can connect B to this, this, but we can also connect this to this guy, right? That's the additional one we get now from starting with this B. So we have 4 total if we don't want redundancy. So this lets us draw 4 geodesics on the cylinder, and you can actually do it. I mean, you can physically do this. You can also do it on your cylinders by kind of changing the angle of your ribbon, and you can see that there's many ways to get from A to B. So I guess a lot of people have gotten this, but maybe on a 3-sheeted covering, how many geodesics will this 3-sheeted covering allow us to draw? So a special prize for whoever can answer this first. Who said? Okay. Okay, so your special prize is the Kerala cucumber. So it's supposed to be very, very good in sambar. Okay, so 6, we get 6 here. But what does this tell us? We can get 6 here. So overall, how many geodesics? What's the total number of geodesics between A and B? On an N-sheeted covering, that lets us draw 2N. And now, forget the covering, just the cylinder itself. The covering was just a tool to help us understand the cylinder. On the original cylinder, how many geodesics do we have between point A and point B? No, but if we, what I'm saying is, we can, we have these, an N-sheeted covering lets us draw 2N geodesics. But now, just going back to our cylinder, how many actual geodesics are there that we can draw on the cylinder? N was up to us. We could do a 2-sheeted, a 3-sheeted, a 4-sheeted, a 5-sheeted covering. So, but that's just up to us. That's just a tool we can use to help us draw more geodesics. If we forget that tool for a moment, actually how many geodesics are there on the cylinder between point A and point B? There's no N now. There's no N now. Because we introduce an N. We introduce a 5-sheeted covering or a 10-sheeted covering to help us draw. But in the end, we're just drawing geodesics on that cylinder, right? So in the cylinder, the actual cylinder, I heard somebody say it, we can go, basically, what is N? It's anything you want it to be, right? So actually, there's infinitely many, right? Does that make sense? You can draw infinitely many, and you can go as high as you want. I can always do an 11-sheeted covering. I can always do a 111-sheeted covering if I want, and get 222. Any even number. So we can draw infinitely many geodesics between A and B. So I want to take a break, but one last question before we break. How many geodesics are there between 2 points on a cone? Are there infinitely many? Given a point A and a B on a cone, are there infinitely many? Are there finitely many? So we'll explore this question after the break, and maybe we'll take a 10-minute, 15-minute? Yeah, we'll take a, what time is it? Is it okay if we just take a 10-minute break? Is that okay? Yeah, we'll take a 10-minute break, and then we'll come back to this. So you can think about this question, and then There's some interesting examples I've seen in the room. So do you still have it, or did you lose your example? Okay. So for example, here's an example with, he's constructed 2 points with 3 different geodesics between them, right? These 2 points, and there's one more that fell off now. But there's an example with 3 geodesics between 2 points. So clearly, it's definitely the case that we can have more than one geodesic between 2 points. But the question is then, is there a limit? Like, are there only finitely many, or could there be infinitely many geodesics between 2 points? So what do people think? How many people think there's infinitely many geodesics between points A and B on the cone? And how many people think there's only finitely many between points? Okay, kind of evenly divided, and some people are not non-committal at this point, but evenly divided, interesting. So we saw, I mean, it makes sense. On the cylinder, we saw infinitely many. And actually, one student, what's your name? Purve. Purve had a nice argument, interesting argument. Why can't we just deform the cylinder into a cone, and we just deform those infinitely many geodesics to another set of infinitely many geodesics on the cone? The problem is that when you're deforming like that, you will get a bunch of infinitely many curves. You'll get a family of curves on the cone, but they may no longer be geodesics. They may not be intrinsically straight anymore. That's the problem with that argument. So we have to be a bit careful with that, but it's a nice idea. So let's explore this question further. So how many geodesics are there between 2 points? Let's use the same strategy. We used an n-sheeted covering for the cylinder. Can we make an n-sheeted covering of the cone? Why are you shaking your head? In agreement or disagreement? So let's start with a 1-sheeted covering of the cone, okay? We take the cone, a simple cone without layers, and then cut it down a cut line, unroll it, and we'll get something like this, right? I mean, if it was a circular base, it'll look like this. This is a cone with cone angle 90 degrees. You may have done one with a different angle, 180, or if you like rolled it over more, you might have gotten less than 90. All of your cones probably have different angles. But in my example here, I'm using 90 degrees as the cone angle. So as a result, my 1-sheeted covering looks like this. And just like in the cylinder case, I have my point Q, the label went away, but this is Q, this is P. Here's Q here, and I have 2 copies of P because those are identified, right? When we glue this up to make our cone, this edge gets identified with this edge. This P is the same as this P. They're just 2 copies of the same point. So how many geodesics can we draw between P and Q using this 1-sheeted covering for assistance? So how many, okay, I heard 2. Any other? Raise your hand with the number of copies of geodesics you think we can draw. So I'm seeing a lot of people say 2. So, and what are those 2? Right, P1 to Q and P2 to Q. So we can draw a line here, we can draw a line here, and this line will give me this geodesic, this line will give me this geodesic that goes around the back. Does that make sense? This blue geodesic, once I roll it up, it's kind of, or I guess, yeah, it's kind of going around the back like that. So we get 2. So, okay, but now how many geodesics are there total? So can we add more sheets? Can we make a 2-sheeted covering? Now remember, the logic behind this covering, we want to why do we want to add another sheet? Well, we want to know what happens to a geodesic once it leaves the sheet, right? We want to be able to follow where it goes next. So if I have a geodesic that's kind of moving, just from some point here and maybe going off here, we want to know where it goes next. And that's where the next sheet comes in. It's just another copy of this, but it tells me where that geodesic goes next because this is identified with this edge. So if I add another sheet here, this will let me follow a geodesic, continue it, and know where it's going next. I can just take whatever I've drawn here, kind of rotate it back to here, and I see where it's gone next. Sorry, I shouldn't touch that, I think. So that's the logic behind a 2-sheeted covering. So we can add a 2-sheeted covering, just like this, and you can physically do this. You can kind of take this semicircle, and you can roll it twice, and you'll get 3 copies of P. 1, 2, 3. And in this case, how many geodesics does this allow us to draw? So everyone take a moment. You can do it either with your cone or just conceptually, but how many geodesics do you think this 2-sheeted covering allows us to draw on the cone? Take a few seconds to think. Why not 6? No, no. We're just at the 2-sheeted covering now, not the n-sheeted covering. So 2-sheeted covering allows us to draw. I heard a lot of people say 4. What are the 4? So P1, Q1, this one here. P2, Q1, that one there. P3, Q1, okay, that one there. And P1, Q2. Nice, nice. You're right, so we get these 4. Wait, is there any redundancy though? P1? P3, Q1? Yes, nice. And yeah, so that's good. So we get 4. Everyone's okay? Cool. And what's the total number of geodesics between P and Q? And again, you can add a 3rd or 4th sheet if you want. So I'll just add it here for you to help you out. If you want, you can add a 3rd or 4th sheet. And now, what's the total number of geodesics? And notice that because this is a 90-degree cone, I can't really add more sheets after that, right? So 8. Yeah, 8 is a good guess, but make sure there's no redundancy. 5? Can you describe the 5? Again, let's call it P1, P2, P3, P4, Q1, Q2, Q3, Q4. So the 5 are P1, Q1, P2, Q1, okay, P3, Q1, P4, Q1, okay. Are those all distinct? Everyone's okay? P1, Q1, P2, Q1, P3, Q1, and P4, Q1, all distinct, right? So we have 4. Any others? P1, Q2, this one. Is that distinct from the 4 that he mentioned? No, why not? We can rotate it, right? So instead of that, we can do this, and that's the same thing, right? So 4. So actually, in this case, the 2-sheeted covering was enough to get all of them. Nothing extra we gained from the 3rd and 4th. And we can't, if we do a 5-sheeted or a 6-sheeted, we're not getting anything else, right? But because the geodesic, we can already, this lets us follow it as far as we want already, right? So there's really only 4 geodesics in this case. And so going back to the question, there is in fact a limit. It's not like the cylinder. There's only 4 in this case. Does this hold for any 2 points on the cone, any P and Q? Or does my choice of P and Q matter? I chose this P and Q here. Keep this cone, this 90-degree cone. Does it matter where I choose my P and Q? Yes. Ah, okay. So you're saying if I just shift this Q over to this cut line, right? Right here, then? Oh, center. Okay, it's the vertex. Okay. Okay, I see. So you're saying, yeah. So then if it's on the vertex, we're just going to have that one geodesic. What if it's on the cut line? Will we have 4 then? If it's on the cut line? 3. Because it's a little confusing what happens when it, can the geodesic pass over the vertex or not? If we allow it to pass over the vertex, then maybe we can have 4. But that's a good question. Can we or can we not? So if anybody here, this is actually a very interesting question. So we're starting to see here is that not all cones are created equal. The fact that this is a 90-degree cone matters a lot. If I'd chosen a 60-degree cone angle, then we'd be having a different story. Then for the general position P and Q, how many geodesics would we have between a randomly chosen P and Q? In this case, can anyone guess? With a 60-degree cone, we'll have a slightly different picture. And how many? I heard an answer 6. That's right. We'll end up having 6 geodesics between an arbitrary P and Q. But again, it's not true of a very specially chosen P and Q. And the other very interesting thing, and this is a very fun experiment that I recommend everybody does later, is actually maybe we can continue the geodesic past the vertex with these very special cones. So the 90-degree cone, the 60-degree cone, these are cones where the cone angle divides 360. So we have it perfectly divides 360. So our our maximum covering space, maximum sheet of cover perfectly fills the Euclidean plane. And that special property makes this what's called an orbifold. And that gives us many nice properties, including the property that we can continue geodesics through vertices. But just on your model, if you have an orbifold, the one way to see it, take a point here, any point P, start a geodesic there, and take the limit as you move your geodesic closer and closer to the vertex from this side, and take the limit as you move your geodesic closer and closer to the vertex on this side. If it's an orbifold, those two limits will agree. If it's not an orbifold, they won't agree. So you really can continue geodesics through vertices on orbifolds, which are these very magical surfaces where the cover perfectly fills the Euclidean plane. And the reason this is an experiment I actually recommend you try on your own at home later is that it's very interesting how this happens, because this, as you can see, as this geodesic comes closer and closer to the vertex, keep a point P here fixed. But as it comes closer and closer to the vertex, it's going to be doing very funny things, because it's wrapping around it, and it might wrap around it many times. So it doesn't, but eventually in the limits, you're going to get something that goes up and bounces back. And that's going to happen whether you come from the left or come from the right. On the other hand, if you try this with a random cone angle, and this is another fun experiment to try, you will get very different things from the two sides. You'll have, on one side, you'll have a limiting case that flows out in one way, and on the other side, it'll flow out in the opposite direction. So it's a cool experiment, which we don't have time for today, but it tells you a lot about the covering space and how it kind of determines the geometry of our surface. So I want to turn our attention in the final stretch to one last surface. And for this, there's one last handout I have to give you. But actually, before I do that, I want to, we can start to pass these out. A second, I think I have one extra. Yeah, we can. And yeah, we'll keep a few here. I think I have too many copies. So the final surface I want to look at is the tetrahedra. And the question I want to ask is, how many geodesics are there that connect two given points on a tetrahedra? The same question we asked earlier. And yeah, so we've seen that on the cylinder, there's infinitely many. On the cone, there's finitely many. It depends on the cone angle. And of course, the points should be randomly chosen. They shouldn't be some weird configuration. On the tetrahedron, how many geodesics are there that connect 2 points on the tetrahedron? So let's construct a tetrahedron and see. So this worksheet is to help you construct a tetrahedron. And these two things here, so the instructions now are to just, first of all, these are just for fun. These, we're not going to use these two small ones today. I just added them because there's extra space, and if we're paying for color prints, might as well add something extra there. We're just going to use this larger tetrahedron. So I want everyone to cut this out right now and include these tabs when you cut it out, because those will help you assemble the tetrahedron. So just cut this out. These you can keep aside for later. These are just souvenirs. They do have some meaning, which I'll tell you at the end, but we're not going to use them today. So this you can just keep and take home. But this is for our use today. So cut this out, fold it up, but do not tape it yet, okay? Don't tape it. Later on you can tape it, but right now just cut it out. And again, the question is, P is now the point at the tip of the yellow lizard's nose. Q is the point at the tip of the red lizard's nose. How many geodesics are there from P to Q? That's the question we're thinking about now. But again, cut this out, don't tape it up yet. once again, one question to have in your mind, are there finitely many geodesics between P and Q or infinitely many? If there's finitely many, how many? Something to think about. Did you get a sheet? Did you want? Okay, okay. We have extras, so. Yeah, if you want, we have extras. So. If you want scissors, there's extras, but no pressure. Oh yeah, I forgot to show. There's also a model I made today morning, just showing 4 geodesics between the points. So this one is a 90 degree. This is a 90. This is actually a little less than 90, which is why I'm able to get this. So if this was a 90 degree, this would be impossible. I cheated a little. I made it less, and that's how I got the second self-intersection. So another question to think about is how many self-intersections can it have on the cone? And actually, on a 90 degree cone, this would be impossible. This one here is also a little less than 90, but I have four geodesics between these two. So. Okay. 4 between P and Q, you've already found. Okay, interesting. So yeah, everyone keep working on this. I'll come and see what people are doing. So what do you have? So this is a very good idea. I think you're on the right track. I think check your unfoldings a little bit. Something's a little funny to me about the way that this is unfolding.
These are all equilateral triangles.
They are. They're all equilateral triangles.
All of them will unfold exactly as mirror
So,
images.
so what you've drawn here, just to clarify, so there's only one on this. There's only one copy of P, one copy of Q. So what you've drawn here is 4 copies of this whole thing,
Of
right?
this whole thing,
Which
yes.
so yeah. So each of these is so now in that case, when you so think about what's happening when you unfold. Something feels a little off there. Just try and go over that part. So, yeah. Yeah, you had your hand up? You think infinite? Intuition, okay. Okay, interesting. Okay. So, okay, what is it? Showing? From the yellow nose to the red nose. Does it come back to where it started? Just check. Yeah. Yes. Yes, but reflection is not the right word. Yeah, reflection is not the right word. But otherwise, you're on the right track. Yeah. So I know a lot of you are thinking about this in interesting ways. So a few people are trying to think about an N-sheeted covering, right? Because that's what we did for the cylinder, that's what we did for the cone. But even before you do that, I think it's a good idea just to play with it like you're doing. See if you try and put a geodesic on it, what happens, what it looks like. What do the geodesics look like? Because that actually tells us a lot about the behavior. What did you get? Oh, nice. Okay, so that's one. But okay, interesting. That's a nice one. Yeah, so there's actually quite a few geodesics that I've already seen here. Okay, so a few people, so any intuition for what's happening? Has anybody seen anything interesting? How is their geodesic behaving? Do you feel like, does it feel more like the cone case or more like the cylinder case? Maybe that's one question. Cone? So what do you think? Finitely many or infinitely many geodesics this time? Finite? Finite? Okay. Let's see. So let's actually, we don't have that much time, unfortunately. Otherwise, there's a lot of fun. There's a lot you can do just by exploring this with these physical geodesics. But I think because we don't have that much time, let's go to this idea of the covering again, the N-sheeted covering. But what is an N-sheeted covering going to look like? So a few of you started working on this, but I don't know if anyone has quite gotten it to work out yet, because it's a little different from the cases we've looked at so far. So let's just do a one-sheeted covering. Everybody has a one-sheeted covering already, right? You unfold, that's why I didn't want you to tape it yet, because now you can unfold your tetrahedron and you have your one-sheeted covering. So suppose we want to make a two-sheeted covering. The logic, again, is if you launch a geodesic from somewhere, we want to be able to follow it. We want to know where it goes next. So where does it go next? So everybody unfold your tetrahedron now. Just everybody unfold it. And try and see on the unfolded thing, if you kind of imagine continuing a geodesic beyond the edge, where is it going next on the tetrahedron? Which part of the tetrahedron is it? Where does it go to from here? Like, in other words, in the assembled tetrahedron, this edge is identified with which edge? Yes, so not mirror image, that's not quite the word. The top, exactly. So it's just that you kind of zip it up, right? You kind of attach this to this. So this geodesic, it's going to continue over here. Does everyone see that? So if we want to do a two-sheeted cover, the second sheet should be what? I mean, so now everybody has a partner, right? You're sitting next to somebody. So your partner can provide the second sheet. So where would the second sheet go? Try and, with your partner, figure out where would you want to place the second sheet in order to give you a two-sheeted covering. So if you imagine it going out, so if you take your sheet as the second sheet, how would you want to position it, orient it? So make sure it's oriented in the correct way to actually give you where it goes next. Sure? Can you show me? Nice. Yes. Yeah, exactly. And now maybe you can team up with even more people and you could do a three-sheeted cover or a four-sheeted cover. So has everyone gotten the two-sheeted cover to work? So it looks like, hopefully everybody got something like this for their second sheet, right? What if you continue it further? Where would the third sheet be? How would the third sheet be? If we have a third sheet here, how would it be oriented? Same as the first. Exactly. So like this, you can actually, how many people are there? There's about 82. We could do an 82-sheeted cover if we wanted. But we won't do that now. We don't have time for that. But you can keep adding sheets, right? And a few of you actually said that the sheet, actually, it's interesting. Quite a few people said that the next sheet should be a reflection. But actually, reflection is not the word I want to use for this. A better word to use, a more accurate word for what's happening from one sheet to the next is rotation, right? So it's not a reflection, it's a rotation. So each time we add another sheet, we're rotating. What's our axis of our center of rotation? To get from the first sheet to the second sheet, it's a rotation about this point, right? This is the center point. And it's a 180-degree rotation about that point. So each time we add a new sheet, that's what we're doing. And amazingly, there's no inconsistency. We can kind of go from here to here, or we can do it this way, but they agree on the sheet. They agree on the orientation. So in this way, our n-sheeted cover, we can keep going. We can keep building it up further and further and further, and we can fill the entire plane. So I've just given an n-sheeted covering where n is, I don't know, 10, 12, something. But this is how we can create an n-sheeted cover and help us solve the geodesic question. So now, how many geodesics can we find containing both points P and Q? Back to that question. So, infinite, yes. And why is it infinite? Well, we have our P's and our Q's all marked here, and I get one geodesic for every sheet, right? I can connect this yellow nose to this, to this red nose in our original sheet. That's in my first sheet. I can connect it to this red nose, or this one here, or this one here. So in every sheet gives me a new red nose, and each of those I can connect it to, and I will get a new geodesic every single time if, I'm cheating a little bit, if these P and Q are in general position. If they're randomly chosen on the plane, then I'll get a new geodesic every time. In other words, if the slope of PQ is an irrational number, let's say. So, because if otherwise, I'll have some redundancy. So we'll see why in a second. I'll get to that in a second. But if the points are not in general position, some of these geodesics will be redundant. So we have to make sure that they're randomly chosen in that sense. So final question today, and this is a very important question because it ties into a lot of other branches of mathematics actually. Can you find a closed geodesic? I'm adding one word here. A closed geodesic, meaning finite length, containing the point P. So P is still, I didn't mark it here, but P is still the yellow nose. I'm ignoring Q now. Q no longer exists. What are the closed geodesics containing P? How many such geodesics can we find? So I'm just showing you the n-sheeted cover. I've just marked all my P's here. How many are there? Are there still infinitely many? Maybe there are, but we do have some clear redundancy here. That's the problem. So we do still have, and so there's a few problems actually. So before the redundancy, there's another problem, which is that suppose you want to connect this yellow nose to this yellow nose. What's happening here? Anything funny happening with this geodesic? Is there anything, if you actually do it on your tetrahedron, does it work? Or is there anything slightly fishy about it? Anything that's slightly fishy if you look at it on your sheet, on your assembled tetrahedron? It's going through this point. What is this point here? It's a vertex point. So maybe that's okay. It depends on your religion, your philosophy, your outlook. Because this is another orbifold, so maybe it's okay to continue it through the vertex. It does work out. Its limit from this direction, same as the limit from this. But it's literally hitting the vertex and bouncing back. So it's not very satisfying. It's literally going from P to the vertex and bouncing back to P. That's what it's doing, right? It's kind of repeating, it's backtracking. So it's not a very nice closed geodesic. But luckily it's easy to exclude those because this one just hits this vertex and bounces back. But it turns out the ones that do that are precisely the ones that are on these opposite orientation triangles. So we can avoid, if we avoid those, and instead we just think of this as a unit, instead of the triangle, think of this rhombus as a unit. Now we get one geodesic for every rhombus. We get one geodesic here, one here, one here. So these are 1, 2, 3 geodesics. Another one here. But we have another problem, which is what you mentioned, which is now we're here and we have this redundancy. So not every new sheet, every new rhombus gives us a new geodesic. And since we don't have that much time, I'll leave this as an exercise. But in fact, there's one geodesic for every rational slope P over Q, where P and Q are relatively prime, co-prime. Because when they're not co-prime, that's when this redundancy happens. So if, this geodesic here that we get from this rhombus, it's the same as the one we would get from this rhombus up here that I haven't drawn. Can everyone see that? So in general, if we get the same slope, it's going to be the same geodesic. So it's really distinct slopes, distinct, you go over p times, you go over q times, and you go up p times. And that each time you do that, you're getting a different rational number, and that corresponds to a different geodesic. So these are the different geodesics you get, and there are infinitely many. And this covering space lets us see them very carefully and enumerate them. They're just in one-to-one correspondence with these PQ pairs that are coprime. So rational numbers. So there's one slope for every rational number. We do have to make sure P is in general position. In the extreme case that P is a vertex of a tetrahedron, then there's no closed geodesics through P. This is something that's a little, again, this is something for those of you who are interested, I recommend playing with this and checking this out. There's no, and maybe you can even prove it, that there's no geodesic through P. Crazily enough, this was something that was proved formally in 2015, not long ago. It's not that difficult, but she and her collaborators, Diana Davis and her collaborators, proved this along with the cube. So the cube is quite a bit harder to prove, but in both cases, there's no closed geodesics from a vertex back to itself on the tetrahedron and the cube. Right after she proved it, others proved that the same thing holds for the octahedron and the icosahedron. And then in 2019, a mathematician, Jayadev Arthreya, showed that there are closed geodesics on the dodecahedron. So that's the only Platonic solid that has closed geodesics from a vertex back to a vertex. So there's a nice YouTube video on this, if you're interested in checking it out. Finally, the final exercise I want to look at. So we've talked about closed geodesics on tetrahedra. Notice something, some of you may notice this, on your tetrahedra, when you actually found a closed geodesic, the geodesics never cross themselves. And this is very fun to play with. If you actually try and, when you do glue up your tetrahedron, you can see that any geodesic you make, you can send it off in any way you want. It'll rotate around in many ways, but it'll never cross itself, any closed geodesic. And why does it, and that's an example of what's called a simple geodesic. Why, so a simple geodesic is a geodesic with no self-crossings. So why does this happen? Why does, and I don't know, does anybody have an example of this just to show us? Because it's something that's kind of cool. If you haven't, does anybody have an assembled tetrahedron? And I think you had a nice example. One of you, I thought had a nice example. But a closed geodesic on your tetrahedron that, just so we can see whether or not, just so we can see that it's actually simple. It doesn't cross itself. So it comes back to itself without crossing itself. Yeah, so any example of a closed geodesic on a tetrahedron? It'll be nice to see one example. Okay, it's a little difficult. Fine. So, nice. So, and you can see that it's closed, right? It came back to where it started. Yeah, this is really nice. So this kind of just very, very nicely cuts, it's like slicing the tetrahedron by a hyperplane. You can kind of see, right? Her geodesic, if everyone can see, it's closed. It's a perfectly closed geodesic. And it comes back to itself at the right angle. So it's at the correct angle that it started with. So it's almost like slicing the geodesic by this hyperplane. Nice, thank you. So but why, and in fact that you'll find as you play with this more, that keeps happening. So why does that happen? Well, there's a very nice explanation for this using the n-sheeted cover. Because if you imagine the geodesic from, just to give one example, we have a geodesic from this nose, to this copy of the nose. It's really the same nose on the tetrahedron, but this copy of it in the cover. So I can do this geodesic. What does this look like on my original tetrahedron? Well, after it leaves this edge, where does it go? Where does it go next from here? Remember, this edge connects to this, is identified with this edge on the zipped up tetrahedron. So this point is really this point, right? So if it's continuing like this section here is actually over here, right? So it's going along like this, and then it's coming down like this. And where does it go next from here? Well, it's going to the nose, but it's really, on the original tetrahedron, this represents this part. So it's doing this. So on the original tetrahedron, what can we say about these two lines? They're actually parallel to each other, right? And why are they parallel? Well, remember that how is this sheet related to this sheet? It was not by a reflection, it was by a rotation. And it was a rotation by how many degrees? 180 degrees. So we're taking this line and rotating it 180 degrees to see where it goes next. And then again, we're rotating by 180 degrees to see where it goes next. So if you take a line and rotate it by 180 degrees, it's going to have the same slope. So you keep getting parallel lines. So this geodesic, and this is true for any geodesic you draw. You can have a very complicated one, and it's just going to be a series of parallel lines on your tetrahedron. So it's never going to cross itself. So you'll get a simple, simple geodesic this way. So as a result, one very interesting consequence of this, you can produce arbitrarily long, simple, closed geodesics on the tetrahedron. You can choose an n-sheeted cover, an nth sheet very, very, very far away, and you can look at the geodesic going there. It's never going to cross itself. So, for example, on any of your tetrahedron, you could literally have, you can literally find a geodesic on it that never crosses itself, but whose length is the length of the equator of the Earth, 40,000 kilometers. And you can literally have a geodesic like that on this tiny tetrahedron that'll never cross itself, come back to where it started, be a simple closed geodesic, which is pretty cool. And in fact, if you do any geodesic, since it's a simple closed geodesic, it's dividing your tetrahedron into two parts. And some people have actually made some interesting art this way. You can take a long geodesic, and it divides the tetrahedron into two equal parts that together, their union forms the full tetrahedron, and their boundary is that geodesic. So you can do fun experiments like this. And you can really make your geodesic arbitrarily long. Very interestingly, just 2-3 years ago, Vladimir Protasov, a Russian mathematician, showed that tetrahedra are literally the only convex polyhedra in R3 that have this property, that admit arbitrarily long, simple closed geodesics. So this is not true on the cube, this is not true on the dodecahedron, it's not true on any arbitrary convex, random convex polyhedron you build. The tetrahedron is a very special creature. It's true for non-regular tetrahedra, but tetrahedra are the only polyhedra that have this property, that let you draw arbitrarily long, simple closed geodesics. And it's an open question for anyone who wants to think about it. Are there hyperbolic convex polyhedra that admit arbitrarily long, simple closed geodesics? Hyperbolic tetrahedra fail in this regard. They do not. But are there others? We don't know. So that's an open question even right now. So I don't want to go on and on. I know we don't have that much time and you must be hungry. So I will, and I want to have some time for questions. But there's a lot more one can say. There's a lot more one can explore. Simple closed geodesics, it's a very interesting story behind them. I mean, this is just one aspect. But like I had mentioned earlier, the exploration of them, it goes back to Poincaré in 1905. He conjectured that any surface that's the shape of a sphere, any surface without holes, has at least 3 simple closed geodesics. Hilbert worked on that problem, I believe, and then it was eventually proved, but there was many errors in the proof in the 1920s by Lusternik and Schnirelmann. I don't know if I'm saying their name right. And it was finally proved in the 80s by a couple of mathematicians, including Uhlenbach. Meanwhile, in the convex case, people like Diana Davis, Arthreya, Jayadev Arthreya, yeah, they worked on very interesting cases there. And the other place that it's been made a very surprising and very important appearance in the last 10, 15 years is in the work of Mirzakhani, who won the Fields Medal in 2014. So what she became very famous for, and when she after her PhD was a method of counting simple or giving estimates for the number of simple closed geodesics on hyperbolic surfaces, smooth hyperbolic surfaces. So something called the prime number theorem of geodesics. So it's something you can look up if you're interested. But that's tied in. That's again related to this idea of a covering space. So her counts, her estimates for the number, end up using information about not just covering space, but also the moduli space, something called the moduli space, of all possible metrics on that surface. So that's way beyond the scope of this talk, but somehow simple closed geodesics and the counting of them plays a key role and ties into a lot of theoretical physics as well, including conjectures by Ed Witten, which her work managed to clarify. So there's a lot more to explore, and if you were interested in exploring these things in a more hands-on way, I really liked, these are some books that I used to kind of design this series of activities. And yeah, I think we'll finish there and have time for some questions that way.
Okay, so questions? Yeah.
Yeah. How, so you're asking what is a hyperbolic tetrahedron basically? So you can think of it as just a tetrahedron. So one way to think of it is in hyperbolic, three-dimensional hyperbolic space, take a tetrahedron. So so basically 4 points, join them by geodesics, and there'll be a natural way to find minimal surfaces for the faces. So that's one way of doing it. Or yeah, you could also think of hyperbolic. Yeah, I think that might be the best way to think of it. Yeah. Okay, any other questions?
Yeah. So I guess you can ask these questions during dinner time.
Yeah.
You'll join for dinner. So I invite Professor Indulekha to just hand over this little memento. You're asking how long the resonance is? No, this will show you inside that.
Thank you.
Thank you. Yeah, have a seat. So I guess people were supposed to be around telling me, whom to thank and so on. So, but in any case, it is, it's wonderful that all of you have been very active, and without your participation, I think this has been very lively both these days. I wonder if it had been 4 days, what would have happened? But in any case, these 2 days have been very active for all of us, and you can see everybody has been present. Professor Mukunda has been present for every talk, not even sleeping, and I was more or less sometimes falling asleep. But all the talks were very wonderful, and really thank all the speakers for a diverse, variety of topics. Let's give them a big hand, the speakers. And I think I should mention some names here about. Mrs. Geeta, her son is not well. She had twin children, so that's why she left. Otherwise, she would have mentioned the names.
Okay. Wow. Okay.
So then I would like to thank the housekeeping staff, Mr. Ravi Kumar, Mr. Venkatesh Datta, Gangadharaya, and Mr. Amit Rama, Mr. Manjunath, Transport and Accommodation, Mr. Sumesh, IT Department, and your Mr. Arun, Mr. Praveen. Thank them all. And Pushpa, and Jay Jimin, and Mr. Nagesh, the catering. I hope the food was good. And Mr. Rupa and Mr. Ravindra, and coordinating with the SRF participants. And finally, Ms. Vaishali and Mr. Vivek Chauhan, comparing feedback with participants. And I think the certificates will be awarded in dinner time. So thank you for coming, and enjoy.
Oh yeah. Oh, yeah. So